Hello and welcome to another Java tutorial. In this tutorial, I'm going to discuss the most important topic in scientific computing, which is solving differential equations. And there are generally two types of differential equations. The first one and the easier one or the simpler one is ordinary differential equations. And the second one, which we typically deal with in physics, is partial differential equations, right? So ordinary differential equations, or ODEs, are simpler and easier to solve and understand, so I'm going to start with them. And what are ordinary differential equations? So ordinary differential equations involve only one variable, all right? You may have multiple functions, but they are all functions of one variable, which in physics is typically time, right? If we want to solve the equations of motion for a system of particles, for example, our independent variable is time, and then the other variables or the functions are the positions of the particles, for example, okay? So in the ordinary differential equations, we only have one basically variable, which means all of the functions are one-dimensional functions, all right? And the most important class of equations are linear first-order differential equations of the form y prime equals f of x and y, all right? Now this involves only one variable and one function, right? So the question is, we have x, we know the derivative as a function of x and y. So it's not just a function of x, because if y prime was given as a function of x, we just integrate it from whatever point to some other point, and then we find y, right? But the problem arises when we actually have y prime in the format of x and y, a function of x and y. So the y prime, the slope also depends on the y itself, the function itself. And any sort of solving the equation, differential equation, basically translates into some sort of integration, all right? Because integration is the opposite of the differentiation. So if I want to solve the differential equation, I have to do the opposite of that, which is basically doing some sort of integration. And again, the complexity here is that the derivative of the function is given in terms of x, the variable, and the function itself. This is the most general case, right? And there are a few very limited number of analytical approaches, and we cannot use these analytical approaches in a most general sense. So one analytical approach is the separation of variables. So y prime is dy over dx. If f of x and y can be separated into the multiplication of two functions, one of them, or the first one, g1 of x, only is the function of the x variable, and then the second function, g2 of y, is only a function of y. And then we can separate x and y. So we bring g2 on the left and dx on the right. We end up with dy over g2 of y equals to g1 of x dx. Now this problem at the moment is basically a simple integration, because on the left side, if we integrate, we only have the variable y, so we can integrate this. On the right side, we have only variable of x, so we can integrate, okay? And then we find an implicit equation of y, because here, when on the left side, when we integrate, we get another function, some expression which is a function of y. And on the right side, we get an expression which is a function of x. And the goal is to find y in terms of x. So it's an implicit equation which we can then solve to find y, okay? But this is very limited case. In most of physics problems or any sort of engineering problems, we won't be able to do this, all right? So in general, if we want to look at numerical ways of solving this differential equation, y prime equals f of x and y, right? There are two types of problems, right? One is the initial value problem, IVP, which tells us, okay, I have been given this equation, y prime equals f of x and y, and I also know the value of the function at some starting point. Let's call it x0. I know that y at x0 is y0. This is called the initial condition. Now I want to know the value of the y of x. at any given point after this x0, right? And in general, I should be able to numerically solve that, because if I know the derivative, I know how y is changing, because derivative by itself is just the rate of change. That tells me how fast or how slow the function is changing, right? That's the behavior of the change of the function. So I should be able to extract the information for the later times by knowing the value of the function at some point, and also knowing the information of how the function is changing. Now, another set of problems are called boundary value problems. This typically arises when the physical variable is not time, it's more like position, x, y, z. And even in the simplest case of y prime equals f, x, and y, right? The boundary condition, instead of initial condition, we can have a boundary condition that gives us a mix of x0, x1 at the end of the interval, or the point that I'm trying to find y, and y0 and y1. So y0 is the value of the y at x0, and y1 is the value of the function at x1, right? So we might not know y0 or y1, but we can be given something like this. So x0 and x1 are given, these coefficients m0, m1, n0, n1 are given, and we are told that okay, there is a general relation like this is established between the value of the function at x0, the value of function at x1, and x0 and x1, right? So this is a more general case than the initial condition. So in the initial condition is basically m1 is 0, n1 is 0, so we can solve for y0 in terms of x0. But in general, it might not be the case. We might have we might know the value of the function at the endpoint, which is the final condition instead of initial condition. So in general, we can have a boundary condition. That's a more general way of having like a condition to be able to solve, because in order to solve this y prime equals f of x and y uniquely, we need to know some sort of in addition to differential equation, we need to know another information, at least one equation that describes the value of the function at some point. We need to be able to have that. If we have that information, we can uniquely solve the equation. And if the value of the function is exactly at the initial point, we call this initial condition. If there is a mixture of the values of the functions at different points, it's called boundary condition. Okay? Now, if only y0 and y1 show up in the boundary condition, we call it a Dirichlet boundary condition. If the derivative of the function show up, instead of the value of the function itself, the derivative shows up, we call it a Newman boundary condition. If both y prime and y show up, we call it in general a mixed boundary condition, or Robin boundary condition, sometimes called mixed boundary condition. And again, boundary conditions have a more general sense when we are solving partial differential equations, and the initial condition has more general sense when we are solving ordinary differential equations. All right? And in classical mechanics, like solving for the motions of particles, we always end up doing something like initial value problem. Okay? In thermodynamics or classical electrodynamics or quantum electrodynamics, we typically have partial differential equations of positions in a space. So we have boundary value problems, okay? So we are given this ordinary differential equation. This is the most basic and the most general form of the basic equation, y prime equals f of x and y. And we are given the initial condition. And we already know that in general finding analytical solution is rare. So we are resorting to numerical solutions. But we want to have a numerical solution with very good accuracy. That's the key point. And there are common numerical approaches, and it takes a long time if we want to discuss all of the methods. But here I have put some of them, and there are two most important ones, and basically all the other approaches can be somehow derived from the ideas of these two. So Euler method, which is sometimes called the forward Euler method, this is the most basic one and the simplest one. Backward Euler method, which is which is a little bit more complicated than the forward Euler method, because it's an implicit method. It gives you an equation, and then you have to solve again for y to find the value of the function y. Midpoint method, it's explicit, so it gives you the value of the y at each point directly. Runge-Kutta, we are going to look at the fourth order Runge-Kutta, which most of the time is called RK4, Runge-Kutta 4. And again, all these methods, Euler, midpoint, all other methods are basically a subset or a special case of RK4, or Runge-Kutta in general. So for example, Euler forward method is Runge-Kutta 1, first order Runge-Kutta. Midpoint is kind of like a second order Runge-Kutta. And there are special cases again of the same Runge-Kutta family, which is Cash-Karp, Fehlberg. And I'm going to focus on Euler method, midpoint method, briefly discuss the midpoint method, and then also the Runge-Kutta 4. So RK4 has a very good accuracy, and it is commonly used in most of the frameworks, numerical frameworks. And one key point that we always have to keep in mind is that different differential equations in general, whether it's a partial differential equation PDE or ordinary differential equation ODE, depending on the type of the differential equation, we probably end up choosing different methods for solving the equation numerically, and we typically don't use the same method for any type of differential equation. And that has to do with the stability behavior of these numerical methods. If if the differential equation is somehow causing, for example, the Euler method to have an ill-conditioned behavior, the behavior is not very stable, then we resort to other methods, okay? So choosing which method to use depends really on understanding how the differential equation behaves. But in general, especially for ODEs, RK4 is a very good approach. It's commonly used. And if you want to look at the full list of methods, of numerical methods for solving differential equations, look at this Wikipedia list. So en.wikipedia.org/wiki/list of numerical analysis topics. So this is general list of all the numerical analysis. And there is a section which is numerical methods for ordinary differential equations. All right, so you can look at this, and it gives you a full list, and it directs you to the pages, Wikipedia pages, that have all the information on those, on all the numerical methods. But again, Euler method, the forward method, midpoint method, and the Runge-Kutta fourth order, RK4, are the most common ones. Especially RK4 has a very good accuracy. The order of error is very low, so it has a very good accuracy. So we can mostly use RK4 for most of the ordinary differential equations that we encounter in physics, engineering, and other fields. Okay. And again, solving differential equations is kind of like doing some sort of numerical integration. But this is a more general problem than numerical integration, because in numerical integration, essentially this function f of x and y does not depend on y. We have y prime equals f of x, so y becomes the integral of f of x from some point to another point. Okay. For example, in that case, if I only have f of x and I am trying to solve the initial condition problem, y of a is given, then y at some point, y of x is just integral of f of x from a to x. Okay, so it's just numerical integration, but this is a more general problem than just numerically integrating a function. But there is a close relation and ties. All right, so the first method is Euler method, and it's very simple. It's like so simple that it's very easy to understand. And again, we have one dimensional ODE, which means we only have one variable x, and we have a function y of x, and we are trying to solve the initial condition. Y of a is given, so at the beginning of the interval y of a is given, let's say y0, and we are asked to solve this differential equation. But what does it mean when we say solving this differential equation? It means that if I give you any other point after a, I should be able to find y of that point, right? Let's say I want to find the y at some point like b, or I want to find the value of the function at any later point after a, right? So here's a diagram. Let's say this is some sort of our function that we are looking for, and at point a the value of the function is given, and we are asked to solve this differential equation, which means at a later point, let's say b, I want to know what the y of b is, and I should be able to do this for any point after a or before a, for what for that matters. Before a or after, we typically, because of the initial condition, we typically look at the points after a, right? So how do we do that? Let's say a is given, y of a is given. I have the equation y prime equals f of x and y, and I want to find y of b. B is a later point after a, right? So the way I do it, I discretize, again, some similar to numerical integration. I discretize this interval from a to b into n subintervals, okay? And then from a forward, at each point, I in those intervals, subintervals, I approximate y prime using a very simple, I'm going to write it down here, simple forward approximation of y prime, okay? And we know that for forward approximation of the y prime, the order of error is always h. It's a linear order, right? The accuracy is order. So in order to get a good accuracy, we have to have a very small h, but we don't worry about that because we have some tricks that we learned in the sequences and series about accelerating the convergence. So we don't need to worry about h being very small, all right? But we're starting with a very simple way of solving a differential equation. I discretize into n small subintervals, so I choose n points from a to b, and then let's call them x0, x1, x2, etc. And then at each point, I write y prime as an approximation y x plus h minus y of x divided by h. And h is the length of each subinterval, and I'm doing a uniform partitioning, so the length of all the subintervals is the same, h, which is b minus a divided by n. N is the number of subintervals. So y of x plus h minus y of x divided by h is y prime, which is f of x and y. So if I rearrange these, I can find the value of the y at some later point, x plus h, which is the value of the y at some point, y of x plus h, f of x and y, and this y is evaluated at x, okay? So if I know the x, the value of the function at some point, I can approximate the value of the function at a very small step after that, all right? And we know that if I have, I increase, the error is order of h, or 1 over n, the number of subintervals, okay? And if I start from x0, which is a, and do this all the way to xn, which is b, I can find an approximation for b, for y at b, right? And then if n goes to infinity, I have infinite number of subintervals. This error goes to 0, so the approximation gives me so this approximation becomes exact in the limit when n goes to infinity. So what does all of this mean? It means that we end up with a sequence. So this is my function, x0 is a, given, y0, this is my initial condition, is given, and I'm looking for y at point b. B is a later point after a, okay? So I do a uniform partitioning from x0, which is a, to xn, which is b, and I create a sequence. This is very important. I'm creating a sequence that converges to y of b as n goes to infinity. and the nth term y of n is actually the value of the function, the approximation of the value of the function at b. All right, so as I increase n, I just increase the number of subintervals and I end up with this sequence y of n. So y1 at some point h is b minus a over n, right? y1 is at x1 and x1 is x0 plus h. y1 is y0 plus h times the slope at y0, which is f of x0 and y0. Remember, y prime is f of x and y. So I find an approximation for y1, and from here x1 y1 I find an approximation for y2, which is y1 plus h times f of x1 y1, and all the way to yn. So I start from here, draw the tangent line and go to x1, and then draw the tangent line, go to x2, etc., etc., all the way to yn. And as n goes to infinity, yn approaches yb. All right, so I have a sequence that converges to the value of the function that I'm looking for, right? So the problem, the Euler method basically boils down the problem, basically it summarizes the problem into finding the limit of a sequence. And because we know that if the function f of x and y doesn't have any singularity at b, it's well behaved, then y of b should exist. So this sequence should converge to a number, right? It shouldn't go to infinity, it shouldn't blow up or anything. So I have a sequence. I'm using a very simple approximation of the derivative to find the yn. The error is very large because it's proportional to 1 over n, right? So error is bad. So what I'm expecting here is that this simple approximation, and this is basically the simplest way of going about it, finding y of b. I'm expecting this sequence y of n to have a very slow convergence. Again, that's because of the error, which is 1 over n, right? But I already know the trick of how to accelerate the convergence, and because the error is 1 over n to some power, the behavior of the error, I just use the Richardson acceleration. Okay, so here's the code. We want to implement this Euler method, very simple way of solving this initial value problem in Java. So f of x and y, define it as a functional interface. All right, this is the way we do it always. So let's call it deriv function. Deriv function means the function based on x and y that gives me y prime. All right, and it has one public abstract method, value, and takes the x and y. All right, and then we define a sequence. Remember, yn is a sequence that converges to the value of the function at point b, and b can be any point after a, any later point, right? So we define a sequence that finds yn for a given endpoint b. All right, so here b is basically x1. I changed the name in the code here, so this x1 is basically my b. Don't confuse it with the x1 that I had here, right? It's not here, it's b, some later point after x0. x0 is my initial point a, and we're doing uniform partitioning. That's the whole point. Typically for solving differential equations, we don't do non-uniform partitioning. We don't do any quadrature method because it just gets way complicated. And if you recall, in the numerical integration, I said that for just purely trying to numerically integrate a function f of x, we actually prefer non-uniform partitioning because they always end up with a sequence that converges quadratically to the value of the integrand, to the exact value. Any uniform partitioning always has a linear or sublinear convergence. You cannot ever get a quadratic convergence. And again, that's because the behavior of error is 1 over n or 1 over n to some power. So you cannot get away with linear or sublinear convergence. That's the problem. So we're doing uniform partitioning. Okay? So h is b minus a over n, So in the code, I'm writing a method Euler sequence, which means this indicates that this generates a sequence based on the Euler method, right? A yn sequence based on the Euler method. So if n is 0, I'm at the initial point, just so I return y0. y0 is a variable that holds the value of y at at x0, okay? Else, if n is greater than, and note that I'm using a multi-line lambda expression. So n goes to something, this is a lambda expression that returns a sequence, all right? And if you're not familiar with how we implemented the sequence in Java, go back and look at my previous lectures on sequences and series in Java. So we define x and start with x0. We define y. At y0, h is x1 minus x0 over n. Remember, n is an integer, but I'm converting it to double to make sure x1 and x0 are double, but I'm converting also h to n to double just for safety. And then we're going to create all this y1, y2, y3 all the way to yn. So it's a for loop from I equals 0, I less than n, I plus plus. Note that n is the variable of the lambda expression, all right? Because I'm looking for yn and I'm starting from y0. So y holds the value in each loop of the for loop. I get y0, y1, y2, etc. So y is y. So originally it's y 0, and then add the h times the function value at x0, y0, I get y1, all right? And now y is y1 plus h, the value of x, which is now x1, because in each loop iteration I add h to x. So now I'm y1 plus h times the function at x1, y1. It gives me y2, okay? And then now y is y2 plus, and x is x2. So y2 plus h times the value of the function as x2, y2, it gives me y3. So eventually after n loops, n iterations, I end up, the value of y is yn, right? This sequence. So I return y at the end, all right? So this is how I'm generating this Euler sequence, the yn sequence that is going to converge to the value of the function at x1 or at b, all right? And again, this is supposed to have a very, very slow convergence because of the order of the error. This approximation, the forward difference approximation for the derivative has a very poor error, order of h or order of 1 over n. But then I apply a Richardson acceleration, and you probably can guess third order or fourth order Richardson acceleration should give me a very good error, like 1 over n to the third power or 1 over n to the fourth power. So Euler method plus Richardson acceleration is that's all that there is about solving the ODEs using the Euler method, or basically trying to find a very simple way of solving the Euler method. We find the sequence, we accelerate it, and we get a very fast converging result. And here's one example. So in this example, y prime is minus y. So the function of f of x and y is minus y. It doesn't even depend on x. And the initial condition is y of 0 is 1. So at x equals 0 is 1. And the exact solution is e to the minus x. E to the minus x, right? So if I take the derivative, y prime is minus e to the minus x. So y prime is minus y. So it satisfies the equation. And y of 0 is 1. So it also satisfies the boundary condition. And this function dies very rapidly, right, as x grows. At let's say I want to find the value of the function at 0.5, and analytically the exact value is 0.60653066. And let's see how the Euler sequence does as we increase n. So this is the code, example 1 here for this is the code. So I define a deriv function, which is basically my f of x and y. And so x and y using a lambda expression, which makes life very easy to define the function. X and y goes to minus y, all right? So this is f of x and y. And then I create an object called ODE solver. So I create an ODE solver and implemented this Euler sequence method in it. ODE solver takes the function, the degree function, the x0. So let's write this down. So this is x0, the initial point, and then the y0, the value of the function at x0. Okay, so the initial condition, we can pass it directly to the constructor. And x0 is 0, the initial point, and the initial value is 1, right? And then I create a sequence yn, which is ODE solver dot Euler sequence, at which point, at which x is 0.5. So I create a sequence, a Euler sequence, that converges to the value of y at 0.5. Okay, so I'm looking for this, and I know that as I increase n, as I move forward in this sequence, I should get a better and better approximation for y of 0.5. All right. So let's plot this. So I create an array of indices. In general, it should be integer, but I just stick with doubles. New double. Let's say 100 terms. So I'm going to go from y0 to y100 in the sequence, right? And then yn values, new double, the length of the indices, and then for loop, indices I is I, and the yn values of I is yn evaluate at I. All right. And then I create a MATLAB chart. This is a figure object, and plot the indices and yn values, render it to create a GUI window. I turn the markers on, and then the x label is number of partitions, which is basically n, right? If we go back, n is the number of partitions that we do from A to B. Y label is y of 0.5 value, right? We're looking for that, and fig.show creates the window. All right, let's see how the convergence works. As I start to increase the number of partitions or increase n, we see that the value starts to converge. So obviously we see the convergence. But after even 100 points, the 100th term in this sequence yn, if I zoom in, you see the value is 0.6058. So we are still like, we have only how many, 2-3 digit decimal places of accuracy. So it's painfully slow. It's painfully slow. So how do we accelerate the convergence? We do, for example, a third order Richardson acceleration. So here's the error, because I already know the exact solution. So I just calculate the error and plot it on a log scale to see very small numbers. And as I put it here, Richardson acceleration is the key to higher accuracy. Why Richardson? Because we already know that all these numerical integrations, or basically this approximation of the y prime, has an error that behaves as h to some power, or 1 over n to some power. That's why it's suitable for Richardson acceleration. As you can see, after 100 terms, the forward Euler method, the one that I showed here, after 100 terms, it definitely converges, but it only has like 2 decimal places of accuracy. But as soon as I apply a third order Richardson, you see the error goes down very rapidly. So at 100, I get more than 3, 4, 5, 6, 7, 8 decimal places of accuracy. Now what you can clearly observe here is that as we accelerate the convergence at very large numbers, we always end up with some instability. I mean, the error is still very small, but it starts to oscillate and probably goes back up as we increase. That's why if you use a higher order Richardson, you should evaluate it at a smaller point, like 30, number 30 or number 20, something like that, okay? And here's a plot of the actual function e to the minus x, and the blue is the exact solution. And I'm using a fourth order Richardson on the Euler, forward Euler, and I evaluate the fourth order Richardson at n equals 100 at here. And it's pretty much giving us the exact result. And the last thing that I want to talk about in this lecture is, let's try to look at the speed, how fast it's solving this numerical solution. So So let's head to Eclipse. I have already created the ODE project here. In the ODE, this is my interface for creating the derivative function. So this is y prime equals f of x and y, and use as a lambda expression for very ease of use. And then this is my ODE solver. I have a derivative function x0 and y0. So I'm solving an IVP, initial value problem, right? So this class is solving initial value problem. And the constructor has a derivative function x0 and y0. And this is my Euler sequence. And I have a test class, test Euler. And in the example 1, this is basically y prime equals minus y, f of x and y is minus y, and I'm creating the Euler sequence for 0.5. So Euler sequence, we're looking for y of 0.5, at y at x equals 0.5. So we create an Euler sequence and then look at its limit. So let's do this. So let's create a timer, new timer dot start, and after finding all the values, timer dot end. Actually, let's okay, let's try to just look at the timer dot stop and timer dot show. This just looks at how long it takes to create the Euler sequence and then find all the values, evaluate the sequence. So I'm going to run example 1, 51 millisecond, okay? And as you can see, we have a very painfully slow convergence to the exact value. But it should converge, we definitely see the convergence, all right? Now let's try to get the Euler sequence and then Richardson it. Let's say a third order Richardson. What I want to see is how much more overhead in terms of computation time this transformation adds, right? Because because we know that this is very good in terms of reducing the error significantly. So we want to see how much time it adds to the overall execution. 53. And as you can see, now the convergence is extremely fast. You see, after only basically 8-9 steps, we're there. We don't need to go to 100 there. And this is pretty much the exact result. I mean, the error has 7 decimal places of accuracy. Okay, so this took 53 milliseconds, and if we just go with that, it takes 50 milliseconds. So 3 milliseconds is the difference, but as you can see, it's very well worth the effort. The 3 milliseconds is very well worth it because we get an enormous improvement in the error, right? We reduce the error a lot, like from 2 decimal places of accuracy to 7 or 8 decimal places of accuracy. Just doing a very simple Richardson transformation. A very simple transformation on our sequence, all right? So this was the first step in our journey to look at solving differential equations. Please stay tuned. I have more lectures to come with more details, and I hope you enjoyed this lecture, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. In the previous lecture, I talked about what do we mean by solving an initial value problem for an ordinary differential equation. And we said that in an ordinary differential equation, we always have one variable and one or more functions. And the very basic case is y prime equals a function of x and y, all right? If we can solve this, we can solve basically almost all of the ordinary differential equations that we encounter in engineering and physics. And then we said that there are some common methods. The most basic one is Euler method, the forward Euler method. and implicit methods such as backward Euler method can also be used, but then because it gives you an implicit result, then you have to also solve an equation to find the value of the function. It's not just solving the differential equation. You have to also numerically solve or find the root of an equation because it's an implicit equation. And then we said that there are also other methods with higher accuracy than the Euler method. And the most famous one is RK4, Runge-Kutta fourth order, and some of its derivatives like Kashkarp, Fehlberg, and other versions of Runge-Kutta with different orders. But RK4 is the most commonly used one, so we're going to look at that. Now, for the Euler method, we said that the idea is that if I am given an initial value problem, so y of a equals y0. And we can call a x0, right, the start point. And then when we say we want to solve the differential equation, it means we want to find the value of the function y at some later point. Let's call it b, right, y of b if I know y of a. And we said that in order to do that, the very basic way or the very basic approximation is to write y prime as a simple forward approximation, y of x plus h minus y of x divided by h. And in order to do that, h basically represents the length of a subinterval. So we discretize the interval from a to b into n subintervals, and h becomes b minus a over n. And we said that we always prefer uniform partitioning because of its simplicity. And again, the reason we do that, because remember, we're solving a differential equation. That means we have to do some sort of integration. And integration, numerical integration, always involves partitioning an interval and summing some sequence over that interval, okay? So we get that, eventually we get this equation. If I know the value of y at some point x, I can estimate it at some very small interval after that, y of x plus h, which is y of x plus h times y prime, which is f of x and y. And we said that the error is not good, 1 over n. And this type of discretization leads to a sequence, y of n, that is supposed to converge to the exact value of y at that later point b. So xn here is b. As we increase n, the length of each subinterval gets smaller and smaller, and the error goes down because the error is proportional to h, or inversely proportional to n. But remember that h is b minus a over n, alright? Even if I have increased n, if b increases, so if we want to find the value of the function at some point very far from the initial point, it is always guaranteed that the error gets bigger and bigger as we go farther and farther away from the initial point, right? So we need to have more and more subintervals. So keep that in mind. The error gets larger and larger, or bigger and bigger, as we try to find the value of the function, the solution for the function, at points that are farther away from the initial point, x0 or a, okay? And we said that the idea here is that based on the method that we use, let's say here Euler method, we create a sequence that basically mimics this yn behavior, right? So we have to specify we're looking for a value of the function at some point. I call it x1 or b. And then we create a sequence that converges to the value of the solution of the differential equation, i.e. y of b, given the initial condition x0 and y0. The sequence converges to the value of the function at the point that we're looking for. And then we said that, okay, Euler has a very bad error behavior. It's very slow, therefore it's very slow convergence, and we can accelerate it using the acceleration methods that we've seen so far for sequences. And because the error behaves in a 1 over n fashion, we know that it's suitable for Richardson acceleration. And we demonstrated that by looking at a very basic example. And obviously when we want to look at how good our numerical method is, we want to look at problems that we know how to solve. We have the exact solution. For example, y prime equals minus y, and y of 0 is 1. So this is an initial value problem. Our f of x and y that describes the derivative, y prime is minus y, right? So this is the drill function. And then we create an ODE solver, we give it the function, the drill function, and the initial value x0, y0. And then we create the sequence based on the Euler method. And we want to look at the value, we want to find the value of y at 0.5. So the Euler sequence, this method creates the sequence that converges to the value of the function at 0.5. And we said that even with the 100 iterations or 100 moving forward 100 terms in this sequence doesn't give us a very good accuracy, only 2 decimal places of accuracy. And then we said that as soon as we apply a third or fourth order Richardson acceleration on this sequence, the error suddenly goes down very rapidly, right? We get more than 8-9 decimal places of accuracy. So this is just for finding the value of the function at y of 0.5, this plot. And then we can find the exact, eventually what we are looking for, y of x. So here I'm comparing the exact solution with the fourth order Richardson solution on Euler at n equals 100. And this is the x values. So x0, 0.5, 1, 1.52, all the way to 5. And remember, as I mentioned, as we try to find the solution at farther points away from the initial point, which is 0, the error increases because it's proportional to some sense. It's proportional to the length of the interval b minus a, right? And that eventually brings us here that yes, if I look at the x values, so the blue curve here is the exact solution at any x, right? From 0, which is the initial point, which the function is 1, right? y0 is 1. And then at x equals 50, the function is very small, okay? But I have calculated and plotted it here, right? So this is not the error of the function. This is the exact value of the function. And it's on a logarithmic scale. And because the solution is exponential, so on a logarithmic scale, it should definitely be a linear curve, right? It's just a line. But then if I look at the Euler solution with the even with the fourth order Richardson acceleration, we see that after passing x equals 30, the value of the solution actually starts to diverge from the exact solution. So we get a large error as we move forward in x, right? At x100, the error is even larger. So this is not good because even if we do acceleration, we still get a large error for large values of x, the values that are far away from the initial value. And the reason for that is because in my code, if you look at the Euler method that calculates the value, it gets the Euler sequence, does a Richardson acceleration, but it always finds the sequence at a fixed point, 100th term of the sequence. And because the error grows with b minus a, the length of the interval, one way to remove this problem is to increase this 100th term. So at x equals 50, I have to evaluate the fourth order Richardson at, let's say, 200th term instead of 100th term. But the problem is that then it changes from one differential equation to another. And it's really, we have to examine a couple of things, the nature of the differential equation to figure out what is the best way to adaptively change this number. And that's not easy. But there is a very easier solution to this problem, and that's it. So I know that I want to, let's say, but this particular solution applies when we're trying to look at basically find the solution at many points from 0 to 50, okay? So what I can do is that, let's say I want to find the values of the solution, y of x, as at an array of x values, let's say 0, 5, 10, 15, 20, 25, all the way to 50, okay? So what I do is that I start from x0 and then find the x1 using Euler plus R4. But then if I want to find the value at the later point, instead of starting from the original initial point, I use the previous point as the initial point. What I mean by that is that I know my solution should return an array of solutions, right? An array of y values, each one corresponding to one x value. So I say that, okay, I copy the original initial points, initial conditions, x0 and y0. They go to x0 copy and y0 copy. And then I write a for loop, and I start from the x0 and y0 and calculate the y from the Euler at x1, y1, x1 index 1, right? But then I change the original initial conditions to the previous points. Y0 changed to the new y that have been calculated at the current step, and then x0 is changed to x1 at the current step, right? So what this does is that it calculates the y at index 1. So y at index 0 is y0, and x at index 0 is x0. So these are given. And then we calculate y1 using the Euler based on the original initial condition, but then the initial condition changes, and y2 is calculated based on the y1 and x1 as the initial conditions. So this way, if you are evaluating at a large number of points, the length of the interval always stays very small, all right? And that means the error actually doesn't get large, doesn't grow large as we get farther away from the original initial point. Because, for example, when I'm solving for x equals 50 to find the value of y at x equals 50, I'm not using the initial value y0 equals 1. I'm using the initial value from the previous point that I solved, right? So this way the error always stays as low as possible, okay? So this is a very neat trick or clever trick to avoid this problem. So after finding a solution at x1, use it as the initial point or the initial condition to find the value at x2, okay? I hope this makes sense, because this is a very interesting trick that we can use. And now let's look at what happens when we apply this trick. So this is again, this is the Euler plus fourth order Richardson. So we have this, and now we are applying that trick. So when I'm solving from 0 to 50, let's say 100 points, 100 x values, at each x value I use the previously calculated point as the initial condition, and as you can see, there's absolutely no error. So we really remove this problem. And to see this more clearly in the code, I'm going to go back to Eclipse. In my ODE project, we discussed that we had this ODE class, ODE solver, that gets the initial condition x0, y0 and the y prime function, and then creates the Euler sequence. In the Euler method, we calculate the Euler sequence for a given point, Richardson it, fourth order Richardson, and evaluate it at 100. And now I have this Euler method that takes an array of x values, which are basically the later points with regard to the original initial point, right, x0. And then I want to return an array of y values, which are the solutions, right, at each given x value. So I copy the original initial conditions, and then I write my for loop. I calculate the y using Euler at some x, and then I change the original initial condition to the current values that I calculated, okay? And at the end, I return the original initial conditions to preserve them, and then I return the y array, okay? So this is how we can remove or basically try to reduce the effect of a large interval on the error of the Euler method, or in general any ODE method, because all of them, as you get farther and farther away from the initial point, the error should get larger and larger. Now in the test Euler class, we looked at the example number 1, which was looking at the Euler sequence for y prime equals minus y differential equation, and looking it at a point 0.5, which is very close to the initial point, which was x equals 0, right? So our initial condition is y of x equals 0 is 1. So if we calculate at 0.5, and let me just run it again, we see that we eventually converge to the value, and I'm applying the fourth order Richardson, so the convergence is fast, right? Now in the example 2 that I have here, again the same equation, y prime equals minus y, the same initial conditions, y of 0 is basically 1. But now I'm trying to find y of 5, x equals 5. Instead of, in the example 1, I calculated y 0.5, which was very close to the initial point. Let me run it one more time. Okay. And now let's look at example 2. So we are getting farther away from the initial point, which was 0. Now we're calculating at 5, okay? And then as you can see here, so the Euler sequence creates the Euler sequence, and then I manually do a fourth order Richardson, right? So the difference from the example 1 here is that I'm applying a fourth order Richardson on the original Euler sequence. And then I plot it. So let's run example 2. So here I'm plotting the error. And as you can see, the error is not that good at the beginning, like compared to the previous case. This is not the error, this is the exact value. After like 5 to 10 terms, we had a very good convergence, but here it's not like that. We have to go farther away, like 60 or 50 terms to get a good error. And the reason is that now in example 2, we are calculating at a point x equals 5, which is much farther away from 0 than 0.5, right? So as we get away and the interval gets larger and larger from the initial point, the error grows and we need more and more iterations, right? But then in example 3, again the same thing, y prime equals minus y, and the initial condition y of 0 is 1. Here I'm going to use the method that we just wrote, including the trick that we're using for changing the initial condition when we are passing an array of x values. So here I'm creating an array from 0 to 50. I want to find the value of the solution y at 1000 points from 0 to 50. So I have a y exact array and y Euler array. Exact solution is e to the minus x. So I write a for loop and calculate them. And the Euler is OD Euler, right? So here what I'm doing, I'm using this, so I'm not using this trick. I'm using Euler method with Richardson at 100 point, okay? So what this does is that it always calculates the solution based on the original initial condition. And that's exactly the plot that I have here, okay? So this is the, let me just see, example 3. So in example 3, what we're doing is that we're calculating the, here, so I'm going to write, calculate y of x always based on y of 0 equals 1. So we always use the original initial condition to find the value of the solution at some later point x, all right? So this is example 3. And if I run it, you see what happens. As we get farther and farther away, the error gets bigger and bigger. So the blue one is the exact solution, the red one is the Euler solution, which is good for like up to 25. But as we get farther away from the initial point, we see that we get this error, which is not good at all, all right? Now obviously if I put, instead of 50, I put 100, we should see that the error even grows more and more. Yes, and it's actually very bad. It's like incredibly bad, okay? It suddenly diverges. So what we need to do, we need to basically, instead of using the original initial condition that causes this problem, because the error is proportional to the length of the interval, we look at example 4. Oh, one other thing is that here the Euler method actually does the fourth order Richardson. So if I don't do that, the error even gets worse and worse. So let's run example 3 one more time. So in the example 3, this red one is the Euler sequence, which has a fourth order Richardson acceleration. So if I go back here and remove that Richardson acceleration, we expect to get even bigger errors at the points that are even closer to the yes. So this is the original Euler solution without any acceleration, calculated at 100th term of the sequence. As you can see, it's just good for small values of x, like 1, 2. At 50, the error is very large. If we do a fourth order Richardson and evaluate that sequence at 100th term, we see that the error is actually pretty good up to 25, x25, but then we still get this error, okay? So what I'm going to do is, let's return back the Richardson acceleration. I'm going to look at example 4. So in example 4, again, y prime is minus y. The initial condition, y of 0 equals 1. I'm setting up a timer here, and now I'm trying to find the solution from x equals 0 to x equals 50 at 1000 points. The exact solution is e to the minus t, okay? And now I'm passing in the array, right? So I'm calling this Euler method instead of this one. So if I pass one double value, it calls this method. If I pass an array, it calls this method. And this method, because we're passing an array, it applies the trick that we use to change the initial conditions at each step to make sure that the length of the interval remains small for all the calculations, for all the x values in this interval, okay? So this is our final case, and we hope that this solution should give us a better solution than the previous solutions, right? And okay, so let's run example 4. Maybe let me just run example 3 first. So this is Euler with fourth order Richardson without the trick, and now example 4. This is Euler with fourth order Richardson with the trick, and the trick is that when I'm trying to calculate the y at some point, I use the previously calculated point as the initial condition. That way, the length of the interval that I'm solving over that interval is very small, so the error is guaranteed to be small. And as you can see, it actually removes all the errors. Now let's see what happens with this trick when we go even further. Let's say 80. Yeah, there is no error. So this method seems to be very effective. And you should always try to use this adaptive method or this clever trick, because for solving differential equation, we can always start from some initial condition, initial point, find the value at a very close point with good accuracy, and then use that new point as the initial point to finding the later values again and again. And as you can see, it's a very effective way of removing the error, okay? So this was the final trick that we can do with Euler. So Euler was not good because it had a very slow convergence, because the error was the behavior of the error was 1 over n. So we accelerated with the Richardson. Let's say if I apply fourth order Richardson, the error should be 1 over n to the fourth power, okay? And then the other problem was that, but the error also is proportional to b minus a, right? Because error proportional to h, so b minus a over n. And now we're saying that, okay, if I want to find the value of the solution at an array, we can use this trick to, after finding the solution at some point, x1, we use that point as the initial condition to find the later point, okay? This guarantees that the length of the interval always remains small. Now let's look at another example. Here I have y prime equals y over x, and y of 1 is 2. Alright, let's go here. Let's call this, for example, example 5. I can just copy and paste this one. So in the example 5, y prime is y over x. So x and y goes to y over x. All right, y prime is y over x, and then this is my derivative function, and then I create the ODE solver, pass in the function and the initial condition. What was the initial condition? Y of 1 is 2. Y of 1 is 2. And then I should calculate the value at y of x for x greater than 1. Just note that this function y prime has a singularity at x equals 0. So we cannot solve for values basically less than 0 or between 0 and 1, right? We should always solve for values that do not, for intervals that do not include this singularity. So we are going to go from 1 to, let's say, 10 with 100 points. So the exact solution is 1 over, the exact solution is 2x. Y is 2x because at 1 is 2, and y prime is 2, which is y over x. So the exact solution is just a linear solution, 2x. So 2 times t, and we apply to the x array, and then the Euler solves for the Euler, and we plot the exact and the Euler. It doesn't take much time. It's like I think we're still running example 4, so let's run example 5 here. 12 milliseconds is very fast, and we shouldn't plot it on a log scale. Okay, so we just plot it on a linear scale, and yes, it's exact. So the blue curve here, so I'm going to turn the marker on the figure number 1, which is the Euler solution, the numerical solution. Line width of the Euler solution to 0. So the Euler solution only has markers, and the exact solution only has, so let me also reduce the number of points to 20, for example. Okay, so this is the solution as a function of x values. Okay, let's go and put this here, and at 1.5, for example, we have 3, which is exactly the exact solution. Okay, but let's also look at the error. So in order to look at the error, so let me just create a new example. Let's call this example 6. In the example 6, what I'm going to do, I'm going to basically do the double error, new double x dot length, and then for int I equals 0 and len equals x dot length, I less than len, I plus plus. Error I is basically math.abs of y exact at I minus y Euler at I. Okay, and now I'm going to just plot the error, and so let's turn the marker off, and let's run example 6. Let's see what happens. So the error remains very small, 5 to the e negative 6, right? And let me just increase the number of points, let's say 200 points. 7 negative 5. Let's say 2000 points. 2e4. So in our method, as we see that as we increase the number of points, the error gets larger eventually, because that's just the computation error, the accumulation of the error. But now let's say we take to 20 points, and instead of doing calculating the solution based on the adaptation of the initial condition, we try to use it, calculate the solution at each point using the original initial condition, x dot length, and then here basically let's see, y Euler at I is Euler ODE solver dot Euler at xi. So as you can see, there's not much difference in terms of the error. We get relatively same error for both different approaches, directly using the initial condition or using the array iteration by changing the initial condition at each step. But if we get farther away, let's say 100, let's increase the number of points. So with the Euler method, this is the error. So if I don't do this and use the array solution, this is the error. So again, as we can see in this case, we see that the error is comparable. There's not much difference, right? But we have to always keep this in mind, that changing the getting farther and farther away from the initial point basically increases the error eventually, even if we do Richardson acceleration. And that's just because the error is eventually proportional to the length of the interval. So let me just plot this. So x values, let's call this error. And it's always pretty fast. It doesn't take much time, like 10 to 14 milliseconds. And let's copy this, put this in the PowerPoint. So this is our error. And this is the evaluation of the function from 1 to 10. And we see always that there is a good match between the exact solution and the accelerated Euler method. So there are more examples, and please stay tuned. In the next lectures, I will explain those examples and also go back and move forward with the other methods, such as Midpoint Method and the Runge-Kutta. And the final word here is that RK4 is eventually what we're going to use most of the time. Even though we're looking at the Euler as a very simple method, it's most of the time, or almost all of the time, we use RK4. And we will see that RK4 doesn't even, it generates a sequence that doesn't even need acceleration, because it's already, the error is already very good. Like, it's the original error for RK4 is already 1 over n to the 4th power, for example. So we don't even need to do any acceleration. And it makes the RK4 more efficient in terms of numerical computation. I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. And so far, we have looked at the Euler method. And we said that the basic idea is that we create a sequence that converges to the value of the function at each point. For example, if I want to solve this differential equation, y prime equals negative 1, and then the initial condition y of 0 is 1. If I want to solve this and find the value of function at 0.5, I create a sequence that converges to the value of the function at 0.5, and then I accelerate it using, so I can easily just try to find the value using the Euler method, and gives me a sequence of values that converges, and then I can accelerate the convergence using a Richardson acceleration. This was the whole idea. And not only we can apply it to Euler method, but as we will see later on in these lectures, we can apply this simple idea to any type of method for solving ordinary differential equations. So we always create a sequence that converges to the value of the function, and based on the method, the sequence could converge fast or slow, and whatever sequence we get, we can always do a Richardson acceleration to increase the speed of convergence and reduce the order of magnitude for the error. All right. And then we said that the problem with such solutions such as exponential function e to the negative x, the solutions that have a very rapid increase or decay, is that as we increase the interval for x, as we try to find the value of the function at points farther away from the initial point, which in this case is 0, the error is also proportional to the length of the interval. And in order to avoid the error getting larger by getting farther away from the initial point, what we can do is that as we progress and solve the value of the function at later points than the initial point, I can take for solving the function at some later point, I can take the previous point that has already been solved as the initial point, and then the interval between them always stays small. So that's a benefit, because then I can get away with this increase in the error. And that's always a good idea. Not only this, but it also helps with the stability of the solution. Again, stability here means that as the interval gets larger and larger, the error doesn't get larger and larger. We kind of control the error in a global sense. All right. So here's another example. Example 2 in this, okay, this should be example 2. In this example, y prime is y over x, and y of 1 is 2. So the initial point is x equals 1, and the value of the function, the initial value is 2, okay? But note that here y prime equals y over x. So this function f of x and y has a singularity as at x equals 0, right? So if we want to solve the initial value problem, we should look at the interval that doesn't have this singularity. So it's the interval that we're going to solve for is from 1 and later points. So it doesn't include 0. So we are safe. We know that our numerical method is not going to have any problems. If we want to solve for intervals that do include x equals 0, then we have to work a little bit harder to look at the behavior of the function, the solution at x equals 0, around x equals 0. Whether it's continuous, does it have limit or derivative or whatever. So singularities are always important when we're solving differential equations. But here in this example, I'm just considering that the interval that I'm solving for does not include x equals 0, which is my singularity. Now this differential equation has a very simple solution, y equals 2x, and if you're wondering how I solve this, I use the method of separation. So y prime is dy over dx, and then because f of x and y can be written as the multiplication of a function, just of a function of x times the function of y, I can do method of separations. I integrate over y separately, integrate over x separately, and we end up with this. Y of x equals 2x. It satisfies the differential equation, it satisfies the initial value, and therefore it's the unique solution of the equation. And now I'm trying to find the value of y at 1.5. And it should be equal to 3. But let's look at the code. And again, all the codes that you're going to see in this lecture and in the next few lectures, the structure is exactly similar. So we start with our derivative function, which defines the y prime as a function of x and y. Okay. So it's a functional interface. If you recall, x and y goes to y over x. X is a double number, y is a double number. And after defining the interface for f of x and y, we create an ODE solver object. ODE solver, new ODE solver. And in the ODE solver's constructor, we pass the function, the initial point, which is x equals 1, and initial value y of x equals 1, which is 2. Okay, now I'm setting up a timer just to see how long it takes to solve. But what I'm interested in solving from 1 to 10 interval. And let's say I want to solve for 20 points, all these red dots. Okay, so what I do, I create an array. X equals linear space of from 1 to 10, 20 points, and I create calculate the exact value because I already know the exact solution. Array func apply t goes to 2t and apply to the array x. Okay, so I'm calculating 2 of x for all the values of this x array, and then the y Euler is simply calling getting the ODE solver object and calling the Euler method. And if you recall, this Euler method takes in an array of values and find the solutions at all the points of this array. Okay, and then returns an array of solutions, this Euler method. And we also implemented the trick that we discussed. So now we just create a plot. The blue color is the exact, y exact, the red color is Euler. I render the plot, x label, y label. I turn the markers on the red plot, and then set the line width on the red plot to 0. So I just want to see the dots, the markers, the points, not the lines that are connecting them. And set the font to 17, for example, and show it in a separate window. And we get this. So the blue is exact, the red is Euler plus Richardson acceleration, fourth order, and we see that we get almost a perfect result. Okay? Now the next example is very interesting because so far all the differential equations that we have looked at, y prime equals negative y or y prime equals y over x, these were kind of linear in y. So we actually had a linear ordinary differential equation. But in this example, I have a nonlinear differential equation, y prime equals minus y squared. And it's an initial value problem. Okay, so this is example 3, and so if it's nonlinear in x, for example, if it was y prime equals minus x squared, we do not call it a nonlinear equation because nonlinearity defined based on y, the function that we're looking for. Okay, but as long as we can write it in the general form of y prime equals f of x and y, we really don't care about the format of the f of x and y. It could be linear in x, linear in y, nonlinear in x, nonlinear in y. We don't really care because we can always use any of the numerical method and exactly solve it. Okay, of course, as long as we don't encounter any singularity. So minus y squared doesn't have any singularity in x and y, so we're good. Y of 0 is 1, so the exact solution, and again we can use method of separations to exactly solve it, is 1 over x plus 1. So there is a singularity at x equals negative 1, but we don't care about that because we're solving from 0 to infinity plus infinity. And for example, y of 1.5 is 0.4. Okay, and as I mentioned, Euler method does not care about linear or nonlinear expression for f of x and y. As long as we can write it as y prime equals f of x and y, we are always able to solve it. And here's the code, and again the structure is exactly similar to the previous ones. Actually, we just changed one line of code, which is the definition of f of x and y, the derivative function. Everything else is exactly the same. So I hope you appreciate how nice this is, because jumping from one problem to another problem, we only need to change one line of code in principle. So we define our f of x and y, which defines the derivative function, or y prime. X and y goes to minus y squared, and then we create our ODE solver, passing the function, the initial point x equals 0, initial condition y equals 1, basically y of 0 is 1, and then set up timer, and then create an array of values from 0 to 50, 2000 points. And for this x array, I calculate the exact function. So t goes to 1 over 1 plus t for x, okay, for this array, 2000 points. And then I create a coarse array that has only 50 points, from 0 to 50 points. So I don't want to solve the ODE for 2000 points, because I just want to be able to differentiate these markers that I put. So I solve the ODE for only 50 points over the same interval, 0 to 50, okay? And the solution of the ODE is just taking the ODE solver object and calling the Euler method on the points, x Euler, which is 50 points, and then creating the figure, plotting it, setting the line width to 0 for the red one, setting the markers on, and then showing. And as you can see, we see the exact result. So the point here was that we don't care about the nonlinearity of the f of x and y. As long as the left hand side is just y prime itself, then we should always be able to solve this differential equation numerically, okay? There might not be an analytic solution, but we don't really care, all right? Now, we started with the Euler method, and we said that it's the simplest solution. Nobody uses it because the error behavior is 1 over n, which is very bad. But the trick that we had up our sleeves was that we said we don't care about the behavior of error, which is 1 over n. I create my Euler sequence, and I then accelerate it using a fourth order Richardson. Suddenly the error becomes 1 over n to the 4 or n to the 5. And I know that my Euler plus Richardson converges pretty fast. So that was the trick. But then there is always a trade-off between evaluating the function, how much computational cost there is for evaluating the function, and how much it is for applying the acceleration methods, like Richardson, fourth order, etc. Okay? And if the computation of the function doesn't have much cost, it's pretty fast, then it's better to, instead of starting with Euler, we start with a method that already gives us a better error estimation, right? Instead of having 1 over n, we have 1 over n squared, 1 over n cubed, etc. And as you probably can guess, it always involves more evaluations of the function. So Euler was simplest because we only had one evaluation of f of x and y. But in a higher order method, or methods that have basically they start with a better error, we always get more and more evaluations of the function. Okay, so there's always a trade-off which method to choose and which acceleration to go for. So the next method is the midpoint method. And okay, so maybe before starting the midpoint method, I want to point out one also important point here. That in the Euler method, we saw that, okay, we say f y prime is y of x plus h minus y of x over h, right? And then we can find the value of y at some later point. And now what happens if f of x and y does not depend on y? Then the problem is y prime equals f of x. And the solution is just an integral, right? From the initial point, which is a, to some point x. And if you apply the Euler method, instead of calculating the integral directly, you solve it as a differential equation. What happens is that the Euler method in this case becomes exactly equivalent to the integration based on the forward rectangle approximation, because we are doing the forward approximation for a derivative. Okay, so basically the area of each subinterval becomes h, the length of subinterval, times f of x. There is no y here, right? The value of the function at the start point of the subinterval. And this is exactly the definition of the forward rectangle. If I go back to the numerical integration case, in the forward rectangle, the area of each subinterval is the length of the subinterval h or delta x times the value of the function f of x at the start point. And if the f of x and y in the Euler approach doesn't depend on y, we end up exactly with this solution. And we in the numerical integration, we also said that this has a very poor convergence. The error is very bad. But the other case is backward integration, which in the ODE language, it has a method called backward Euler method, which I'm not going to discuss because it's very similar to the forward method. But then we said that there is another way, and that's the center method or the midpoint method. Here we approximate the area by taking the value of the function at the midpoint of the interval. So if the interval is xi plus 1, we calculate the value at xi plus 1 over 2 times h or delta x. And we said that this center approximation has a better error than the forward or backward. So here, for forward or backward, if the error is 1 over n, and n is the number of subintervals, the center is 1 over n squared, all right? Now back to the ODE case, this center approximation has an equivalent ODE solution or ODE method called the midpoint method. So in the midpoint method, we do exactly this. So we are giving this differential equation, y prime equals f of x and y, and we are trying to solve the initial value problem, y of a equals y0. And again, you already know the routine. We divide if I want to find the function, the solution at some point b, I divide the interval between a and b to n subintervals. And in each subinterval, I try to find the y of x plus h, for example, the next point, and then I progress until I get to y of b, which is y of xn. So now I have a sequence that converges to y of b. Now for the midpoint method, what we say here is that we approximate y prime with the secant line. In each subinterval, we approximate y prime with the secant line that connects xn to xn plus 1, right? And then we have yn plus 1, and and then we say that, okay, we don't know yn plus 1, okay? And we also don't know yn, but when I start from x equals a, we know y0, okay? But we don't know yn plus 1, and that's what we're looking for. If I have the exact slope for this secant line, then I can solve this. Yn plus 1 minus yn over xn plus 1 minus xn equals the slope of the secant line. So I already know yn, xn plus 1, so I can exactly solve for yn plus 1. But the problem is that we do not know the slope of the secant line. So what we do, we use one of the theorems in calculus, in differential calculus, that says that for any continuous and smooth function, let's say this blue curve is a continuous function and it's a smooth function, so the derivative exists everywhere in this subinterval, the slope of the secant line must be equal to at least the slope of the tangent line in one of the points inside this interval. Let's call it Cn, right? We don't know where Cn is exactly, but we don't know that this Cn exists such that the slope of the tangent line is exactly equal to the slope of the secant line, all right? So we know that this Cn must be in the interval. It's most likely, in almost all cases, it's never the exactly xn or xn plus 1, unless the solution is a constant solution. It's constant, so yn plus 1 is in fact equals to yn in that case. Otherwise, the Cn is never exactly xn or xn plus 1, all right? And again, to refresh your memory, we're considering always a uniform partitioning when solving ODE, because non-uniform partitioning or quadrature approaches just get very complicated and they're not worth the effort. And even with uniform partitioning, we can always get very good error rate or error we always end up with a very reliable error or very small error. So uniform partitioning is what we use for ODEs. And h is the length of each subinterval, b minus a over n, and we're looking for the value of the solution y at point b, given the initial point a, okay? So we don't know where Cn is, but we can use the midpoint, exactly the midpoint of the interval, as an approximation for Cn. So Cn is approximately 0.5 xn plus 1, all right? But then the other thing is that now we need to be able to calculate y prime at Cn at the midpoint. So y prime is f of x and y. So f of x is given, or know the x at the midpoint, which is Cn, this is the prime. But I do not know the value of the function at the midpoint, right? I don't know what y of n plus 1/2 is. So for midpoints, we always use the index n plus 1/2. It doesn't really mean anything. It just indicates that we're at the midpoint of the nth interval. All right, from xn to xn plus 1, we typically use the notation xn plus 1/2 to denote the midpoint of the xn and xn plus 1. Similarly, from yn to yn plus 1, the midpoint we denote it by 1n plus half. All right. So I know xn plus half, but I do not know yn plus half. But what I can do when I put it here, I can approximate yn plus half using the simple Euler method. So yn plus half is yn plus the length of the subinterval. Now it is h over 2 times the slope of the tangent line at xn, which is f of xn and yn, which I already know, right? So this is how we do the midpoint method. So yn plus 1 is yn. So if we rearrange this, yn plus 1 is yn plus times plus y prime of Cn times h, right? Xn plus 1 minus xn is h. But I do not know y prime of Cn because I don't know Cn. So we approximate Cn by the midpoint. We say that, okay, it's probably close to the midpoint. And then the y prime becomes f of midpoint, x Cn, and y at Cn. So we approximate Cn, but even if we know Cn, we don't know the value of the function y at Cn, at the midpoint. So we approximate that also using the forward Euler method. Very simple Euler method, right? It's yn plus h over 2 f of xn and yn. So we approximate yn plus 1/2 using Euler, and we approximate the Cn by the midpoint of the interval. Now if you work out the math and look at the error, this midpoint ends up having an error of 1 over n squared instead of 1 over n. So this involves 2 evaluations of the f function instead of Euler method that had 1 evaluation per subinterval. We get 2, so a factor of 2. But then the error already starts from 1 over n squared instead of 1 over n. So that's an advantage. So the advantage is that the error has a better order. The disadvantage is that we need to have more function calculations per step or per subinterval. All right. Now one thing here is that if y prime is large, which means the function has a large concavity or it's a convex, all right, then this Cn is definitely gets farther and farther away from the endpoints. So our approximation gets better because if we are getting farther and farther away from the endpoints, then there is a higher and higher chance that this tangent line, which has a slope similar to the secant line, becomes closer and closer to the midpoint. Now the question here is, what happens if f of x and y does not depend on y? Then the solution should be an integration of the f of x from a to b, right? But what happens in this case? What do we get actually? So if the function doesn't depend on y, we remove this part. Yn plus 1 is yn plus h times f of xn plus h over 2. So it's the value of the function at midpoint, and the area underneath is being approximated by a rectangle, right? The value of the function at the midpoint times the length of the interval h. And that's exactly the midpoint approximation for the numerical integration. That's why that method is called midpoint method, because when the function doesn't depend on y, we end up exactly with this numerical integration for the midpoint. And we mentioned that the midpoint or center approximation of the integral does in fact have a error which is h squared or 1 over n squared. Alright, so this is the midpoint method. The code is exactly similar to the Euler method. So what we did for the Euler method, here, instead of having instead of having Euler sequence, we create the midpoint sequence, and everything the same. We start from x0, y0. We define the h, which is x1 minus x0 over n, and here x1 means the b, the point that we're trying to find the value of the solution. And then instead of having y equals y plus h times the value of the function at x and y, remember x and y here in each loop of the for iteration are holding the values of xn and yn, and at the next iteration they become xn plus 1 and yn plus 1. So instead of having this, we use the midpoint equation. Basically y equals y plus h times the value of the function at x plus h over 2, y plus h over 2 the value of the function at x and y. Alright, we just update this one line, and everything else is exactly the same to the Euler method. And it's actually a general case here, because even if we move forward to the other methods, we only need to update this one line to implement that particular method, because this one line defines the iterations, how we generate this sequence that converges to the solution. And that's the beauty of how we implemented this way of solving ordinary differential equations in Java. So we create a sequence that converges to the value of the function at a given point, and that enables us to update the method just by updating this one line. All right. So this was the midpoint method. Almost nobody uses midpoint method because we have in fact better methods to use. So in the next lecture I'm going to talk about Runge-Kutta, fourth order Runge-Kutta, and two things we're going to see. One is Runge-Kutta, the fourth order, has a very good error which is 1 over n to the fourth. Okay. And then what we're going to see also is that the Euler method, midpoint method, they are all special cases of the general Runge-Kutta method. That's why basically everyone just uses Runge-Kutta, and nobody cares about Euler or midpoint, because midpoint and Euler are special cases of the Runge-Kutta method. All right. So thank you for watching. Please stay tuned. I have many more lectures to come, and I hope you enjoyed this lecture. I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. And in the last lecture, we looked at the midpoint method, and we said that the midpoint method gives us a better error compared to the Euler. So Euler's error was 1 over n. Midpoint gives us 1 over n squared, but the price that we are paying is calculating the function f of x and y twice. Instead of Euler method, that was just 1. All right. So we're trading off the cost of computation of f of x and y with the better accuracy. And this trade-off always exists in solving differential equations. Okay. So what I'm going to do, I'm going to implement this midpoint method in our ODE solver class, and then compare the result with the Euler method, see how fast the convergence is compared to the convergence of the Euler method. So let's head to our Eclipse. In the ODE project, we have this ODE package, and we have the ODE solver. To refresh your memory, the ODE solver takes an initial condition, x0, y0, and a derivative function that defines f of x and y, and the derivative function just returns a double value. It only has one public abstract method value, which takes the value of x and the y, and it defines y prime as f of x and y. All right, and we always use it as lambda expression for easy use. So we created this Euler sequence, and we said that if we want to find the solution at any x1 point, we just do this iteration in the for loop n times, and in x and y are start with x0 and y0, and after each loop they become xn and yn, all right, at the end of the for loop. And then we said that we can return the Euler by doing a fourth order Richardson to accelerate the convergence, okay? And if we pass in an array to the Euler solution and use Euler solution, we can use each evaluated point as the initial condition for the next point. And this helps a lot with the convergence of the stability of the solution as we get farther and farther away from the initial point, all right? So what I'm going to do, so I'm going to do exactly this, but for the midpoint sequence. So midpoint sequence. So for the midpoint method. So if n equals 0, obviously we're just at the beginning, we return y0, and then we define x, y, and h. And here we're defining our sequence. So the midpoint sequence is y plus h times f at x plus h over 2. So we have this midpoint, 0.5 times h. And we said that we don't know the exact value of y at basically at the midpoint, so we simply use an Euler method to approximate it. So y plus 0.5 h times func.value at x and y, all right? xn and yn times half of h plus yn gives me yn plus half, the midpoint of y, and then x plus half, all right? So basically we are evaluating, we're saying that yn is yn plus h times f of x, basically x with the index of n plus half, and y with the index of n plus half, something like this, all right? So we're calculating the f at the midpoint. And again, yn plus half is approximated using an Euler method, all right? So I'm going to delete this. So this is our midpoint sequence, and the rest are exactly the same. So we can have a method called midpoint, and we just take the midpoint sequence and evaluate at the point x1 that we're trying to find the solution. It gives us a sequence that converges to the exact solution at x1. We Richardson it, and then we evaluate it, let's say at 100 point, all right? Well, what I'm going to do, I'm going to create a test class. So test midpoint. Let's have a main method here. And in the main method, I'm going to invoke, let's say, test1. And in the test1, so test1 is going to be public static void test1, all right? And in the test1, I'm going to look at one of the previous solutions that we did for Euler. So this is just y prime equals minus y, and we're creating a sequence, and we look at the convergence of that sequence. So here, let's remove this timer, okay? So y prime equals negative y, ODE solver, and then yn, let's say Euler. We don't want to Richardson it, so I'm looking at the Euler sequence, and then another sequence yn midpoint, ODE solver dot midpoint sequence at 0.5, all right? So again, looking for y 0.5. Let's add the semicolon here. So we have two methods, two sequences with different method Euler. So here the error is obviously 1 over n, for the midpoint 1 over n squared. So we expect to see a better convergence or faster convergence for yn in terms of the error, right? How fast the error goes down. So I'm going to change this name to, let's say, yn Euler vals, okay? And then we're going to copy paste this yn midpoint vals. So we have this yn Euler, and copy and paste this yn midpoint values, and it's yn midpoint. Okay, so yn Euler, let's plot it with blue color, and then fig.plot x indices and yn midpoint values, let's plot it with R, and we render it. Let's turn the markers on and number of partitions. Alright, so everything is set. We're just going to run it, and it doesn't show the window, the plot, because I'm running it on a Mac, so I have to go to the VM argument and remove this check mark. Alright, now we see that, and let's look at the convergence. I'm going to do a fast configure here, and then let's go full screen. So the red one is the midpoint method, and the blue one is the Euler method. And as you can see, we definitely have a much faster convergence for the midpoint method, right? Because it's not a much faster, but it's definitely faster than the Euler method, at least by 1 order of magnitude in terms of error, because the error is proportional to 1 over n squared. So as you can see, it's faster, and we can actually look at that by, let's create another test and calculate the error, the absolute error. Public static void test2. So we're going to invoke test2, and in test2 we are going to, let me also remove the unused imports, Command Shift O for organizing the imports. In the test2 I'm going to basically copy and paste the same thing, but here I'm going to create a double value, double exact, and we know that the solution here was e to the minus x, right, minus 0.5. And now we're going to basically, in the Euler values, I'm going to calculate math.abs, evaluate at I, minus exact, and then the same thing here, math.abs, yn midpoint, minus the exact. Alright, so we are calculating the absolute error. And then again, we're plotting this, and here is just the error, or absolute error. And most likely we're going to plot it on a log scale, but just like, let's add the linear scale. And as you can see, the midpoint method has a much faster drop in the error. So the midpoint method by itself is much better. It looks much better because the error has 1 order of magnitude better performance than the Euler, right? And the price that we are paying is that we are evaluating our f of x and y twice, right? One for estimating yn plus half, the midpoint using the Euler approximation, and then one for evaluating the y at n plus 1, which is this evaluation. We're evaluating twice, but we get a much better error. So if the calculation of the function doesn't have computation cost that much, it's not a complicated function, so it's better to go with methods that have more evaluations of the functions but give us much better error rate, right? So I'm going to also plot this error on the set y-axis to log, just to see the log here. Okay, so you can clearly, so let me also increase the font size, fig.font, let's say 17. All right, now you can clearly see that how fast it is for the midpoint to drop, right? And it's kind of like a 1 order of magnitude. So we know that error is 1 over n for Euler and 1 over n squared. So if the Euler method is 10 to the negative 3, the error for midpoint should be around 10 to the negative 6, something like that. I mean, here we see that as we get here, error better than 10 to the negative 3. For midpoint, it's about 10 to the negative 5, 6. So that's more or less in the same ballpark as we expect it to be, all right? So it's not one order of magnitude better in terms of the absolute error. It's whatever we had for the Euler, you square it. So if the absolute error was 10 to the negative 2, for midpoint we get 10 to the negative 4, right? So it's like 2 orders of magnitude improvement instead of 1 order. That's why the midpoint has much better convergence, okay? And yeah, so, and again, the beauty of the way that we implemented these methods in Java using the concept of sequence is that no matter what method we use, the approach is almost exactly similar. So we always start with a sequence for that method, and we update only this one line, the way it iterates and calculates yn plus 1 from yn. That's the only thing that we update as we go to other methods. And the rest is exactly the same. So midpoint, so I can also have it's a method, midpoint method, that finds the solution at a given array of x values, and here instead of Euler are called midpoint. Everything else is exactly the same, and we are updating the initial condition as we progress in the evaluation of this array, the solution, okay? Okay, so back to our slides, but again, nobody uses midpoint because midpoint and Euler are both special cases of a general approach called Runge-Kutta, and the most commonly used Runge-Kutta is Runge-Kutta of order 4, so 4th order Runge-Kutta. And again, the problem is that we are giving a one-dimensional function, y prime f of x and y, and we want to solve the initial value problem. If ya is given, y of a, then what is y of b at some later point? And again, from a to b, we discretize the interval into n sub-intervals. We stick with uniform partitioning because of avoiding a lot of complexities to deal with the quadrature method or whatever. So xn plus 1 for each sub-interval is xn plus h, and h is the same for all the subintervals, b minus a over n. So the length of the subinterval is inversely proportional to the number of subintervals. So we can express the error either in terms of the orders of h or orders of 1 over n. And then Runge-Kutta says that in order to go from yn to yn plus 1, use this expression, yn plus 1 over 6 times k1 plus 2k2 plus 2k3 plus k4. And k1 is h times f of xn and yn. And x and yn are the beginning, starting point of the nth subinterval. All right? k2 is h times f of xn plus h over 2, which is the midpoint, and yn plus k1 over 2. k3 is h times the f of xn plus h over 2, yn plus k2 over 2. So we calculate k1, put it here, calculate k2, put it here, calculate k3. And finally k4 is h times f of xn plus h, which is the endpoint of the subinterval, times and yn plus k3. So it's more like, in order to get k4, we need to calculate k3. In order to calculate k3, we need to calculate k2. And in order to calculate k2, we need to calculate k1. All right? And this is a 4th order approach. And the error has been hugely improved compared to the Euler or midpoint. So Euler was order of h, midpoint was order of h squared. For RK4, Runge-Kutta 4, the local error or the truncation error in each subinterval is order of h to the 5th. And then when you add them up, all the n subintervals, you multiply by n, or you divide by h, right? So order of h to the 5 divided by h becomes order of h to the 4. So this is the global error, which means when we go from a to b using this sequence of iterations, or we basically move forward or progress in this sequence, we end up eventually the order of error for evaluating y of b is order of h to the 4. All right, so 1 over n to the 4. And as we increase n, the error goes down extremely fast. Okay, that's very important. Now, there are two things here that you can immediately see. Runge-Kutta first order is just using k1. So yn plus 1 is yn plus k1. All right? Or basically you substitute k2, k3, and k4 with k1. And you end up with yn plus k1. And that's exactly the Euler method. Runge-Kutta second order is basically k2. Yn plus 1 is yn plus k2. And that's exactly the midpoint method. Okay? So if we look at the midpoint method, it's exactly equal to the k2 because we calculated the y at the midpoint, yn plus half, using the Euler method. And that's exactly what happens here. We calculate the k1, which is the Euler approximation for delta y, and then we calculate k2, which is the midpoint approximation, h times f of xn plus h over 2 yn plus k1 over 2. All right. Now, what the important thing here is that we said that there is a close relation between these methods and the methods for numerical integration. And methods of numerical integration are special cases of these methods for solving ODEs, because if f of x and y doesn't depend on y, the solution is equivalent to integrating the function f of x. And we said that the Euler method is equivalent to the forward rectangle integration. The midpoint method is equivalent to the midpoint or center rectangular approximation. And you can immediately see here, especially with this 1 over 6 factor, that the RK4, the Runge-Kutta fourth order, is equivalent to the Simpson's method of numerical integration. So if f of x and y is independent of y, Runge-Kutta 4 is exactly the Simpson's method. And to refresh your memory, first of all, let's see what happens if f does not depend on y. So k1 is h times f of xn. k2 is h f of xn plus h over 2, which is the midpoint of the interval. k3 is h of f xn plus h over 2. So k2 and k3 are equal. And k4 is h times f of xn plus h, yn plus k3. And f doesn't depend on y, so k4 is h times f of xn plus h, which is the value of the function at the end point. So k1 is the value of the function at the start point of the subinterval, k4 is the end point, and k2 and k3 are in the midpoint. So we end up with h over 6, f of xn, 4 times f of xn plus h over 2, and f of xn plus h. And this is exactly the Simpson method for integration. If I go back to the integration, here's the Simpson method. And we said that if I have a small subinterval, I can estimate the integral in a very small subinterval a to b by b minus a over 6. b minus a is basically h, the length of subinterval, times f in the beginning, f at the end, and 4 times f at the midpoint. And we said that the error was h to the 4th power, which is exactly the error for the numerical for Runge-Kutta as well. And we said that this Simpson's method comes from the condition that the integral should be exact for a quadratic polynomial, for a quadratic function, which means it's exact for constant functions, linear functions, and also quadratic functions. And that gives us a very good, very nice error. The error goes down very rapidly. So back to the Runge-Kutta. This is exactly what happens here. If f of x and y is independent of y, we end up with the Simpson's method. And we said that out of, so before going to the quadrature methods for numerical integration, rectangle approximation, trapezoid approximation, and Simpson approximation, they all end up with a sequence that converges to the exact value. but the convergence always has a linear or sublinear convergence, right? It never has a quadratic convergence, which is the case for basically quadrature methods or non-uniform partitioning. And out of all these uniform partitioning cases, Simpson was the best one that gives us the most accurate. The price that we were paying was evaluation of the function at 3 points. Midpoint requires one evaluation for numerical integration. Forward rectangle requires one approximation or calculation of the function. Simpson requires 2, and Runge-Kutta requires 3, because we have f of x and yn, f of xn plus h over 2 and yn plus k1 over 2. K3 is yn plus k2 over 2, and k4 is yn plus k3. So we end up with 4 evaluations of the function. And again, if evaluation of the function is costly, it takes a lot of computation effort to evaluate the function, it's better to stay with Euler or midpoint and then do a Richardson acceleration on the sequence that we get. Okay? Because we can calculate the value of the function, calculate the Euler sequence, and once we have it, we just do a Richardson approximation on the values that we have already calculated. All right? But again, typically in the physics or engineering problems, the ODEs, the function evaluation doesn't have much cost of evaluation. So we go with Runge-Kutta 4, the error goes down very rapidly, and we don't even need to do any acceleration on the generated sequence. We are not going to do any acceleration. And again, the implementation is Java is like this. It's exactly like the Euler or the midpoint method. Again, that's because of the way we implemented this ODE solver in Java, which is a very beautiful way of looking at it. We generate a sequence that converges to y of b, starting with y of a. And then because the order of error is already so good, we don't even need to do any Richardson acceleration on the sequence. So here's the code. Sequence, Runge-Kutta sequence. I'm trying to find the solution at b or x1 here. If n is 0, we're already at x0, which is a, and we already know the value, which is y0. Otherwise, we start with x, we create this sequence of xi and yi. So originally x and y are x0 and y0. H is the length of each subinterval, uniform partitioning. And originally let's initialize k1, k2, k3, and k4 to 0, okay? And in each iteration of the for loop, we calculate the k1, k2, k3, and k4. So this is for evaluation of the function. So k1 is h times the function at x and y. K2 is function at the midpoint, x plus half h, y plus half k1. K3 is x plus half h, y plus half k2. And k4 is h times function at x plus h, y plus k3. And once we calculate that, we put it in this calculation. Yn plus 1 is yn plus k1, 2k2, 2k3, k4 over 6. And then we also update x. So in this term, this line updates the y from y0 to y1, and x goes from x0 to x1. And then we go into the next iteration of the loop. Y becomes y2, x becomes x2. And after n iterations, y becomes yn, which is the one that is we're looking for, and x becomes xn, which is b, because we're doing a uniform partitioning. All right? And again, the error is already 1 over n squared. So if we evaluate at n equals 5 or n equals 10, we should be very good in terms of getting a extremely small error. So here's one example. Y prime is minus y, and this is what we looked at here by comparing to the to midpoint with the Euler. Okay. And here's the code. Again, the style of the code is exactly the same. I'm not doing anything. Again, deriv function, we define with the deriv function, which is y prime defines the y prime minus y. Create the ODE solver class, passing the function the initial point, which is 0, and the initial value y of 0, which is 1, and then create the sequence now called the Runge-Kutta sequence method and calculate it at 0.5. And then indices, we are going to progress 100 terms in this sequence to look at the convergence, and yn values, we evaluate the sequence and then plot it. And you see at n equals 5, at the 5th term, we already get almost perfect convergence. And here I wrote that in a general case, let's just take n equals 20 as the good approximation, or the best, as the point that the convergence has been absolutely reached. Okay? And let's try to also in our test 1 and test 2, let's also include the Runge-Kutta. So here yn midpoint, and I'm going to create a new sequence, yn Runge-Kutta, and instead of the midpoint sequence, I'm going to call the Runge-Kutta sequence, and it's going to be 1 over n4. And then we have the exact yn midpoint. Let's also calculate the yn rk, or Runge-Kutta values, and let's copy and paste this yn Runge-Kutta values, yn Runge-Kutta sequence. We're evaluating at I minus exact, and let's also plot it yn Runge-Kutta values with, let's say, magenta color. Alright, so let's run it. Wow, look at this beautiful convergence. It's so good that like it completely obliterates the Euler and the midpoint method, and that's what we expect. So at 100 terms, we get more than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more than 10 decimal places of accuracy for the absolute error when we are evaluating the solution at 0.5, right? So Euler after 100 terms gives us about 2 decimal places of accuracy, and the midpoint method gives us about 5 decimal places of accuracy, and the Runge-Kutta 4th order gives us about more than 10 decimal places of accuracy. That's incredible. And generally RK4 or Runge-Kutta 4 is considered the best trade-off between function evaluations, the cost of function evaluation, and basically the cost of error, the truncation error. So we end up with 4 evaluation of the function, and we end up with very good error. So mostly it's considered a golden trade-off between the number of evaluations of the function and the error that we get for the solution. Okay? And again, we don't even need to do any Richardson acceleration of the sequence. It's already so good that we don't even need to improve the error rate. So here's another thing that we discussed for the Euler and midpoint, is that we can use the trick of when we are evaluating the solution over an array of points, let's say x0, x5, 10, 50. We can use the previously calculated points as the initial condition to calculate the next point, and that avoids the case when the interval becomes large, because the error also depends on the total interval. So if we are starting with the initial point of 0 and we want to find the solution at 50, the error is could in theory be much larger than when we're trying to evaluate the function at x equals 5, right? There's a factor of 10 here. But then if we progress in the solutions in the x values and use the previous solution as the initial point for the new one, it also helps with the stability. All right, so this is a trick that you should always keep in mind. Once we're trying to solve the ODE for multiple values of x, we can start from the initial point, calculate the next one, and use the next one as the initial condition for the next one. All right, so So this is the one way that we can stabilize the numerical integration. And I hope you enjoyed this lecture. So we have finished our study of all the methods, or the most commonly used methods for solving ordinary differential equations. The next thing is to look at how we can solve a system of ordinary differential equations. So basically what happens if I have y1 prime, if I have two functions, let's say y1 and y2, or y and z, and y prime is a function of x, y and z, and z prime is also another function of x, y and z. So I have two differential equations, first order ODEs, that are coupled to each other. And we will look at how to solve them exactly using the concepts and the sequences that we have looked here, exactly using the same methods, but now we have to extend to an array or a system of differential equations. So please stay tuned. I hope you enjoyed this lecture, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. In the previous lectures, we looked at the general approach that we used to implement solving ODEs in Java. And the idea was to create a sequence that converges to the value of the function at each point. And then if the error of the method that we were using was not good enough, we used Richardson acceleration. And eventually we looked at the most commonly used method, which was the Runge-Kutta first order. We said that if f of x and y does not depend on y, the fourth order Runge-Kutta becomes Simpson's method. And we always use uniform partitioning to partition from A to B, and A is the initial point, B is the point that we're trying to solve for. Find the value of the function y of b at this point. And then we said that the first order Runge-Kutta is basically the Euler method, the second order Runge-Kutta is the Midpoint Method, and eventually the fourth order Runge-Kutta is the most commonly used, because it has a good trade-off between the number of function calculations, how many times we need to calculate f of x and y, and the accuracy of the error, or the order of the error. All right, so we try to stick with Runge-Kutta 4 from now on when we talked about solving ordinary differential equations. But then the next thing in terms of solving ordinary differential equations is that so far we only have looked at one differential equation, y prime equals f of x and y. All right, now the question is, what happens if we have multiple differential equations, like y prime equals f of x, y, z, and z prime equals g of x, y, z? This is called a system of ordinary differential equation. All right, so system of ODEs. Most of the time, especially in physics, we have several functions coupled to each other via differential equations, right? This forms a system of first order ODEs. Let's say we have m functions, so we end up with m equations, y1, y2, and ym. Okay, and then we are looking for the values of these m functions, and we are given m equations, f1 of x, y1, y2, ym, f2 of x, y1, y2, ym, all the way to fm. Note that if we have m functions, we should have m equations. If we have less than that, then there is no unique solution. If we have more than that, then there could be no solution, because the equations may not end up being consistent, right? If we take only m of those equations and solve it, and then put it to the m plus 1 equation, the solution may not be consistent. All right, so the goal is to find the solution of these functions y1, y2, ym using all these m equations, and the number of equations must be m, equal to the number of functions, and we need m initial conditions. So before we only had one equation, so we only needed one initial condition. Here we need m initial conditions, one initial condition for each function. So y1 of x0 is y1 with the annotation 0, y2 x0 is y2 with the annotation 0, all the, okay? Now again, we can implement a general method and then basically a general procedure, and we can use any of the previous method that we looked at, like Euler, midpoint, Runge-Kutta, let's say RK4. So we're going to define all of these FK equations as functional interface, okay? So the functional interface takes x and an array of m variables and returns an array of m values, right? And then we can apply Euler method. Instead of Euler, let's say okay, we can apply Euler or let's say particular method to all functions in each step. All right, so we basically generate the equation. For example, okay, let's keep this as Euler because this equation here is for Euler. So, but the same exact procedure can be done for the midpoint method or Runge-Kutta method. So here I'm just writing the procedure for the Euler method. So we define the functional interface that represents or returns the value m values or an array of m values for all these m equations, and then we use the Euler method, apply the Euler method to all functions in each step, and then we create the Euler sequence, the Euler iteration. Yk at x plus h is yk at x plus h times fk at x, y1, y2, yn, all right? And then we create the Euler sequence for each function, and then we can apply fourth order Richardson acceleration. If you use Runge-Kutta fourth order, we don't need to use the Richardson acceleration, all right? So that's the idea. However, it's much easier to write it in a vector form. So we have a vector of m functions, y1, y2, ym. So the left hand side becomes the derivative of a vector. And then for Euler, the right hand side becomes a vector at each step plus h times f. F is a vector. That is, the components are f1, f2 to all the way to fm. So in a vector way, in a vector form, and here again the f vector is calculated at x and vector y at step k, all right? So now instead of having a double function, a function which is a number, now we have vectors. But the structure of the code, the way we create the Euler sequence or Runge-Kutta sequence is exactly the same as before. Whenever we have y, we have to replace it with a vector. And the way I suggest to do it is like this in Java. When we want to do implementation, I start with creating an object called nd array. This array is an object, all right? And what it does, it represents an array of m, basically a double array. But then the reason that we're implementing the array as an object, because we then overload the operators plus, minus, times, division for the array, okay? Because by default Java, just a double array in Java doesn't allow you to do plus or minus between them. You cannot overload the operator. So I create this nd array that holds an array of double values, but then I also implement the operator overloading, right? Nd array is just an array with some number of components, which also supports the operator overloading. Because here, if I'm representing the vectors with an array, nd array. If I want to multiply h or this vector f by h and then add it to another vector, I cannot simply do it for n double arrays. So I use an object and overload the operators. And then another thing that we need to note, that we are generating a sequence for all the m simultaneously. We are generating a sequence for the vector that has m components, right? So our sequence is basically always an array, and each component is a sequence that is representing each of these functions. So I define also an array sequence, and it has one public abstract method which returns nd array and basically evaluates the array sequence at a given index, all right? So this array sequence is representing a vector. Each component of that vector is a sequence. And then if I want to get the sequence that represents the particular component of this array, I define a method, a default method called @index. So, and then use a lambda expression. N goes to evaluate at n, returns an nd array, and then I just look at the index component, the component which is defined by this index number for this nd array. Okay, so let's head to Eclipse, and I'm going to show you first the nd array. So I have added the nd array to the sequence package, the project that we had before, nd array. And this nd array is just a wrapper for a wrapper class for double array with support for operator overloading. That's the only reason we're doing this wrapper, because we want to be able to do operator overloading and directly add the nd array objects together. So this nd array has a dimension and just holds the internally manages or holds the double array x. All right, and then the constructor takes a var argument of a double array and then assigns assigns it to the internal x array, and then the dimension is just the length of the array. And then the method add returns the value of the double array at the index I. All right, we have a two-string method, and then there is a method called array that actually returns the double array representation of the nd array. Just returns x, right, which is double array. And the dim is just returns the dimension. And these are all the operator overloading methods. So addition, subtraction, multiplication, and division. And also a static assignment, the value of method. So the value of method, basically this is the equality overloading or the assignment operator. So basically if I say nd array like d equals a new double, for example 1 2, it creates an nd array by calling the value of method on this double array, something like that. And then we have add. We can add a double value to nd array, which adds the double value to all the component of the nd array. We can add it to add another double array to the nd array, so it adds component by component. And we actually need to care about, we probably need to have an exception here to check make sure that the length of the two arrays are equal, but for simplicity I'm ignoring that at the moment. Add reverse, basically this is basically v plus the nd array, and again it's a double array, it's just v plus this component by component. Add to nd array to an nd array, add reverse nd array to nd array, subtract from a double, subtract from a double array, subtract reverse, subtract from an nd array, subtract reverse, multiply by a number, multiply reverse. And note that multiply to an nd array doesn't make sense, but we're defining it as a component wise, basically component wise multiplication. So this is how we're defining that. Multiply reverse, again component wise. Divide by a number, divide by an nd array, again it's component wise division. And then reverse division, and then negation, minus d. So we take the array, negate each component, and return a new nd array. All right, so this is just because we want to be able to easily adapt the previous method that we had in the ODE solver. So this was for solving a scalar equation. Now we want to do exactly the same sequence, but here instead of having double values, we want to have an nd array, so that and the nd array supports our operator overloading, so the equation doesn't really change. And in each iteration it gives us an array sequence, a sequence that is basically a vector of n sequences. So in order to do that, I have also implemented the array sequence, and it returns an ND object. So basically when we say evaluate at some index, it returns a vector that has m components, right? And if I want to get a sequence which is representing the some component, I just evaluate, I use a lambda expression, and then n goes to, this lambda expression is from the sequence interface, so n goes to evaluate n. So this is a n-dimensional array, and then use at method in the ND array represents returns a number, a double. All right, so this is how we're doing using lambda expression and a default method to also get a sequence representation of each component. And then we have all the previously methods that we developed for the sequence interface. They already are, we don't need to change any code because operator overloading is supported by the ND array. And all these transformations, Aitken-Shanks, all of them are linear things. So they just involve multiplication and division and other stuff. Richardson, everything. So it's already applicable to the array sequence interface as well. And the trick was to, instead of having a double array here, we're returning an ND array object, and the ND array supports operator overloading, so it makes the code much cleaner. All right, now that I have this ND array, I create an object called ODE system solver. And in order to do that, I just like the deriv function that represents the double value, a single scalar f of x and y, I define a deriv n function. So it represents an ND array. So basically represents an n-dimensional array. This is basically f1 of x, y1, y2, etc., f2, etc., all the way to fn, if we have n equations. And the method here is values. It has a plural s here. So in the ODEs system solver, we have the deriv n function x0. So the initial point is still a scalar because this is an ordinary differential equation. And by definition, ordinary differential equation has only one variable, x, or in physics or engineering is mostly time, t. So y1, y2, ym, all of these are functions of x, okay? That's why x0 is still a double. But the initial condition now, it's an array of double values. So y0 is array. And then we also have this extra parameter num equations. And in the constructor for the ODE system solver, we pass in our n equations as the function. This is an array function. This is the deriv n function. And then the initial point and the initial condition as a vararg parameter. It's always better to use vararg and instead of an array of double. But the caveat is that the vararg argument must always comes at the end of the list. So if we cannot put it before double x0, it should always be the end, which is the case here. So I'm just defining the array of the initial condition as a vararg. And the number of equations is just the length of how many equation functions we have in the initial conditions. Now we see the dimension of the function and the y0 should agree, but I'm not checking for that for simplicity. And then let's say we want to create a Euler sequence. So this Euler sequence should give me an array sequence, basically a vector that has each component of that vector or array is a sequence by itself. So again, if n is equal 0, we return an ND array. Okay, note that I'm using a multi-line lambda expression. So when I do n goes to ND array y0, it automatically gives me an array sequence object. And if n is greater than 0, what we do is the code is very similar to the scalar case. So y, instead of being a double, is now an ND array from y0. And x is still the scalar, and then we have ND array func vals, because now the func vals or evaluation of the function gives me a double array, which I need to convert it to an ND array. Actually, I do not need to convert it to ND array because I believe because we have the value of method. So if I say that, okay, this ND array func_vals is equal to the array, it should be able to call the value of method. But to make sure that it doesn't fail at some point, or maybe the compiler messes up something, so we are creating a new ND array anyways. So func values, it returns a double array, and we're converting to ND array. And then now the multiplication and summation are overloaded for the ND arrays. So y is ND array, which starts from y0, and then h times func_vals assigns it back to y. So in each loop of the for iteration, in each iteration, y becomes y1, x1, y2, x2, etc. And y remains a vector, or remains a vector ND array. And because I'm using the lambda expression, when I return y, it automatically converts it to the array sequence. Okay? That's the beauty of using a lambda expression. So for the Euler, we calculate with the equation is y equals y plus h times func_vals. We evaluating the vector, and the vector is func.values at x and y.array. The reason that I'm converting the y ND array to a double, because just the way I define the derivative function using a vararg, and this is a double array, not an ND array. So I call the array method on the ND array to get an array representation of the ND array. Okay? And then we have the Euler, which takes the Euler sequence at point x1. So the Euler sequence is an array sequence. So it's a vector of n component. And then does a Richardson, fourth order Richardson, and then evaluates it at 10 or some number of points, maybe 10, 20. I believe for the scalar one, we evaluate that, yeah, we evaluate at 100. But here, for simplicity, I'm evaluating at 10, let's say 15. And this basically becomes an ND array, okay? Because the evaluate method in the array sequence returns an ND array. And then I call the array method in the ND array to convert the ND array object into a double array. Because for users, for someone who's using this API, it's easier to deal with arrays instead of ND arrays. And then we have the Euler that evaluates at an array at x1. One thing that I like to emphasize here is that we are returning a vector, right? So if I'm calculating at, if I'm trying to calculate for an array of x values, then each row of basically each function must return an array, a double array. So now I have n functions, so it becomes a two-dimensional function, a two-dimensional array. That's why I'm returning a two-dimensional double array. And each row is representing the values of one of the functions. So the first row is the values of the first function y1 evaluated at all these x points. The second row is the values of the second function evaluated at all these points. And just like before, I'm using the trick that we used for the fact that we calculate at some point and then use that value as the initial condition for the next point. This helps with the stability of the ordinary differential equation. All right. So I call the Euler method, returns an array of double values, and then assign the kth row, basically, and this is the values of all the functions at a particular point. So that's why it's assigned to the one column of the double array. And then I update the initial conditions and then make sure that I put them back. All right. So let's head back to our slides. So this is the general idea, using array sequence, ND arrays, objects, so that the operator overloading is supported and the implementation becomes extremely simple. And here's example 1. So in the example 1, I looked at the decoupled equations. In the decoupled, I have two equations, y1 prime equals x, y2 prime equals 1. So y1 prime doesn't depend on y2, and y2 prime doesn't depend on y1. So instead of solving these together as a system of two equations, I can solve them separately using the method that we had before. But here I'll solve the two equations simultaneously. So I have the initial conditions for the two, and each of them has a closed form solution. The first one is 0.5 x squared plus 1, and the second one is just x. It's linear, the first one is quadratic. And I'm going to use a fourth order Runge-Kutta, and again, if we go back to the code for the ODE system solver, the Euler, the Runge-Kutta implementation is exactly the same as before. We have k1, k2, k3, k4 defined as ND arrays, and then yn plus 1 is yn plus k1 plus 2k2 plus 2k3 plus k4 over 6. And then xn plus 1 is xn plus h. And because this is a lambda expression, when I return y, it automatically returns an array sequence. And again, the same thing for calculating at an array of x values and returning a two-dimensional array. Each row represents the values of one function. All right? Okay, so let's call this again example 1. And again, the style of the code is exactly the same as before that we had for scalar equations or one equation. Here, instead of deriv function, we have deriv n function, which takes x and y, but y here is an array, y0, y1, y2, okay? And the return type is an array. So basically the return type, the first component represents the y0 prime. So y0 prime is basically the first function, which should be x. The second component represents y1 prime, which is the second equation, and it should be 1. All right? So that's how we're defining the vector of the f functions, f of x and all the y. And x0 is 0. That's the initial condition. Note that all the functions must have the same initial point, initial condition. And here they all are defined at 0. And then I have an array of two components, and I'm immediately initializing it with 1, 1. So y0 is now a vector or an array with two components, 1 and 1. And then I define my ODE system solver, passing the n-dimensional function and x0 and the n-dimensional y0, n-dimensional initial conditions. And then you know the routine. So we create an array of x values from 0 to 15, 1000 points. And I calculate the exact solutions using this dense number of x points. All right. And then I define a coarse array XODE, which only has 20 points because I just want to discretely see these markers. And then call the Runge-Kutta method on this array XODE, and it returns a two-dimensional double array. I create my figure. So each row of the values of each row represents the values of one of the functions. So if I want to plot the second y2, I say plot x and y2 exact with color B, and then XODE y values, the first, basically the second row. So y values at index 0 is the first row, y values at index 1 is the second row. And that returns the values of the second function, which is y2 here, all right? And as you can see, there's a perfect match. And yes, this should be y2. And then similarly, I can plot y1, so x and y1 exact, XODE y values at index 0. And it gives me the exact solution. Okay, now there is another example here, and this example on the other hand is a coupled equation, because most of the time in physics and engineering problems we have coupled system of equations. So y prime equals y2, y2 prime equals minus y1, and this minus 1 has a important physical meaning or interpretation. But we don't care about that at the moment, we just care about the math. So y1 prime is y2, y2 prime is minus y1, and this is a system of coupled equations. So we cannot use previous methods for scalar equations to solve these. So we have to solve these two equations simultaneously together. And again, we have the initial conditions. Both of them are defined at the same x point, which is 0. One of the function is 0, one of the functions is 1. And it turns out this system of equations has closed form solution. y1 is sine of x and y2 is cosine of x. And we can confirm that they satisfy these differential equations, and they also satisfy the initial conditions. So these are the unique solutions. I'm going to use exactly the same code that we had before, but update the deriv n function, update the initial conditions, and use Euler plus fourth order Richardson to get the solution. I mean, it's always recommended to use fourth order Runge-Kutta, but here I'm just showing you that Euler plus fourth order Richardson also gives us a very accurate result anyways. So deriv function x and y is a vector, an array, and it must return a 2D array. The first component represents y0 prime, or the first y prime, which is y2, and y2 is the second component of the y vector at index 1. And then the second component here is y1 prime, which is minus y0. That's why we're returning minus y0. x0 is 0, and y0, the initial conditions, the first function is 0, the second function is 1. And the rest is very similar to before. We create our ODE system solver, passing the n-dimensional function, x0, the initial point and initial condition, which is n-dimensional. Create our dense array from 0 to 20 that has 1000 values, and calculate the y1, y2 exact. y1 exact is sine, y2 exact is cosine. And then create a coarse version of the X array, which has only 100 points, so 0 to 20, 100 points. And then use the ODE solver object and call the Euler method that takes an array of X values and returns a two-dimensional array. Each row represents the solution for one of the functions. And let's say I'm plotting y1 exact, so x and y1 exact. This is the blue curve with color B, and then I want to plot the ODE solver solution. So x Euler and y Euler at row 0. So the 0th row, or the first row of this double array, represents y0, the 0th component of this vector, which is our first function here, y1. And then we plot them, y solution, and as you can see, we get the perfect match. And then if I want to plot the second function, here I call y Euler at index 1, which is the solution for the second function, and it gives me the cosine. So we see that we actually can solve a system of ordinary differential equations together, and it gives us all the functions simultaneously, which is very good. It's really good that we can do that. And the only requirement is that we, on the left hand side, we should have y1 prime, y2 prime, y3 prime, etc. On the right hand side, we can have any function of x, y1, y2, etc. It could be a nonlinear function, linear function, but we should not have any singularities over the interval that we are trying to solve the functions. Okay? So I hope you enjoyed this lecture, and I will have more lectures in the future, so please stay tuned, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving systems of first order ordinary differential equations, and we said that the general format should be a vector that contains all the function, the ddx of a vector, y1, y2, ym, equals m equations, all right, in x, y1, y2, and ym. And these equations, we don't have any condition on the equations. They could be linear, nonlinear in x, y1, y2, ym. These equations could be in general coupled to each other, which means y1 prime could depend on y2, y3, etc. Or they could be decoupled from each other, which means y1 prime doesn't depend on y2, y3, etc. Okay, but in general we can simultaneously solve for all the functions, all the m functions, and in order to do that we need m initial conditions. And then we said that the idea is to do exactly what we did for scalar functions, a scalar problem which only had one equation, and extend it to vectors. Okay, so because when we implemented Euler, Runge-Kutta or midpoint method, we just had this iteration to generate a sequence that converges to the value of the function. And now we are extending this into a vector sequence, right, or array sequence, such that the vector sequence or array sequence converges to a vector, that is this vector of all the solutions, all the values of the functions at the particular point b, or x1 here in this code. All right, and the beauty was that then we didn't really need to change that much into our code. We just replaced y with arrays or nd array vector. And the reason we used nd array was because this nd array is simply a wrapper for an array, but it also supports operator overloading. And using operator overloading allows us to write the equations in a very simple way. We don't need to write many for loops to just iterate over all the elements in the loop, okay, in the arrays. So it's just an elegant way of removing all the unnecessary for loops that we have to deal with, and they are all encapsulated in the nd array. Okay, and we looked at some examples, and the first example was two equations that were actually decoupled from each other. And we said that because the equations are decoupled, we can solve them separately as like simple ODEs, or we can solve them together using a system of ODEs. And then we looked at a more general case when we have coupled equations, and we said that in physics and engineering typically we have this type of problems. And as I mentioned, all the right hand side of these derivatives can in fact be nonlinear functions. We don't care, we can still solve it, but we shouldn't have any singularities on x or y here, right? And now the very interesting consequence of being able to solve systems of ODEs is being able to solve higher order linear ordinary differential equations. So far we have only looked at the first order ODEs. Y prime was a function of x and y. But now we're going to look at, for example, second degree or second order or higher order ODEs. And we can use a very simple trick to solve these higher order ODEs using the approach that we have for solving systems of ODE. And the trick is very interesting. So here is just an example, and it's very easy to generalize it. So let's say we want to solve a higher order linear ordinary differential equation using a system of ODEs. And again, when we say linear, it just applies to the highest derivative that appears. So basically, if I have an equation that y is raised to some power, y prime is raised to some power, but y double prime has a power of 1, I still consider it a linear, and I still can solve it, okay, with the methods that I have seen so far. All right. So when I say linear here, I mean in general a linear ODE means y double prime, y prime, y, they all have a power of 1, okay? But in general here I mean just y double prime has a power of 1. So it could be in fact nonlinear in y and y prime, and I can still solve it, all right? So by linear here I mean the highest order derivative should be linear. The other derivatives and other terms that include y can in fact be nonlinear functions. It doesn't matter that much. Now obviously the condition here is that a2, a1 and a0, these coefficients which can be dependent on x, they should not have any singularities in the region, in the interval that we are solving for the function y, all right? But let's say everything is fine and there is no singularity, the differential equation is linear. Let's see how we can solve this. And the way we're going to solve this is we're going to convert this second degree equation, for example, or second order equation into a system of a first order equations. And in order to do that, we introduce a change of variable, or we introduce a new variable, or if we have like y, if we have more than second derivative of the function, we introduce more than one variable. We introduce in general a couple of new variables equal to the lower order derivatives. So this is the key word here. For example, in this equation y double prime y, we define a function z that is equal to y prime. All right, and then this equation becomes a2z prime plus a1z plus a0y equals f of x. Now this is first order ODE in terms of the z function, right? Because z prime and z appear. But then the equation coupled to the y. So one equation is just y prime equals z. That's just a change of variable. Another equation is a2z prime equals f of x minus a0y minus a1z. And now we have a system of two first order ordinary differential equations, all right? Y prime z prime equals f of x y z and another function of x y z, all right? Now we can solve this. So now we have the standard form. Y prime equals f1 of x y z, and the 1 is always just z because that's just the definition, the change of variable. And then z prime is f2 of x y z, which is this right hand side here. And now we can just easily solve it. And we already know that in order to solve a second order differential equation, we need to have two initial conditions, one on y and one on y prime, which translates into having initial conditions for y and z here, because z is y prime. So we can uniquely solve this second order differential equation by transforming it into a system of first order differential equations. Now if there was a y triple primes or the third derivative of y, then we get three equations. So z is y, we define z as y prime, we define another function, let's say w as y double prime, and then we get three equations. All right, so what's the benefits? The benefit here is that we are simultaneously solving for y and y prime, because we are solving for y and z is y prime. So it simultaneously gives us y and y prime. We don't need to calculate y first and somehow try to calculate y prime from y. The information is already in the equation, in this equation. And when we solve it, we extract that information, not only the function, but also the derivative y prime. And once we have y and y prime, calculating the y double prime is just an algebraic equation, right? Because if I know y and y prime, I put them in the equation and I calculate y double prime or z prime. There is nothing to solve. It's already solved, right? When I have y and z or y and y prime, I can find y double prime, all right? So the way we solve this, transform this differential equation into a system of first order ODEs allows us to extract all the information of the solution, not only the values of the solution, but also the values of the first derivative, second derivative, etc. And that's very powerful technique, okay? Because in most cases, not only we want to solve the differential equation and find y, but we want to also find the first derivative and second derivative. Now, obviously, transforming into a system and using vectors and arrays adds more computation, right? So it's a little bit costly if we do this approach. But it's a very straightforward and nice way of solving differential equation. And at the end, we have y prime, and then when we solve for y and y prime, finding y double prime is just an algebraic equation. So we can also have y double prime, all right? So again, the equation only needs to be linear for the highest order derivative, i.e. y double prime. Because if y double prime here was to some power, for example 2, and then we end up with z prime squared, which we cannot solve using the previous techniques, okay? Now let's see the power of this approach. And the first one, I'm just going to present some examples from physics and engineering, which I think it's very interesting to look at them. Example 1, is the free falling ball. So I have a ball, I hold it at some position above the ground, okay, let's say at 200 meters above the ground at time t equals 0. T is the variable of time. And then because I'm holding that, it doesn't have an initial velocity, right? Because I'm grabbing it, I'm holding it above the ground. So the initial velocity, or y prime, is 0. And then I let it go and I release the ball. So it starts to move towards the earth, ground, because of the gravitational force. So I know in general in Newtonian mechanics, the force is equal to mass times acceleration. The gravitational force is minus mg because the force is downward, and I'm assuming the positive direction for y-axis is upward. So then m cancels out, a is y double prime, acceleration. Therefore the equation that I should solve is y double prime equals minus g, or minus 10 meters per second squared. All right, I mean, we already know that this differential equation has a very simple closed form solution, but I'm going to use the method of systems of ODEs, because not only I get the position, I also get the velocity, or the first derivative of position as well. So z, I define a vector z, or array z, which contains y of t and v of t. V is just y prime, right? And if you're familiar with the Newtonian mechanics, typically the vector that contains the position and velocity is called phase space vector. And this is just a terminology, and it's good for you to know that. And let's look at the code. And again, the structure of the code very similar to what we had so far for solving systems of ODE. So nothing is changed. I'm using Euler plus Richardson fourth order. Alternatively, I can use Runge-Kutta, which is recommended. But here I'm just using Euler plus Richardson fourth order. So we have the vector z that contains y and y prime. So z0 is y and z1 is y prime, okay? So we have to define the deriv n function, or z prime vector. T and z, my independent variable is t time, and z is an array or vector, goes to an array of two components, right? The first one is z0 prime. z0 prime is y prime, which is z1, okay? The second component is z1 prime, which is y prime prime, y double prime, which is minus 10 meters per second square, right? What is t0? The initial time is 0. What is the y0? The initial position is 200. And what is the initial velocity? v0 or y0 prime is 0. All right, I have this, I have my equation, so I just create an ODE system solver, new ODE system solver, pass in the function, all the equations, the time 0, and all the initial conditions for z0 and z1. So y0, v0, because z0 is position and z1 is velocity. And then I create the timestamps that I want to find a solution at them. So from 0 to 6 seconds, 500 points. And then basically I find the solution. So z ODE dot Euler, I call the Euler method, pass the array of timestamps, and then the ODE dot Euler from the ODE system solver returns a two-dimensional array, and each row, so I'm calling it z here, right? It's a two-dimensional array. Each row gives me the solution of the function and all the t values for each component of the z vector. So the z0 is basically the values of all the values of the function z0. All right? So the values of the solution y are the first row, z0. For example, velocity is the z1, the second row of the z array. And then I want to also compare it with the exact result. So I use the function interface, function double, func exact, t goes to minus 0.5 times g, which is 10 times t squared plus y0. And then I find the exact solution on all the t values. I call the array func class and use the apply method, use the lambda expression, func exact apply, and apply it to the t-vals array. And I create the figure. I plot the ODE solution with blue, and I plot the exact with red. Okay, and then I just turn the markers on the solution. So this is how, and you see that we not only I can get the position, but also can get the derivative of the y, which is the velocity. And obviously velocity is a linear function, so its derivative, which is the acceleration, must be constant. That's what we started with. Okay, so this is one example of the solving physics problem, which physics problem and engineering problems are typically, and we always almost always end up with a second degree, linear second degree or second order differential equation. So we can always use this method of systems of ODEs to solve it. And as you can see here, so the ball starts at y equals 200 meters, and after about 6 seconds it almost reaches the ground, right? The position becomes almost 0. All right, the other interesting example from physics is mass spring system. Now this is basically a drawing of how it looks like, the system. We have a string that are fixed at some point, and then it's connected to a mass or an object. All right, now the way the spring works, at least to the first order approximation, is that the spring has something called a restoring force. All right, and the definition of the force comes from Hooke's law, which is an experimental law. All right, so the way it works is that when we have a spring, it is at rest, right? So it has a length. So there is no compression or decompression on the string, right? So we call that initial length of the string, or if one end is fixed, the initial position of the other end as the rest position, or x rest here. Now if I compress or decompress the spring, then the length of the spring or the position of its endpoint changes, right? And the spring applies a restoring force on my hand because I'm compressing or decompressing it, and the direction of the force is always in the opposite direction of the direction that I compressed or decompressed, and it's linearly proportional to the change in the length of the string, and the proportionality constant is called K, or the spring constant. Sometimes it's also called the stiffness of the spring, because the higher K means it's harder to basically compress or decompress it. So if I change the length of the spring from its initial length or the rest position, then I get there is a restoring force on me. All right, and so let's now assume that we have an object connected to the spring and the system is at the rest position. So originally there is no compression or decompression on the spring. Okay, now I move the object this way in the positive direction of the x-axis by let's say 2 centimeters. All right, and let's assume that the rest position is 50 centimeters. So this was originally 50 centimeters, and now I decompress the spring by dragging the object 2 centimeters in this way, right, in the positive direction. Note that I'm still holding the object. Okay, so the initial position of the object is x rest plus 2 centimeters, which is 52 centimeters. All right, x rest is 50. I drag it this way by 2 centimeters. So initial position of the object is 52 centimeters. But because I'm not letting go, the initial velocity of the object is 0 because it's not moving. I'm holding on to it. All right, and then at this position, 2 centimeters away from the rest position, I let go of the object. All right, because at the initial position here, the the spring has been decompressed, so it applies a force in the negative direction, right? So it moves the object back, and at the when object reaches the rest position, it's still moving because it's still accelerating. So it goes back and compresses the spring. And as it compresses, the force in the opposite direction, the positive direction, starts to increase, and eventually it can completely cancel out the acceleration. So it stops the object and pushes it back. So we can see that if we ignore the friction, there is a damping effect. The object should oscillate indefinitely around about the rest position, and that's exactly what we see in the solution. So we already understand the force that is applied on the object, the initial conditions. So the initial position of the object is x rest plus 2, and the initial velocity is 0. Okay, and we want to find the position and velocity of the object as a function of time. So what is the differential equation that we need to solve? The differential equation is force equals mass times acceleration, and the force is minus k x, which is the position of the object at each point in time, minus x rest, which is the original length or original length of the spring. Note that what I want you to really understand is that the x rest or the rest position of the spring is not the initial position of the object. The initial position object is some distance away from the rest, because we need to initially compress or decompress the spring so that it can apply a force on the object and be able to move it around. Okay, if the initial position is x rest, the solution is that the object cannot move because initially there is no force on the object. So that's very important to understand. So the force is minus k times x minus x rest equals mass times acceleration, mass times x double prime. So x double prime plus k over m, x minus x rest equals 0. And again, x rest is not the initial position of the object. X rest is the initial length or the initial position of the other end of the spring that is not fixed. So the spring has one end that is fixed, and we call it x equals 0. And then the spring has another end which is not fixed and can move and compress and decompress the spring. Okay, so x minus x rest. So x0 or the initial position is x rest plus 2 centimeters, and the initial velocity is 0. And again, the Java code is exactly the same. We define a vector z that has two components, x and x prime. And typically this k over m, we already know that the object must start to oscillate. So k over m is the frequency of oscillation squared. That's usually in the physics textbook they define omega 0 squared. So here I'm defining omega 0 2 times pi. So the frequency of oscillation is omega 0 over 2 pi, which is 1 hertz. That means that the periods of oscillations should be 1 second. Every 1 second the object from here goes here and comes back. All right, and we will see that in the solution. So omega 0 is 2 pi, t0 is 0, x rest is 50 centimeter, x0 is x rest plus 2 centimeter. The initial velocity is 0. I define the derivative n function. T and z goes to a two component array. The first one is z0 prime, which is x prime, which is equal to z1. And the second one is z1 prime or x prime prime, x double prime, which is minus k over m minus omega 0 squared. The minus sign is here. Minus omega 0 squared times x, which is z0 minus x rest. Okay, remember we have to include x rest here, because the force for a spring, the force always defined as the compression and decompression from its rest position or its rest state. Now that we have the derivative function or all the two equations, we define our ODE system solver, passing the function, the initial time, the initial position, and initial velocity. These are the initial conditions. And then the t-vals, I want to solve from t0 to 10 seconds after that. T0 plus 10 seconds, 1000 points. And ODE solver, I'm solving using the Runge-Kutta method at 1000 points, returns a 2D array. The first row of this 2D array Z is all the values of X function at all the time steps. And the second row, Z1, here, is all the values of the velocity at all these time steps, all right? And then I plot the X. So T vals X with blue color, time and xt, and similarly I can plot vt. So I automatically solve for x and x prime, or x and v, and then obviously x double prime is just minus omega 0 squared x minus x rest. All right. Let's look at the solution. So we said that we expect, because of the restoring force and the fact that the force changes direction when the spring is compressed or decompressed, the object should start to oscillate about this rest position, and the amplitude of the oscillation should be 2 centimeters. And that's what we see. So 50 centimeters is the rest position, and we drag the object 2 centimeters away. So the x0 or initial position is plus 52 centimeters, and then the object starts to oscillate. So the solution is sinusoidal. It goes down to 48 centimeters. So it comes to 50 centimeters, but it doesn't stop. It goes to 48 centimeters, comes back up to 52, 48, 52, etc. And as we expect, the period of oscillation is 1 second. So the period is 1 second. As we expect, because I set omega 0 to 2 pi. So f0, or the frequency, is omega 0 over 2 pi, which is 1 hertz. That means the t0, or the natural oscillation period, is 1 over f0, which is 1 second. And if you look at the velocity, the sign of the velocity can actually tell us which direction the object is moving. So originally when the object is here and we let go, initially the speed is 0, but then it becomes negative. Negative means the object is moving in the negative x direction, so it's moving this way. And it comes to the rest position. Here the velocity is maximum when it comes back to its original rest position, but then the velocity, it's not 0, it's actually maximum. So the object has a lot of velocity when it reaches here, so it continues moving, and now it's compressing the spring. And then the force changes direction and it tries to stop the object. That's why the velocity is negative, so the object is still moving in this direction, but because it's compressing the spring, its velocity starts to go back to 0. And when it's to 0, the spring has been compressed a lot, and then it forces the object to move back. Now the velocity becomes positive. So the object reaches here and then it moves back. So again, a very classic physics problem, and you can make this more difficult by hooking up another spring and another mass to the original mass. So we have 2 springs and 2 masses. Maybe at some point in the future I'll look at this problem too. But again, as long as we can write down a differential equation, we should be able to easily solve, no matter how many objects we have, how many springs we have. Okay. Now the last example is from electrical engineering, and our LC circuits, resistors, a resistor, an inductor, and a capacitor. And again, this is also similar to mass spring, and this is more similar to the mass spring by including the friction. In other words, LC systems, inductor and capacitance, they always oscillate, but then if we have a resistor, it's a damped oscillation, so eventually the oscillation dies after a long time, and we will see that. Now let's say we want to find the solution for this system. So if I apply a force, if I know our LC values, if I apply a force, I want to know the current that is flowing in the circuit as a function of time. I can also find basically the current is shared between all these components because they are all in series. So the KCL rule tells me that the current that goes into the R also goes into the L and goes into the C. All right. So I'm going to define I as IL, the current of the inductor, as the current of the circuit, and there is another component which is the voltage across the capacitor. All right. So what is the solution? If I apply a voltage as the source here, V of t, it's equal. KVL rule of a circuit tells me that the total, the sum or algebraic sum of all the potentials across all components in a loop must be 0. In other words, the voltage that I drop here should be equal to the sum of the voltages across all these components. And the voltage of a resistor is R times the current, so R times IL. The voltage of an inductor is L times di dt, so the derivative of the current through an inductor gives me the voltage of the inductor. But then for the capacitor, it's the other way. The derivative of the voltage of the inductor of the capacitor, the derivative of the voltage dvc dt, gives me the current of the capacitor, which is equal to the current of the inductor or the current of the circuit. So if I want to write KVL or this equation purely in terms of the IL or the current of the circuit, I have to replace VC here with the integral of IL. Then I don't have a differential equation, I have a differential integral equation. And typically what we do is we take one derivative from the whole equation, then I have dv dt, r di dt, l d squared I dt squared plus basically here dvcd dvt dt, which gives me I. So I end up with a second order derivative, second order differential equation. But then the problem here is that we have Vt, basically dV dt, the derivative of the voltage. And in general, this voltage could be a discontinuous voltage, could be just a step. From 0, is suddenly we have a switch, for example, in the circuit, and then we close it. So it's a step, and its derivative becomes something undefined at exactly we close the switch, for example. So in order to avoid that, what I'm going to do, instead of turning this circuit into a second order differential equation in terms of the current, and with the dV dt, the derivative of the voltage source, I'm going to turn it into a system of two first order differential equations, basically a system of ODEs. And the state variables, in circuit terminology, we always talk about the state variables of the circuit. They're always the current of the inductors and the voltage of capacitors. That's because the voltage of the inductor is the derivative of the current, and the current, and basically the current of the capacitor is the derivative of its voltage. So voltage of the capacitor and the current of the inductor are always the state variables in a circuit. All right. So I'm going to convert this problem into a system of ODEs. I have two variables or two functions: the current of the inductor, which is also the current of the circuit, and the voltage of the capacitor. And I can find them simultaneously, which is very good. And when I find this, I can immediately find the di dt, because I know Vc, I know I, and I know V. And also when I find yes, I can also find this equation. I already know I and V, so the only thing I can find next is the voltage of the inductor and voltage of the resistor as well. So let's see how we can solve this circuit, and I'm going to look at two cases. The first one is undamped oscillation, which means the resistor is 0, there is no resistor here, L and C, and I just apply a voltage, turn it on, a step voltage. So the voltage is 0, and then I turn it on at t equals 1 second. Alright, let's see. So let's say the resistance is 0.2. Let's not worry about the units at the moment. The capacitance is 1 and the inductor is 1. So if you're familiar with the circuit theory, we know that omega 0, the natural frequency, is 1 over square root of LC, which is 1 over 1, which is 1 radians per second. So f0 is omega 0 or 2 over 2 pi, so f0 1 over 2 pi, and t0 or the period of oscillations for L and C is 2 pi or 6.3 seconds. So every 6.5 seconds roughly we should see an oscillation. And now I'm defining the source voltage, this Vt here, and the way I define it, I use the functional interface and use a ternary operator because I want to apply a step. So I said that if t is less than 1, my voltage is 0. This source function returns a 0 as a function of time. If t is greater than 1 or equal to 1, I return 1. So I'm applying a step voltage from 0 volts to 1 volts exactly at t equals 1. So obviously before t equals 1, before applying the voltage, the system or the circuit is at rest. And the way I enforce that by setting all the initial conditions for IL and VC to 0. Okay? So t0 is 0, that's initial time. IL 0, the initial current for the IL is 0. And the initial voltage of the capacitor is also 0. This means the circuit is initially at rest, and when I apply a voltage at 1 second, before that the I should be 0. There should be no current flowing in the circuit, and we will see that in the solution too. So initial conditions, the values of the parameters and the source function, and then we need to define our derivative n function, which is t and z. Z is a vector, our state vector, which is IL, the current of inductor, and the voltage of capacitor. And this must return an array of two components. I call them equation 1 and equation 2. Now equation 1 is this one, and I should write it in terms of the state variables. So equation 1 should be z0 prime equals equation 1, right? What is z0 prime? Z0 prime is dIL dt. So I have to reorganize this equation. So it's a source voltage minus, which I'm going to apply t because it's a function. I have calculated the value of the source voltage at time t, minus RIL, R times IL is the zeroth component of the z vector, minus VC. VC is the second state variable, so it's z1, divided by L, alright, inductance. So this is how I reorganize this equation. So the second equation should be z1 prime equals the function or the equation. z1 prime is vc prime or dvc dt. So I have to reorganize this by moving the c on the other side. So z1 prime equals equation 2, which is 1 over c times IL, and IL is z0, so z0 divided by capacitance. These are my two state equations, alright? And the rest is very simple. An array of two components that I call them initial conditions, IL0, which is 0, and VC0, which is 0, so the circuit is originally at rest. And then I create my ODE system solver, passing the function, passing the initial time, which is 0, and passing the array of initial conditions. And then t-vals, I'm going to calculate from t0 to t0 plus 50 seconds later, 1000 points. Obviously, I'm using Runge-Kutta, fourth order, and then it returns an array of a two-dimensional array of values. I call this z again. And then the first row of z vector of this two-dimensional vector is the values of the first state variable. So IL, the values of IL or the solutions are z0, the first row, and the second row is the values of the second state variable, which is VC. So I simultaneously calculate for ZL, IL, the current of the inductor, and the voltage of capacitor. And then I'm plotting t-vals and IL, the current of the inductor. As I mentioned, so this is let's look at the first case when we don't have any damping or resistance. In this case, we see that before applying the voltage at t equals 1 second, the current is 0. That's what we expect because there is no initial condition for current, it's 0. So the circuit is at rest and there is no current flowing. As soon as I apply a step function, so the voltage, the applied voltage goes to the 1 volts, okay? the current starts to oscillate with a period of 2 pi. That's because we don't have any resistance, so L and C, it's a perfectly periodic oscillation. Okay? Now if I change the resistance to 0.2, so we have some damping, so the resistor burns some of the current, and basically it doesn't allow the current to freely flow in one direction or the other, because the current is originally positive, which means it runs in this direction, and then it becomes negative, so it changes direction. And the reason is how the magnetic induction works in the inductor. You can look it up in the physics books. If I have resistance, we see that the current starts to go up to 1, but then as it comes back and it continues over time, we see that it dies away. The current dies off, and that's because of the fact that the resistor is basically killing the the current, the flow of current, right? And another way of looking at it is that when the current becomes 0, there is no voltage across the resistor, and then there is also no voltage across the inductor, right? Because dI/dL is also 0 after a long time. So all the source voltage must drop across the capacitor. So if I look at, in this case, if I actually look at the solution for VC, we see that it actually oscillates around 1 volt and eventually settles on the exact voltage of the source, 1 volt. And that's very interesting because in many physical cases, we always have an RLC and we try to look at the voltage of the capacitor, and it gives us an overshoot, which after a while it dies away and becomes the voltage of the source, and we call this the settling time. So I'm just going to show you that when this case happens and there is some resistance or damping, when the current goes to 0, the voltage of the capacitor eventually settles exactly at the voltage of the source, which here is 1 volt. So let's head to Eclipse and try to quickly look at this. So in my example packages, I have this RLC circuit, all right? And here I'm going to plot the VC as a function of time, and the resistance is 0.2, capacitance, and the voltage is 1 volt, right? So before t 1 second, the voltage is 0, the source voltage. After t equals 1 second, the voltage becomes 1. So let's look at the voltage of the capacitor now, here. So as you can see, it's 0 before 1 second, and then we know that. Let's also plot the source voltage. That would be very interesting. Fig.plot t-vals, and then I'm going to do the array func apply source voltage. T goes to basically source voltage. Source voltage. Yeah, my Eclipse is lagging a bit. Dot apply T, and then apply this to basically all the t-vals, and I'm going to plot this with color red. All right, so okay, why is this complaining? Okay, this should be t-val with a small v. Okay, so we're plotting the voltage of the capacitor, and what I mentioned is that if there is some damping, there is some resistance, and the current dies off after some time, then the voltage of the capacitor should eventually become the voltage of the source. So let's see. So the red curve here is the voltage of the source, and the blue curve is the voltage of the capacitor. And there are two things here. So one is this oscillation, and we call this settling point, or the settling voltage of the capacitor, It's the final voltage or the settling voltage, and the time that it takes for these oscillations to effectively die, it's called the settling time, which in this case is very long. You see, after 50 seconds there is still some oscillation. And the peak, the maximum peak that always happens in the beginning is called the overshoot. And overshoot is typically a problem when we are dealing with control circuits most of the times in the control theory we have, let's say, a sensor that controls the temperature of an object, and we want to lock the temperature at some value. And we always design a circuit that tries to do a feedback loop, and eventually it ends up being equivalent to an RLC circuit. And this overshoot problem and the settling time problem is always a problem. Now the response of the circuit is fast, so it can quickly rise up, but because of the fact that it's a second order equation, it oscillates. So a first order system, basically what happens, it doesn't do any overshoot, but it has a rise time, exponentially rise time, and it's a pretty slow one. Okay, so a second order system or an RLC system can in fact have a faster response, but it runs into the problem of overshoot and settling time. So this is one interesting thing that I wanted you to see. We can also look at the longer time, let's say 100 seconds instead of 50 seconds. Okay, so now you can see that the voltage of the capacitor has basically effectively become the voltage of the source. If I apply 1 volt, the voltage of the capacitor as a function of time eventually becomes that, because the current dies off. But then we have all these oscillations and a very large overshoot here. And this period from 1 second that we apply the voltage to, let's say, 60 seconds that the oscillations die is called the settling time. And obviously in this circuit it's very long. Okay, so I hope you enjoyed this lecture. Please stay tuned. I have more lectures to come, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. So as a quick recap, we said that in general we want to solve a differential equation such as y prime equals f of x and y, right? And we said that this is the most general case for an ordinary differential equation, or ODE. And then if the right hand side, the function, doesn't depend on y, so y prime is just f of x and x is the variable, then the problem is just doing a numerical integration, right? So that doesn't have any challenge, we already know how to do it. But then we said that in general, in order to solve y prime equals f of x and y, we need to have initial condition, which is also called IC, initial condition. And typically it's given as a point for x, and it's mostly x equals 0. But here we can have anything like x equals a. So y of a is given. Sometimes instead of initial condition we have final condition, y of b equals yb. So in general, in order to be able to solve the differential equation, we have to know the value of the function at some point. And based on that, we can find the value of the function at the later points or earlier points, right? Both are possible. And we said that the common numerical approaches, the very basic one is Euler method, forward Euler method, and then backward Euler method, midpoint method, Runge-Kutta method. And in particular, we talked about Runge-Kutta fourth order. And later we will talk about the general family of the Runge-Kutta, which also includes Cash-Karp method and Fehlberg method. And we said that most likely we always end up using RK4, Runge-Kutta fourth order, but in general the stability of the solution depends on the ODE itself, depends on the actual equation for the ODE, alright? And sometimes it's better to use backward Euler method. It has more stability than the forward Euler method, but then it adds more computation costs. So explicit methods such as forward Euler method or Runge-Kutta RK4 are typically used because they are explicit, so they can easily give you the values of the function at the later points, all right? And we said that in general the idea here is that at each point x we can estimate the value of the function at some very small point next to it, x plus h. And the Euler method, the forward Euler method, is just estimating y prime based on a simple forward difference. And then we said that the key point is that in order to start from point x equals a, which y of a is given, the initial point is given, and in order to find the value of the function at the later point b, we create a sequence of the values of the function that converges to the value of the function at point b. And the way we create this sequence yn is by basically discretizing the interval between a and b into n sub-intervals. And we always go for uniform partitioning in this case, because non-uniform partitioning or quadrature partitioning is just has more complicated equations. So we just prefer to do uniform partitioning, all right? And then we build the y and x at each point. X is just by adding the h to the previous x because it's uniform partitioning. And then y, for Euler method, we just evaluate the f at xi, yi, and then we get yi plus 1, right? And then the key here is that this sequence converges to the exact value of the solution, right? And we said that therefore the way we do it, we first create a sequence object, and based on the method that we choose, for example here Euler method, we create a sequence that converges to the value of the solution at some point, let's say x1 or b, right? And basically n here in this lambda expression, n is the number of sub-intervals from a to b, and this for loop just generates the sequence, right? And then we said that the beauty here is that this becomes a general approach. So instead of having Euler sequence, we can have Runge-Kutta sequence, we can have midpoint sequence, we can have Cash-Karp sequence, whatever. The only thing that changes is this for loop, the way we generate the yn sequence. That's the only thing that changes in our implementation in Java. Everything else is exactly the same. And that's very beautiful, because not only it makes the implementation much easier to understand, also because now that we have a sequence and we're looking for the limit, we can use sequence acceleration. And in this case, we should use Richardson acceleration. And we prove this by just looking at the Euler itself, and we said that it has a painfully slow convergence. But once we apply third order or fourth order Richardson acceleration, we see that the convergence becomes very fast, all right? And then we said that in order to avoid the error at a very far points from the initial point, we can use the previously calculated solutions, the previously calculated points, as the new initial point for finding the solution at the later point, right? And we prove this point by looking at one of the important equations, which has an exponential solution. And it turns out that the exponential solutions, y prime equals some number times y, is actually a measure of the stability of a differential equation, a first order differential equation. We will talk about this later, because in general exponential functions have the fastest growing or fastest decaying behavior in any natural physical system, right? So if the solution doesn't have much error for exponential solutions, then we can be confident that the numerical methods are stable. And then we looked at more examples of the Euler method. Here I'm comparing the exact solution with the Euler plus fourth order Richardson acceleration. Then from Euler we said that it has a very poor order of error. That's why we have to use convergence acceleration. But then now we said that we can actually improve the error by making a better estimation of the y prime, right? And we said that one way is to look at the midpoint method, and that basically says that, okay, the slope of the secant line must be equal to the slope of the tangent line at some point inside the interval xn and xn plus 1. And obviously the reasonable choice is to approximate this point with the midpoint of the interval. So yn plus 1 is yn plus h times f of xn plus half, yn plus half. So xn plus half we can exactly calculate it. Yn plus half, we don't know the value of the solution at midpoint. So we estimate it with the Euler method. So yn plus h over 2, because now from xn to cn, if cn is the midpoint, the step size is h over 2 times f of x and yn. All right? This is how we constructed the midpoint method. And we said that this has, on a uniform partitioning, it has 1 over n squared error or h squared error, which is 1 order of magnitude better than the Euler. But obviously the price that we are paying is evaluating the function f of x and y at twice, right? We're evaluating function twice. And that's the general trade-off in general for solving differential equations, ordinary differential equations in this case, is that we are trading the accuracy with the number of times we need to evaluate the function. And then we said that we can extend this way of thinking about increasing the accuracy of the solution by going to higher order approximations, and the famous one is Runge-Kutta fourth order, okay? And it creates a sequence yn plus 1, which is yn plus 1 over 6, k1, 2k2, 2k3, k4. And again, uniform partitioning, and k1, k2, k3, k4 are given by these equations. And so for the fourth order Runge-Kutta, that gives us a h to the fourth error. So it's a fourth order error. We have to evaluate 4 times. All right. So for Euler, the error is order h, and we evaluate 1 time. For the midpoint, the error is order h squared. We evaluate twice. For RK4, the error is fourth order, and we are evaluating 4 times. Now it turns out that after RK4, if we are trying to find order of h to the fifth order error, we have to at least do 6 evaluations of the function, not 5. It's not possible to do 5 evaluations. And we'll discuss this in more details when we talk about the general Runge-Kutta family. That's why the RK4 is always considered the sweet spot, because it gives you the fourth order error with the minimum possible evaluation, which is 4 times. So if I evaluate the function 5 times, I still get a fourth order error, not a fifth order error. For a fifth order error, I have to evaluate the function 6 times, not 5 times, okay? And we said that the interesting thing is that if the right hand side, the function f of x and y, does not depend on y, then the Runge-Kutta fourth order becomes the Simpson's method for integration, which we discussed in details when we talked about numerical integration. And again, to reiterate, for numerical integration, if y prime is just equal to f of x, we always prefer quadrature methods that operate based on a non-uniform partitioning of the interval, because they always have better than linear convergence. They have a superlinear or quadratic convergence, unlike uniform partitioning that can never have anything better than sublinear convergence. And the same thing for Runge-Kutta. We said that we create this sequence of functions by partitioning the interval between a and b. A is our initial point, b is the point that we are trying to find the solution. And then we don't even need to do any Richardson acceleration. We can create the Runge-Kutta sequence easily by, again, the code is exactly the same as Euler and midpoint. We just change this implementation inside this for loop that generates this sequence, yn, okay? So we calculate k1, k2, k3, k4, and y is y plus k1, 2k2, 2k3, k4 over 6. And we start from y0, x0, and then becomes y1, x1, y2, x2, and etc. Eventually, it returns yn, and this is a multi-line lambda expression, all right? And then we said that the Runge-Kutta method does, in fact, have a very fast convergence, and we took n equals 20 as the stop point for RK4, all right? And then the same thing here with evaluating over a very large interval. We take the previous points as the initial points for the next point that we evaluate. when we pass in an array of x values to solve the solution. All right. And then we said that now we want to, most of the time we have a system of first order differential equations that are coupled together, and this is the general format of the first order system, right? y1 prime, y2 prime, ym prime. So we have m equations, and these are equal to f1 of x, y1, y2 to ym. So x is the variable, y1, y2 and ym are functions, real functions, the functions that have real value, right? And the goal is to find y1 all the way to ym, and we have m equations. We cannot have less than that, and if we have more than that, we cannot have a unique solution. And in order to find a unique solution, not only we should have exactly m equations, but we also need to have m initial conditions. All right, y1 at x0, y2 at x0, and ym at x0. And the general approach was to use any method and define a sequence that converges to the value of all the functions at the given point, and then we do acceleration or whatever we need. And again, in order to make life much easy in terms of the implementation, we went with a vector-based approach or an array-based approach, and we said that for all the previous methods, Euler, Midpoint, Runge-Kutta, that basically generates a sequence. The sequence is still valid for a vector, right? Each vector represents one of the functions, y1, y2, each component of the vector, right? So we have a y vector. A y vector is equal to y1, y2, ym, all right? And in order to do that, we implemented an object called nd array, and this array is basically encapsulates a typical double array with the support for operator overloading. And the reason we did that because we wanted to avoid writing a lot of for loops and whatever. It's just much easier to have an array object that already supports operator overloading. All right. And then we also defined a vector-based or array-based sequence. Array sequence is basically when we evaluate it, it returns an array, nd array. And if we want to get the sequence for a particular component of this array sequence, we use a lambda expression that represents a sequence. So we evaluate at n, which returns an nd array, and we just call the whatever index we're looking at, all right, for this array. And as you can see, we create our array func. So this is a basically this function represents the this vector, this array, right? So this function returns an n-dimensional array, right? Takes x and all the y values, and then we create the Euler sequence, and then this way. And we showed that this method works very well. And here I'm using fourth order Runge-Kutta. And then we looked at many examples, like oscillatory example. And again, to note that so far all these functions are assumed to be real functions. They have real values. They don't have a complex value. All right. And then we said that actually one of the very nice use cases of the way we are solving a system of first order differential equations is that we can actually use it to solve a higher order differential equation, a higher order linear differential equation. And we said that by linear, it has to be linear in the highest order derivative. It doesn't have to be linear in, here for example, we have y double prime, y prime, and y. It has to be linear in the y double prime. It could be y prime squared or y squared, doesn't matter. And we said that we do a change of variable and convert this, for example, second order differential equation into a system of two first order differential equations. And the beauty is that when we do this and solve the system of differential equations, not only it gives us the value of the y, it also gives us the value of y prime. And then based on an algebraic equation, we can also find the value of y double prime. So this way of solving higher order differential equations allows us to immediately find y, y prime, and y double prime. And we had examples, for example, a free falling ball, a mass spring system that gives us a second order differential equations, and an electric circuit, RLC. And then the next question is that, okay, so far we have looked at the equations for which all of the functions, for example, if you look at this y prime equals f of x and y was a real function, x is a real variable, and y is a real function. Now the question is, in most situations in physical systems, we have a complex function that has an amplitude or phase, or a real part and imaginary part that is in fact describing the state of the system. So it's not a real function, it's a complex function. So far our variable and functions were real valued. In most cases the variable is real, so the variable is real, but the functions are complex. And this happens all the time in physics, in mechanics, in electrodynamics, in quantum mechanics, all the time. So complex functions represent the phasors of a sine or cosine function. So the phasor, what do we mean by phasor? So if you look at the general representation of a cosine or a sine function, a general representation is that if I have the cosine function, it could be an amplitude times cosine of omega t. Let's say t is our variable, or x. Typically it's t. In physics, t represents time. So this is more like the oscillation in time. So t is the variable, omega is the frequency, and then some phi, some phase, right? This is the most general case of a cosine or sine function. And this can be very well described by the amplitude and the phase. So this a times cosine of omega t plus phi equals to real part of a complex function, a e to the j phi e to the j omega t. And the phasor is defined based on the complex amplitude and phase. F, the phasor f, is equal to a times e to the j phi. So if this is the phasor, you see there is no time dependence in the phasor. So f of t, the real value, the time dependent function is real part of the phasor, the static phasor. It doesn't have any time dependence, times e to the j omega t, which represents the oscillation. That's the definition of phasor. So one-dimensional ODE in a finite interval a and b, again, it's y prime equals f of x and y, but now y is complex. And the initial condition y of a is y0, now y0 is complex. Y0 is complex, is a complex number, all right? So have this in mind. Y of x is a complex number, x is real, so we are still assuming that our variable is real, f of x and y. So in general, f of x and y, x is real, y complex, so f of x and y is in general a complex number, a complex valued function. So how do we solve this? So the way we're going to solve this, we're going to build based on what we have built so far in terms of solving ODEs. We can solve a real valued ODE, we can solve a system of real valued ODEs. So it turns out that if I write y of x in terms of its real and imaginary parts, so because any complex number, any complex function can be written in terms of a real function plus j times another real function, right? U and v are real functions. U represents the real part of y of x, and v of x represents the imaginary part. I can always do this. Now take this and put it in the y prime equals f of x and y. And note that we can also write the f of x and y in terms of its real and imaginary parts. So f of x and y is f sub r, f real of x, u and v, right? And j times f imaginary, x, u and v. So if we do this, we can say that, okay, when two complex numbers are equal, the real part must be equal to the real part, and the imaginary part must be equal to the imaginary part. So both conditions should be satisfied simultaneously. That's why if I put u plus jv on the left side, I get u prime plus jv prime. On the right side, I get f of r plus j f sub I. So u prime must be f sub r, the real part of x u v. V prime must be f imaginary x u v. Now we have a system of two real valued ODEs, U and V, and f of r, f sub r, and f sub I. And we already know how to solve this, right? So a complex valued ODE with a real valued variable. Remember, the variable is real. If the variable is complex, things get way complicated because functions of complex variables behave quite completely differently from functions of real variables. Okay, so here we are still assuming that the variable is real. A complex valued ODE is a coupled real valued ODE system. That's the baseline. That's the conclusion here. And we already know how to solve this system of two equations, right, for real valued functions. So the problem has been already solved. We have already solved the problem of solving complex ODE of complex functions. The only step here, the only extra step is to convert the original equation y prime equals f of x and y into the system of equations u prime equals f sub r and v prime equals f sub I. That's the extra step, right? And that's what we're going to do. So I'm going to define an interface, derive function complex, and it returns a complex value. So this represents our complex function f of x and y. X is real, it's a double value, and y is a complex valued function, right? So x real, y complex, and returns a complex value. And then we define our ODE solver complex class. So this solves an ODE system, ODE equation, y prime equals f of x and y. Y and x are both complex. We pass in our f of x and y, which is complex. We pass in our initial value for x, and we pass our complex initial value for y. All right. Now all we have to do internally is to define an ODE system solver and a derive n function. So remember, derive n function, this was used for solving a system of real valued ODEs, right? So we have this function complex x0 y0, and then this func system represents the derive n function for basically the system of real valued ODEs, the u prime and v prime, right? So it takes x, which is real, z, which is an array of two variables, u and v, or z0 and z1. So z0 is the real part, u, z1 is the imaginary part, or v, okay? So z0 is u, z1 is the imaginary part, and v. So what I'm going to do here, I'm going to call the function, this complex function, passing x and y. What is y? Y is u plus jv. So it's z0 plus jz1, all right? And this returns the value of on the right hand side, this one, okay? And then my equations are the real part of this function and the imaginary part. So the function for the system of two ODEs is double val, this complex function, the real part, and val imaginary part, all right? And the system solver ODE, the ODE system solver has two equations, right? So we pass in our func system that represents the two differential equations, x0, and then we have to also break the complex initial condition into two real valued initial condition. So u is the real part of the y, so its initial condition is the real part of the initial condition of the y, right? So y0 dot real part, y0 dot imaginary part. And then we do a pass-through. Pass-through means now if I want to, now I can create an array sequence method, Euler sequence at some point, and we just call this ODE system solver and call the Euler sequence at this point. This returns a sequence that represents the u and v, and the values of this sequence must converge to the value of the u and v, the solutions, the real part and the imaginary part, all right? So let's look at some examples. Y prime equals minus y. We write y of x in terms of its real value, u of x plus j v of x, right? And then we put it on the both sides. The left hand side is u prime plus jv prime. The right hand side is minus u minus jv. So u prime is minus u, v prime is minus v. And what we see here is that there is no coupling actually between the real part and the imaginary part of y, right? Now let's look at another example. Y prime equals minus y squared. So left hand side is u prime plus jv prime, right hand side is minus u plus jv squared, which is v squared minus u squared plus j minus 2uv. So in this case, the u prime is v squared minus u squared, v prime is minus 2uv. Now we see that there is actually a coupling between the real part and the imaginary part of the solution. Okay? And in both cases, our approach works fine, because no matter if there is a coupling or not, no coupling between the real part and imaginary part, our ODE system solver solves the system of u prime equals something, v prime equals something, and returns the solution, right? So our Java implementation is simple. We define the complex function f of x and y that represents the complex value of the right hand side. So it takes x as a real variable and y as a complex variable and returns a complex number. And then we define an ODE solver complex class, and all we do in this class is to transform the original problem into a system of two ordinary differential equations, right? And then we do a pass-through methods for solving, for example, Euler, Runge-Kutta, and they return array sequence or the solutions or whatever. So let's look at an example. So y prime equals minus y squared, and y of x is u of x plus j v of x. So u is the real part, v is the imaginary part. And the initial condition is given as y at 0 is equal 1 plus j, right? So in the past we had a real number here, but now we have a complex number here. And this differential equation has an exact solution. Y of x is 1 over x plus 0.5 times 1 minus j. So this is already a complex number. So the solution is 1 over x plus some complex number. If I put x equals 0, this becomes 1 over, basically 2 over 1 minus j, which is 1 plus j. So it satisfies the initial condition, and obviously you can confirm that it also satisfies the differential equation, which is very easy to see. So let's look at y at 1.5. So the initial point is 0. We're looking at a later point, 1.5, which is 0.470588, the real part, plus j times 0.117647, the imaginary part. Now we use our array sequence method here for the Euler sequence, and this returns sequences that converge to the real part of the solution and the imaginary part of the solution. Okay, so let's see what happens. As we expect for the Euler method, the convergence is painfully slow, but we definitely see the convergence, and they converge to the basically the actual or the exact solution. All right, so let's look at the code. We want to solve y prime equals minus y squared for complex function y. So y is a complex function, and it's only one differential equation. So we call our derivative function complex func, which represents takes a real variable x and a complex variable y, and returns the complex value of the right hand side, minus y squared. And this pov is coming from my complex math class. It's not coming from the math library of Java, because y is a complex. All right, so minus y squared, and then the initial value for x is 0. The initial value for y is a complex number 1 plus j. And then the ODE solver complex, new ODE solver, we pass in the function, we pass in the initial value for x, the initial value for y, and then we create an array sequence yn that is basically it has two components. The first one represents the real part of the solution. The second component represents the imaginary part. So we take our ODE solver and call the Euler sequence at x equals 1.5. So we call the Euler method. It creates an array of sequences, two sequences that converge to the real part and imaginary part of the solution at 1.5. And then we create an array of indices, an array of complex functions that represent basically the complex solutions. And then for int I equals 0, I less than length of the indices plus indices I is basically I, and then we calculate this sequence at I. It returns an ND array with 2 components, and the yn vals, the complex value, is the 0th component plus j, the 1 component. All right, and then we create the figure passing the indices and the complex array. It already when we do this, it already plots the real part and the imaginary part separately. All right, and then yeah, so we see that definitely there is a convergence, and it's converging to the right values, but it's very slow. So we can do a Runge-Kutta fourth order, for example, and note that I'm using J by importing static members of the complex class from my mathlib library, and I'm using the POV, as I mentioned, from my complex math class in my mathlib library by importing the static methods in the complex math class. All right, because remember, y is a complex number, so you cannot use the power method in the Java's math library. You have to use a complex version of the power function. And here I'm plotting the solution from 0 to 20, all right? So 50 points, and we also evaluate the real part and imaginary part of the exact solution, and then we're doing the comparison. We're plotting the real part and imaginary part for the exact solution and the Runge-Kutta solution. And as you can see, our ODE solver complex, which basically breaks down the complex differential equation into a system of 2 real function ordinary differential equations, it works perfect, and it gives us the exact solution. All right, so this is the basic of calculating the or solving ODEs with complex functions. And it's very important because, again, in physics, in most cases we always have complex numbers, so we always end up with an ordinary differential equations that actually involve complex functions. Now, moreover, even the coefficients can be complex. So far, we've looked at the cases where the coefficients were real, right? But the coefficients could be complex, and our method still works because this derivative function complex is general, right? It takes x, which is a real value, and y complex, and it returns a complex number. So it doesn't care about whether or not the coefficients on the right hand side are real or complex. They could be complex, doesn't matter. And in the next lectures, I will look at the examples that the right hand side of the equation is actually has complex coefficients. And we see that our method for solving the ODE of a complex function works perfectly. So I hope you enjoyed this lecture, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussions on solving ordinary differential equations of complex functions. And I'm going to continue with another example. And this example is from an actual scientific publications. So here's the publication from Satcher and Poon, Dynamics of Microring Resonator Modulators. So this is an actual recent research. It was published in 2008. Maybe not very research, but we see that, as I mentioned before, this type of if you look at this publication, for example, the whole point here is to solve a differential equation that includes a complex function, and the right hand side is actually a complex function that has complex coefficients. So that's one of the examples that we're going to look at. And this is called a rate equation, a complex rate equation of a resonant modulator. And the rate equation is typically basically d dt. T is the variable of time of some function equals some function, right? This is the rate equation because the left hand side is the rate of change over time of the function, which could be real or complex, and the right hand side is basically describing how this rate of change depends on the other parameters of the system, right? And you don't need to understand the physics of the system at the moment, but in general we have some input light that comes in, A, which in general can depend on time, A of t, and then some of it goes into the resonator and it starts to go around and resonate. And applying an electrical voltage to this resonator can alter the behavior of the resonator. So V of t can be an input to the rate equation. And then eventually what we're looking for is the output, B of t, right? And then there is a state variable of the system, which is the internal energy of the system. But this internal energy is a complex number, so the magnitude squared of this quantity, small a of t, is basically the energy stored in the resonator at each time. But then because this voltage can affect the phase of the light inside this optical resonator, we are also tracking not only the energy but also the phase of the system. So eventually the whole problem is solving this rate equation. d dt of A of t is J, the resonant frequency of the cavity of the resonator as a function of time, minus 1 over tau. Tau is basically represents the time constant for the energy to be lost inside the cavity. So it represents how long it takes for the energy to be dissipated from the resonator through the loss mechanisms that are inside the resonator. So it's like the lifetime of the energy, right? And then A of t again is the state variable. So we have a complex number which actually depends on time times the state variable itself, the function, minus j mu. Mu is a parameter that describes the strength of the coupling between the input and the resonator. A of t is the input amplitude, input light, right? So A of t is given, mu is given, tau is given, and then omega raised, the resonant frequency is changing based on this voltage. And in most cases, in reality, these devices work based on a linear function. So omega raised is omega raised at 0 voltage times 1 plus some coefficient times the applied voltage, all right? So these are mostly linear systems in terms of the voltage to the energy inside the cavity. So and then the output B of t is again a complex number, is a complex function, is minus j mu A of t. A of t again is a state variable of the cavity plus A, which is the input, which can also depend on time, A of t, all right? So what we want is we want to specify the voltage V of t, we want to specify A of t, the input, and we want to find the output B of t. So V of t, this input signal is a voltage, it's a real. A of t is complex because light can have amplitude and phase. And B of t is also complex, and the output energy of the system is magnitude of B squared, right? And in order to do that, we have to solve this rate equation to find our the energy inside the resonator as a function of the input amplitude of light and the applied voltage, right? And here's the code that I wrote. So I'm going to assume that there are two cases. One is that we don't apply any voltage, but then we turn the light on and off in the input. Let's say we input a pulse of light, and see how the system reacts by looking at the output. So here A is 1, and then this is the amplitude of the pulse of light. So it's 0 and then jumps to A and then comes down. T0 is the initial time, 0, and the A0 is the complex value for the A of t, the initial condition, which is 0, all right? So I'm assuming that at t equals 0, there is no light coming in, so there is no energy stored in the resonator, and then at some time I turn the light on, and then at some other time I turn it off. So when I turn the light on, the energy starts to build up inside the resonator, and as a result, the output starts to change, right? So I define a function double input light, t is the variable. So tau g or tg here is the unit time of the resonator. What it means is that how long it takes for the light to go one round around the resonator, right? So when the light comes in, it goes inside the resonator, it starts to go around, right? So for resonators, we always define this unit time. I'm saying that if t is less than 10 tg or t greater than 80 tg, and tg in general it's around like for actual devices it's about like 2-3 picoseconds, so it's very small. It's 0, so before 10 tg and after 80 tg it's 0, and in between it's a. So I'm defining a pulse, so it's 0, the input is 0 and then goes up to a constant complex amplitude and then comes down, right? And in order to solve this, I define this derivative function complex, which represents the right hand side. T is the real variable and a is my complex function, right? This goes to -1/tau, and I have defined tau somewhere else, like outside, but tau is just a number given, times a minus j mu. I also have defined mu somewhere, times input light dot apply at t. So input light is a function that represents the input a of t, right? So it's 0 and then jumps up and then comes down. And then I create my ODE solver complex object, new ODE solver. I pass in my function, which is this rate equation, t0 initial value for the time and a0 initial value for the function, which we already know that it's 0, right? If there is no input light, there is no buildup of energy. And then I define a time array from 0 tg to 250 tg. So I want to see what happens when light starts to go into the resonator and then up until the light goes around 250 times, right? So the time unit here is tg, 1000 points, right? From 0 tg to 250 tg. And then complex array A is ODE solver dot Runge-Kutta complex. So Runge-Kutta complex basically returns the solution at each time point, at each point of time, the complex solution, right? So if you recall, we said that in the previous lectures that the way we're solving this, we're basically internally redefining the problem from a single complex equation to two real complex equations, and it becomes a system of two real valued equations that in fact couple to each other, and each equation represents the real part or the imaginary part of the solution, right? And then we can put them together to calculate the complex solution, because once we have the real part and the imaginary part, we can find a complex solution. All right. And then the output power is basically the magnitude of the output, b of t squared. So I calculate minus j times mu times a at each time point ai, plus input light dot apply at time I, right? Because if a is a function of time, then it could be present or not present, right? If I turn the light on and off. Dot abs squared. And this is a method in the complex numbers. So this is a complex number, minus j mu a plus input light that apply at time t. And it calculates the abs squared or magnitude squared, right? Which gives me the output energy or output power. And then I just create a MATLAB chart, and I plot based on the normalized time, so t over tg, and then the output power normalized. And the normalized output power, I just take the output power and normalize it to its maximum value. And then I also plot the input light as a function of time. So I want to see what happens if there is no voltage applied. So here I don't have any voltage. I just turn the input light on and off. And I want to see how the cavity or the resonator behaves and how the output light behaves, right? That's it. So I plot the output power, the output b squared, and also calculate the input light, which is a. All right. So let's see what happens. So this red one here, I have the legends, is the input light, and this black curve is the a of t, is the energy inside the resonator. All right. That's our state variable. So A of t is a complex field or energy inside the cavity, and it's in fact our state variable. And as you can see, and as we expect, as soon as I turn the light on, the energy starts to build up inside the resonator. And once I turn the light off, the input off, the stored energy starts to get out, right? Because if there is no light in, as the light goes around, some of it gets out, and eventually after a long time all the light gets out and there is no light inside the resonator, right? So this makes perfect sense, and this energy is normalized to its maximum value. That's why the scale is from 0 to 1. Just I'm normalizing, just it's easier to visualize what's happening, right? Now we can see what happens at the output, right? So the red one is still the input and the output. So as soon as I turn the light on, there is still no energy inside the cavity, so the output gets a very large spike of energy. And then as the light goes inside the cavity, we expect the output to reduce, right? Because now the light starts to go more and more inside, so the output goes down. And again, once there is a sharp change in the input is off, the output gets a spike. It's not as big as the previous one, but it still gets a spike. And then it goes down again, all right? Because once the input is turned off and all the energy inside the cavity has got out, I mean, the output is also 0, right? Because the output is a combination of the input and the stored energy inside the cavity, all right? Now, this is a fairly complicated case, but in general, rate equations appear all the time when you solve, for example, balanced rate equations in fluid dynamics. And now we can solve them not only for real valued differential equations, but also for complex valued differential equations. If the right hand side is a complex, our state variable is a complex, it doesn't matter, we can still solve it, all right? Now, so far, this example shows what happens to the output when there is no voltage applied, or in a more scientific term, when there is no modulation of the energy inside the cavity. So there was no voltage in this example, it's just the input is changing. I turn the input light on and off, and then the cavity reacts, and then the output also reacts, all right? Now, let's look at the modulation. In the modulation case, what I'm going to do, I'm going to first turn the input light on. A of t is this green curve. This green curve is input light. So I turn it on, and then the output and the voltage is still off. This red one is the voltage. So the voltage is off. I turn the light on, and then we know that the output gets a large spike because initially there is no energy inside the resonator, but then the energy starts to build up, so the output goes down. And then at some point later, when the output is completely 0 and the cavity has built a lot of energy, I turn the voltage on and off. So I start to play with the energy inside the resonator. I start to distort it. And once I distort it, I turn the voltage on, the output starts to go up. And then reaches a steady state, a constant, and then as soon as I turn the voltage off, the output also goes down, right? So this is how we are translating the electrical signal, this electrical voltage. Remember, the voltage is an electrical signal. On the light, right? The output is the light. This is the optical power, right? I mean, the scale is not, it's been normalized, so it doesn't matter. It's just a normalization, but you see how the output behaves. So we are translating an electrical signal, a pulse, onto an optical signal. This is called optical modulation, all right? Performing optical modulation. And this whole paper, Dynamics of Microwave Resonator Modulators, is all about this, right? And we see that how easy it is to, if we are able to solve this rate equation, it's very easy to understand what really happens. And again, the way we implemented this in Java really gives us a powerful tool for analyzing all these rate equations, all these resonant structures. So this optical modulation, the thing that I want to point out here is this rise time and fall time, or this delay, this time that it takes for the output light to actually get to its maximum value and it stays constant and then goes. So there's a rise time and fall time to the pulse. Even if I have an ideal voltage pulse, my cavity, the resonator, doesn't respond instantaneously, because energy needs to build up. Any change in the energy has to take place over time. That's why we see this rise time and fall time. And there are ways to make the cavity faster, which it's related to some quantity called modulation bandwidth or modulation frequency response. You can just Google it and see, look at different scientific papers about that. All right. So this was one of the very interesting examples. Even if you are not a scientist, if you just follow these lectures, you should be able to solve these complicated systems and see actually what happens in reality. And what I'm going to tell you is that if you build this and solve this equation and build and fabricate this device and measure it, you will exactly see this response. So this is not the abstract math that we're talking about. This is the reality. You will definitely get this response. I have done it, I have measured it, and this is exactly what you get. So believe me when I tell you that this complex structure, this is just described by this rate equation, and we are able to solve it and analyze it, and that's very interesting. All right, now obviously the last step is that if I can solve one ordinary differential equation of one complex function, the next step is very naturally is to extend it to a system of complex ODEs, a system of ODEs of real valued variable x and basically m equations of m complex functions. So here in these m functions, m equations y1, y2, ym are complex functions. They all have real and imaginary parts, and therefore f1, f2 all the way to fm are also complex valued in general. They have real and imaginary part. X is a real variable, and y1 all the way to ym are basically complex functions. So the goal is to find these complex functions. We obviously need exactly m equations. If we have m functions, we also need exactly m initial conditions to be able to uniquely solve the system, right? And again, the initial conditions in this case are all or can all be complex numbers, are all complex numbers. So how do we solve this? So if each equation has a real part and imaginary part, then we basically do the same thing. We break this system down into real and imaginary parts of the functions, right? So from m equations, we end up with 2m equations. But those equations now are real valued. Everything is real. So we convert these m complex equations into 2m real equations. And once we do that, we already know how to solve it. So it's no brainer. We've done it. We know very well how to do it for a system of real valued equations. So we define an array of size 2m, and then basically for each equation, I do it like this. So for y1 prime equals something, I end up with the real part of y1 prime and the imaginary part of y1 prime. So I have 2m of equations, 2m equations, and the order is like this: the real part of y1, the imaginary part of y1, the real part of y2, the imaginary part of y2, etc. So the index of 2k, k could be 0, 1, 2, all the way to m minus 1, is the real part of the function yk, and then z 2k plus 1, and let me write it down here. So k goes from 1, 2 all the way to m. All right. Now obviously here our indexing is from 1 to m, but in Java we index from 0 to m minus 1. All right. So the idea here is that the index 2k is the real part of the solution yk, and the 2k plus 1 is imaginary. And then the real equations are arranged based on the real and imaginary parts of each complex equation. All right. So it's completely up to you how you rearrange the real and imaginary parts, but I think it's this is the most natural way. The real part of yk, the imaginary part of yk, the real part of yk plus 1, the imaginary part of yk plus 1, etc. All right. Okay, so here's the way we're going to do it. So we create a new object ODE system solver complex, and we define deriv n function complex. So deriv n function complex is like a deriv n function, but instead of taking an array of double values for y, it takes an array of complex values for y. So we can go to Eclipse quickly. So in the ODE project, in ODE package, we had deriv n function takes the real valued variable x, an array of double values, and returns the array of double values for all the equations. And then deriv n function complex takes the x, real valued variable, and the complex values y, and returns an array of complex numbers, which represents all the complex equations. Okay, so this is our functional interface. And then what we are going to do, basically the idea is the same. We take this complex array, complex function, and transform it into 2m equations of real valued equations, of real valued functions. And internally we create this func system that represents the 2m systems, 2m equations, real equations, and then the ODE system solver that solves this 2m real ODEs. All right, that's the whole point. So x0 is the initial value for x, y0 is the initial value for y, the complex functions. That's why y0 is a complex array. Number of equations must be equal to the length of the initial conditions. We must there should be an extra check here to confirm that the number of equations that is determined by the array that this complex function returns must equal to the number of initial conditions. I mean, I don't have it here, but you should implement it. That's an extra check to make sure that we can in fact get a unique solution after solving the differential equation. And then I'm going to also create an initial condition for those 2m equations after we break these m equations into 2m real equations. So y0 real image is a double array of twice the number of equations. So y0 real image at 2i index is the real part of y0 at I, and remember y0 is complex, or y0 at index I is complex, and y0 real image at 2i plus 1 is the imaginary part. And again, this is based on my convention that the solution, or when I break these complex equations into real equations, into the real part and imaginary part, the index 2k is the real part of the yk, and the index 2k plus 1 is the imaginary part. That's why the initial conditions also must correspond to this convention. And now I'm creating the 2m system of real equations. So I create an array of complex numbers for the m equations, number of equations, and this value I is basically so this z is an array of 2m elements. So, and it holds the values of the y functions z2i plus j, z2i plus 1. All right, these are the complex values. Why am I doing this? Because I have to pass the complex values to this complex function. All right, and then equations complex is an array, and that's basically after calculating the complex function at x0 and the values, the complex values of the functions. All right, and then we have 2m, or twice the number of equations for the equations that have been broken down into the real part, imaginary part. So 2i, the index 2i is the real part of the value of the function, complex function, and the 2i plus 1 is the imaginary part. So once I have all these 2i or 2m equations, I create my ODE system solver by passing in this function system, the x0 and the y0 real image, which is the initial value for the real part and imaginary part. All right, this is the whole idea. Once we do this, the rest is exactly what we already know. So let's head to Eclipse. So ODE system solver complex, and the Euler method, again, we have a method Euler sequence that generates an array sequence which has 2m. The length of this array sequence is 2m. So it represents all the real and imaginary parts of all the m functions. And we just call the Euler sequence for this ODE system solver, all right? And then we can have the values of the solution at each point, the values of each of all the solutions for an array of the input x, so it's a two-dimensional array, and also the complex array for at each point for all the m functions, which is basically we take them and add the j here, take the real and imaginary part and put them together. Or if we want to find the complex solution at some array of x values, it should return a two-dimensional complex array. Similarly, for the Runge-Kutta, we just call the Runge-Kutta on the ODE system solver. So everything is the same, no matter what method we use. This way of implementing solving ODEs in Java, the way I'm doing it or the way we're doing it, it's a very powerful way because it's very easy to add more methods for solving, and the general skeleton or the general way of implementation is exactly the same. All right. So back to the PowerPoint, here's an example. And I have an oscillatory system. We already have seen this system before, but in the past it was real valued functions. So the coefficients are real. y1 prime is minus y2, y2 prime is y1. All right. So the equations are exactly the same. But now the initial conditions are complex numbers instead of real numbers. Now in this case, if the initial conditions are real numbers, the solutions are always real. If the initial conditions are complex, the solutions end up to be complex. And this system of equations turns out to have exact solutions, and y1 is minus sine of x, the real part of it, plus j, 2 cosine minus sine. So it has a real part and imaginary part. y2 is cosine of x plus j, 2 sine plus cosine. So it also has a real part and imaginary part. And we can confirm that at x equals 0, y1 of 0 is 2j, y2 of 0 is 1 plus j, and y1 prime is minus cosine plus j minus 2 sine minus cosine, which is minus y2. And y2 prime is y1, right? y2 prime is sine plus j, 2 cosine minus sine. So this is the unique solution of this system of differential equations with complex functions. And we don't see it immediately in the equations that the solutions are complex, but the complexity of the solution, whether or not the solutions are complex numbers, in this case is determined by the initial conditions. All right. Now here's the code. I'm using the Runge-Kutta method to solve it, and y1 is z0 here, so I define my deriv n function complex, x and z. X is a real number, z is an array of complex values, complex functions. New returns a complex array. So z0 is y1, so z0 prime is minus y2, which is z1, so minus z1, and z1 prime is y2 prime is y1, which is z0. All right. And then x0, the initial condition 0, complex array y0. So y0 is the complex array, so it's 2j for the z0 and 1 plus j for z1. And we create our ODE system solver complex, new ODE system solver complex. We pass in our complex function. It's not a function, it's an array of functions, right? It's two functions, or a 2D array, array with two components. Pass in our initial condition for x, our initial condition for y, which is a complex array, an array of complex numbers. And then we want to evaluate the solution at from 0 to 4 pi at 1000 points. We also want to evaluate the exact solutions and compare them with the result of the Runge-Kutta solution. So exact is only at 50 points. So basically exact here is the markers, and the solid curves are the Runge-Kutta solution. And then, okay, so we have our ODE solver, and we call the Runge-Kutta method on this array of x values, and it returns a double array. All right. Now it can in fact return a complex array, but the complex array here, or maybe we go back here, ODE system solver complex. So if I call the 2D double array on the Runge-Kutta, it basically returns a two-dimensional array that the rows represent separately the real part and the imaginary part of the solutions. If I call the complex one, it returns a 2D array of complex numbers. Each row is the complex solution of each function, right? So here this 2D complex array has is basic the number of rows. Number of rows is equal to n, number of equations that we already have. Here basically if I call the double solution, here the number of rows is 2n, twice the number of solutions, because now each row is real part plus, and the next row is the imaginary part of the solution. Okay, but so in this example I want to get the real part and imaginary parts and plot them separately. So when I get this, z0 is the solution of the y1, the first function, the real part. z1 is the solution of the first function, y1, the imaginary part. z2 is the solution of the second function, y2, the real part of it. And z3 is the solution of y2, the second function, the imaginary part of it. All right? And then I create my chart, plot the x values, y1 real, and with blue color. So the blue one is the real part of y1, and then y1 image with the black color. So this black one is the imaginary part of y1. I also plotted the exact solution with markers, and as you can see, this Runge-Kutta solution for our complex system matches perfectly with the exact solution. All right, and here's the y2 solution. Again, the same thing. The solid ones are the real and imaginary part of the Runge-Kutta, and the markers are the exact solution, the real part and imaginary part. As you can see, it's a perfect match. So our implementation works great. All right. Now the last thing here is that in order to make life easier for ourselves, we can create a helper class with a private constructor, so we don't want the user to instantiate it. Okay, now this helper class has one method, get ODE, which is a static method. All right, but it is overridden, so we're doing it is overloaded, so we're doing method overloading. Why? Because we want the user to easily basically call this class ODE and call the get ODE function. It's much easier to remember because we have defined 4 different types of ODEs, right? And the method, because we're using method overloading, the method already takes care of which one to call based on what kind of deriv function the user passing, right? So if user call the get ODE method with a deriv function, the type of deriv function, it means that the user wants to use to solve one ODE of a one real valued function, right? It's a real ODE with a real valued function. If the user called the ODE method, exactly the same method, get ODE, with a deriv n function, it means that the user wants to solve a system of real valued ODE functions, right? A real ODE system, an ODE system with real valued functions. So if the user calls the get ODE with the deriv function complex, it means the user wants to solve one ODE equation with a complex function as the solution. If the user calls ODE, get ODE, again the same method but overloaded with deriv n function complex, it means that the user wants to solve a system of ODEs with complex functions, right? The solutions are complex functions. So I think this is easier in terms of usability, because you just call this ODE and one of the static methods, and which one is called, the compiler determines based on which function the user is passing it. as the descriptor of the ODE system. All right. So I hope you enjoyed this video, and thank you for watching, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations, and in this lecture, I'm going to start with looking at the concept of steady state solutions for a ODE or a system of ODEs. And by a steady state, we mean that in general, as we said before, an ODE is y prime equals f of x and y for one single equation, or y could be a vector. So then f is also a vector which represents a system of differential equations. Okay. Now, if our variable is x, we want to see what happens when x goes to infinity. And if variable is time, which is basically where the name steady state comes from, when t goes to infinity, or after a very long period of time, what happens to the solutions? Do they reach a constant value and don't change anymore, or are they constantly changing? Obviously, for a system that has a resonant response, like the solutions are sine, cosine, it can never reach a steady state solution, right? Or basically it can never reach a constant solution when the derivatives are zero, because the solutions are oscillatory. They change constantly over time. But there are many systems that can in fact reach a constant solution after a very long period of time, or when the variable x goes to infinity. So we're going to define the steady state solution as this. When our variable x goes to infinity, does our system has a non-zero solution? Where so by non-zero solutions we mean that it's a constant solution, So if the solutions reach a constant value, constant level, then we set the ddx to 0 if the variable is x. And then basically this sets the y primes to 0. And then on the right hand side, we have a system of equations. It's not a differential equation anymore. It's just a system of equations. Now, these equations can be nonlinear, right? Linear, nonlinear, because when we talked about the ODEs, we said that the right hand side can be anything, right? F of x and y, and it could be any sort of equation. We don't care that much. So we set all the derivatives to 0 on the left hand side, and then find the solution by solving a system of equations, which in general is a nonlinear equations. The steady state solutions are independent of the initial conditions. And in general, that's the case. So what this means is that no matter what the initial conditions are, because remember, the initial conditions change how the solutions behave, right? But how basically the derivatives start to change. Because at the initial point, the derivatives are determined by the initial values, right? And after that, the function is determined because of its derivatives. But then when the system reaches a steady state, the derivatives are 0, no matter what the initial conditions are, right? So we can conclude that no matter what the initial conditions are, the system will always reach the same steady state solution. And this is very important. And here's an example that I have here. Let's assume I have a system of two equations. Y1 and Y2 are my state parameters or state variables. So my system is determined by Y1 and Y2, and they are coupled to each other via this system of ODEs. Y1 prime is 2 minus Y1 minus Y2, and Y2 prime is 3Y1 minus 5, all right? And first of all, let's look at the steady state solution. In the steady state solution, if the system has such a solution, then we can set the y1 prime to 0, y2 prime to 0, and try to solve the system of equations. So this is a linear equation, very easy to solve. So if y2 prime is 0, y1 is 5 over 3, which is 1.666. And then we put it here in the next equation, 2 minus y1 minus y2 is equal to 0, and y1 is already 5 over 3, so y2 becomes 1 over 3, 0.333. So this system of differential equation does in fact have a steady state solution, a constant solution after a very long period of over the very long interval for the x variable. All right. Now here I'm presenting the solution of the ODE y1 and y2 for different initial conditions. So just bear that in mind. This is different initial conditions. And the point I'm trying to make here is that no matter what the initial conditions are, the system will always reach the same steady state solutions. And it's very clear here. Let's assume that y1 at 0 is 0, y2 at 0 is 0. All right? So what happens here? So first of all, both initial conditions are 0, but we know that y1 prime and y2 prime are not 0, even if both the initial conditions are 0. That if they were both 0, so we didn't have these 2 or 5, then the solution is definitely a constant 0 over time, because the derivatives don't change, the initial conditions are 0, so the system doesn't change. But even if y1 at 0 is 0, y2 at 0 is 0, y1 prime is 2, y2 prime is minus 5 at 0, so the system starts to evolve, starts to change. That's why we see that y1 starts to oscillate, right? But the oscillations eventually die and y1 reaches a very steady level, a constant level, which is 5 over 3, 1.666 as we expect. And y1 starts from 0. y2 also starts from 0. Its derivative at 0 is minus 5, so it has a very sharp beginning, and it starts to oscillate, and suddenly it dies off and becomes a constant over a long period of x, 1 over 3. So this is our steady state solution, steady state, all right? So with this initial condition, the system reached steady state as we expected. And we could, in fact, predict the steady state levels. Now let's change the initial conditions. y1 at 0 is 1, y2 at 0 is 0. So the initial conditions are different. Therefore, the slope of the solutions at x equals 0 is different, right? But again, we see that now the oscillations are different. It goes up for y1, it goes up to 2 before it went up to 2.5. So it goes up from 1 to 2 and a little bit of oscillation and then dies off and becomes constant. Again, 5 over 3, 1.666. y2 the same thing, the oscillations are different from before, but again the oscillations eventually die and then we end up with 1 over 3, 0.333. So the steady state remains the same. So this is the code I wrote using Runge-Kutta fourth order for solving this differential equation with different initial conditions. So we want to solve y1 prime equals 2 minus y1 minus y2 and y2 prime equals 3y1 minus 5. So we define our state vector, so z is y1, y2, this is our state vector. Vector here is basically an array, okay? And deriv n function, this is a system of real valued functions, so we call our deriv n function x and z, and we return a double array of 2 elements. The first one is y1 prime, which is 2 minus z0 minus z1. The second one is 3 z0 minus 5, all right? And then initial condition for x is 0, initial condition for y could be anything, right? Here I'm solving for y1 is 1, y2 is 0. And we create our ODE system solver that solves the real valued system of real coefficients and real functions. ODE system solver, we pass in our function, deriv n, we pass in our initial condition for x, and we pass in our array of initial conditions for y, y1 and y2. And then I'm going to solve for x0 to x0 plus 50 and for 1000 points. And then when we call the Runge-Kutta and pass in an array of x values, it returns a two-dimensional double array for z. Each row is all the values of one of the solutions. So z0, row 0 is all the values for the solution of z0, which is y1. So here I'm creating a chart, plot z0 with blue curve, which is y1. So this is y1 solution. and Z1 is with color red, which is Y2 solution. Render the plot, set the font to 17, X label X, Y label is Y1 and Y2 solutions, and we create the plot. All right. And as you can see, again, the point here is that even with different initial conditions, the transient response is different, but the steady state will remain the same. All right. Now, how do we find the steady state solutions? And as I mentioned, we set all the derivatives on the left-hand side to 0, and then we end up with a system of equations, all right? So we must, and these equations could in fact be any type of linear, nonlinear equations. We might have sine of y1, sine of y2, y2 squared, or whatever. So in general, it's a nonlinear system of equations, okay? So if it's a nonlinear, first of all, it's a system of equations in general. So we have to have a root finding solution or a root finding method that has n-dimensional behavior, can solve for n-dimensional. Second of all, a nonlinear means root bracketing most likely doesn't work. All right. So most of the softwares use Newton-Raphson iterations. We've looked at this for one-dimensional case. Now the problem with n-dimensional case for basically Newton-Raphson is that you have to calculate, first of all, it doesn't need root bracketing, right? So that's good. We just start with the initial condition, so that's good. But then the problem is that we need to find derivatives. And in this case, the derivatives are actually pretty complex because we end up with something called the Jacobian matrix. I'm just going to write Jacobian here. So Jacobian means it's a matrix of partial derivatives. So it's not just it's not just one derivative or two derivatives. You have to calculate the derivatives and then the cross derivatives, dy1, dy2. Eventually it gets pretty complicated first, and then the other thing is that numerically calculating derivatives is not easy, okay? So what do? We use our very powerful particle swarm optimization tool that we wrote in Java. Very simply, it was a very simple algorithm. It's a linear programming. It's just a bunch of summation and multiplications. There is nothing fancy about particle swarm optimization. We don't need any derivatives. We don't need anything. Particle swarm optimization is the best. We're going to find the roots of an n-dimensional function or a system of n equations using our particle swarm optimization. We briefly talked about this when we looked at the particle swarm optimization. Let me just quickly bring it up. So in case for a one-dimensional case, we said that, okay, the way we're going to solve f of x equals 0 for a one-dimensional function f of x, we're going to say that, okay, in general, f of x could be crossing the x-axis. Even if it's tangent and not crossing, that's fine. We define a function magnitude of f or absolute value of f, okay? So if the f does in fact have a root, then that root should be the minimum of the function in the interval that we're looking for, the root, right? Because when we take the absolute value, the negatives becomes positive. So the minimum value can be 0, right? So we said that we take the absolute value of the function, we construct a function based on our original function or original equation such that its minimum values actually becomes the root, all right? So we find the minimum, and the PSO for minimization is pretty fast, pretty good, no root bracketing, nothing, it just works. And then once we find the minimum of this absolute value, we check whether or not it's in fact the root. So we find the minimum in this interval, we put it in the function and see if it's very close to 0 with some tolerance, 10 to the negative 9 or something. So we're going to do the same thing here. And again, PSO that we wrote, easily, we just wrote it. It was very easy to write it for an n-dimensional case, particles with n-dimensional variables. So we already have it there. And then what we do, we just have to translate our system of equations into one single function, because PSO, if you recall, it had one fitness function that was minimizing or maximizing. And we want to ensure that the zeros, the solution of our system of equations, Fi, which is F1, F2, if we have n equations, F1, F2, Fn, the zeros of these are where the minimum of the fitness function happens, all right? So what we're going to do is that we can just basically do we can do, for example, take the absolute value of each equation, f of I equals to 0, and then sum them up. Because if there are some functions that are never negative and their sum is 0, then each one of them should be 0. That's at least for real functions, and we know that here we're dealing with real functions, right? When we take the absolute value of a real function or even a complex function, the result is always real, right? So this g of y1, y2, etc., this becomes our basically fitness function for the PSO, and is defined based on, so this is our fitness function for PSO. Okay, and then it becomes 0 if and only if y1, y2 all the way to yn are in fact the solutions are the solutions of the nonlinear system of equations that we need to solve. So when we do this, we have to do the minimization. So PSO must be set to minimization. But the other things that we actually don't know where these happen, right? Because if you recall, PSO requires an initial interval, initial guess for each one of the variables. And we had implemented two types of optimization. One is bounded optimization. So we set the initial interval for each variable, and then the PSO guarantees that the result at the end should be inside that interval. But here we don't want that, because we really don't know the exact solution. We're just looking for the solution. So we do an unbounded search or unbounded optimization. And what it means is that even if we start with the interval that this minimum is not inside that interval, that's fine. The PSO doesn't have to stay in that interval all the time, all right? So we do unbounded optimization. So here's the code. Let's say I want to solve this y1 prime equals 2 minus y1 minus y2 and y2 prime equals 3y1 minus 5. All right. Now, obviously, in order to find a steady state solution, what I need to do is set the derivatives to 0. So y1 prime is 0. So I have one equation, 0 equals 2 minus y1 minus y2. And the other equation is 0 equals 3y1 minus 5. And I need to solve this system of two equations. So I define my fitness function for the PSO, and it takes an array T. Remember, T is an n-dimensional array. And then I set the T0 as y1 and T1 as y2. So the first equation becomes the absolute value of 2 minus T0 minus T1. The second equation, so I add them together, plus absolute value of 3 T0 minus 5, all right? So if I minimize this, the minimum must be the solution of these two equations, because each one of these absolute values must independently be 0. And I create my PSO, new PSO, 100 particles, passing my fitness function, and then initial intervals for each variable, T0 and T1. And again, it doesn't really matter, the intervals, because we're doing an unbounded search, unbounded optimization. So the PSO doesn't have to guarantee that the solution eventually is inside these intervals. So we just set them to something like minus 100 to 100, minus 100 to 100, all right? And then I definitely want to do minimization. So set minimize to true, set bounded optimization to false. And I believe the default was also false, but it's good to make sure that it's always false. And this is very important, because we actually don't know whether or not the solutions are inside these initial intervals. And then I do solve and plot. The reason I'm plotting the convergence or the values of the fitness function for the iterations, right? For the number of iterations. And then best position is basically t value, right? T vector, T array. It prints the T0 and T1. So what we have here is that if I do if I run the solve and plot for 100 iterations, so I have 100 particles with 100 iterations, the result is very fast, almost takes no time, because we're not doing any calculation of the derivatives, Jacobian or etc. And here's the convergence. So if there is a steady state solution for our system of ODEs, which means if the fitness function does in fact results in a minimum, if a minimum exists for the fitness function, then we should see a very nice convergence. And here we see that. So our fitness function, the PSO with an unbounded optimization, definitely reaches a steady state. Basically, it brings the fitness function to 0. And that's what we want, right? Because we already know that absolute value of something plus absolute value of another thing, if it has a solution, if it's equal to 0, if it has a solution, it can only be 0, right? And we hit this 0, the value of the best value is basically the value of the fitness function. So we definitely hit a solution for this system. And before going to the next slide, I'm going to reiterate that if a steady state solution exists, the PSO minimization will find it, and we can clearly see whether or not it exists if we see a nice convergence in the fitness function and it goes to 0. We can check by looking at the convergence of PSO and whether or not the value of the fitness function does in fact go to 0, right? It has to go to 0. So here's the let's head to Eclipse and try to run this code. In our Eclipse, in our ODE project, ODE package, we have all the interfaces, all the classes, and in the test I have this test steady state solution, and test 1 is basically the code. So deriv n function, this is my system of equations, initial conditions. This basically solves the solution, right? So this solves the ODE with any initial condition that I said. So right now it's 1, 0, and we see that it goes to 5/3 and 1/3, right? 3.3 and then 166. Now let's change it, for example, to 1 and 1. Let's run it again. Again, 1.666, and the transient response, this part is different, right? We start from 1 and 1, and then it has some oscillations and eventually reaches the steady state. Here we start from 1 and 0, and we reach the same steady state. So no matter the initial conditions, we definitely reach a steady state. Now in test 2, we're going to find the steady state directly by solving the equation, right? So this is our PSO fitness function, ABS of 2 minus T0 minus T1 plus ABS of 3 T0 minus 5. We create our 100 particles, we set initial interval, set minimization to true, set bounded optimization to false, 100 iterations, and we looked at the best position, right? So as you can see, we reach for T0 or Y1, we end up with 1.666, 5/3 as expected, and for Y2, which is T1, we end up with 0.333, which is 1/3 as expected. And as you can see, we get a great convergence, right? And it doesn't really take that much time, so it's pretty fast. PSO for finding roots is pretty fast. In general, PSO for minimization is pretty fast, so that's a good thing. And then the next thing about the steady state solutions is that a system may have more than one steady state solution, right? Now in this example, the system is just linear equations, so It either has no solution, one unique solution, or infinite solution. And we saw that, yeah, the system has one unique solution. But what if the right hand side of one of the equations is nonlinear? In general, we might end up with more than one solution. And what determines which steady state will be reached by the system of equations? It's the combination of the ODE itself, how it behaves, like the stability analysis of the ODE, and also the initial conditions, where the system starts to evolve from, all right? So the evolution of the system and the stability of the system itself. For example, if an ODE doesn't ever oscillate, doesn't have any oscillatory solutions, and it always ends up with the growing or decaying exponentials, there's definitely no steady state solution, unless we all of this no, in fact, it can reach a steady state solution if all the solutions end up with only decaying exponentials, right? If a system allows for growing exponentials, but it can never reach a steady state solution. So here's a system which is similar to the previous one, but instead of having 3y1 minus 5, I have 3y1 squared minus 5. Now we have two steady state solutions, because now if I set y2 prime to 0, I end up with y1 equals plus minus square root of 5 over 3, all right, which is plus minus 1.291. So I have two solutions for y1, and then if I set y1 prime to 0, I end up with two solutions for y2, which is 2 minus y1. One is 0.709 and the other one is 3.291. All right, and again, we can find all the solutions. I mean, the way I'm doing it here in this code, I'm creating a list of double values for y1 steady state, y2 steady state values. I just run the PSO 50 times, right? Now, obviously, this is not the best way to search for all the solutions, but what I hope here is that when I run it for 50 times, because PSO, the start point of the optimization in these intervals is random, right? It randomly picks a number for initial value of the y1 and initial value of the y2 in the PSO optimization. So what I'm hoping is that after 50 times of randomly running the PSO, it probably hits or reaches both of these minimum values. That's why I'm hoping to get both of the steady state solutions, and it does in fact picks up on both of the solutions. So PSO is the same. After solving for 100 iterations with 100 particles, I just add the solution for y1, which is t0, and then a solution for y2, which is t1, and then I just plot them, right? y1 versus y2, because I want to look at the state diagram, y2 versus y1. And we clearly see only 2 points, which means it does in fact have two steady state solutions. But if you look at the ODE itself and analyze its stability, you see that this steady state is oscillatory. It has an oscillatory transient response. So the system can in fact oscillate a little bit and then reach this state. But this one doesn't have any oscillatory solutions, which means that the system before reaching this, it does in fact, the solutions in fact diverge before reaching this. So based on the initial conditions. So these solutions can never be reached, this steady state solution. So let's head to Eclipse and try to look at this code. So this one is test 3. So let's run test 3. And in test 3, what I'm doing is basically creating a list of double values, two array lists, and running the PSO 50 times, hoping that eventually when I run it randomly, I end up with all the solutions, all the minima of this fitness function, which I do. And then I create a chart, plot y2 versus y1, render it, set the line width to 0, set the font to 20, and then let's plot. Yeah, as you can see, this is 1 point and this is another point. All right, so we end up with 2 points. Now what happens if, for example, we change our equation a little bit? Let's say t0, and here we also have t0. So if t0 squared is 5 over 3, then t1, so we only should have only one steady state solution. As you can see, so we have two steady state solutions because t0 can be plus or negative square root of 5 over 3, right? But for either of these values, t1 is always 2 minus 5 over 3, which is 0.33. So we have two steady state solutions pretty much at the same level for y2, all right? And let's say now we have, instead of this, we have t1 squared. So t0 can have two values, and then for each of those values, t1 can have two values. So we should end up with 4 steady state solutions, which is indeed the case, right? So this is plus square root of 5 over 3, and this is minus square root of 5 over 3. So y1 steady states are plus minus each other, and y2 steady states are also plus minus each other. So we have 4, right? Now again, what determines which steady state solution the system can in fact reach is the initial conditions, all right? So what I'm going to show you here is that if we start with our solution, or 3y1 squared minus 5, 2 minus y1 minus y2, this is our original example, and let's look at the test 4, which is solving this system of equations, 3y1 squared minus 5, 2y1 minus y2. So here we have y1 squared, and this is our deriv n function, 2 minus z0 minus z1. Z is our vector, basically our state vector, and 3z0 squared minus 5, initial condition 0, and initial conditions for y1, y2, let's say 1 and 0, all right? And we're solving the ODE for x0 to x0 plus 50 using Runge-Kutta fourth order. See, we have the oscillations and we reach the steady state. One of the steady states is basically square root of one of the steady state is 1.291, the other one is 0.709. So 1.291 and the other one is 709, okay? And we have some oscillations around, and so let's change the initial condition, for example -1. You see, we still get the basically we still get the same steady state, right? 1.291, and then but then the initial conditions are different. We see the oscillatory behavior. We start from -1, we start from 0, okay? Everything is good. But the question is, can we reach the other steady state? So if I want to reach the other steady state, y1, let's try to make it large, let's say 4, right? Because the steady state solution is -1.29. And let's also keep this as 0, for example. So we hope to reach the steady state solution for the second solution. Let's see what happens. As you can see, in fact the solution starts to diverge, or the system becomes unstable. So as you can see, we have a exponential that growing very fast, and both solutions end up with a growing exponentials. One of them is positive, the other one is negative. No oscillation happens, so the system becomes unstable and the solution in fact diverges, right? So pretty much no oscillation. If I set this, for example, to minus or maybe 10, again the same thing, the solutions start to grow exponentially. So before reaching the second steady state solution, the system in fact diverges, and it's not possible to reach the second steady state solution. So steady state solutions are not just about the initial conditions. The behavior of the ODE itself can also determine whether or not the system is able to reach a particular steady state solution. All right? So I hope you enjoyed this lecture, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to look at the general Runge-Kutta family methods for solving ordinary differential equations, either a single equation or a system of ordinary differential equations. And we already looked at the Euler method, midpoint method, and then the Runge-Kutta fourth order, and we mentioned that Euler method and the midpoint method are actually in fact part of the Runge-Kutta family. But what is the general Runge-Kutta family? So the general Runge-Kutta family, again, the idea is the same. It creates an iteration or a sequence of y values, the solution values for the solution, and these solutions can be either a single function if we are solving one single ODE, or a vector, okay? And could be a vector of solutions, n solutions, which are the solutions of n system of ordinary differential equations. So in general, we end up with an iteration, yn plus 1. At the n plus 1 step is yn plus something. And obviously h is the step size. And again, we mentioned that we always, for solving ordinary differential equations, we always use uniform steps or uniform partitioning. So I'm going to write it again here, because it's just simpler and partitioning. It's just easier to deal with compared to the quadrature methods or nonlinear step sizes. So h here can be considered a uniform step size, and then so in the nth step of the solution, in this sequence that converges to the value of the solution of the ODE at a given point, at x, for example. Again, let's go back and just quickly look at the approach here. So the approach is that if the initial condition is given at x0, which is equal to a, y0 is given, which is y of a, and we want to find the value of the solution y at some later point b, we basically partition the interval between a to b into n sub-intervals, and the length of each sub-interval is h, which is a uniform partitioning, so all the sub-intervals have the same length. And we said that we create a sequence yn, right? y0, y1, y2. From y0 we find y1, and then y2 all the way to yn. And we said that this sequence, as we increase the number of sub-intervals, the accuracy becomes better and better. So this sequence yn, as n goes to infinity, it does in fact converge to the value of the y, the solution at the point b. And then we said that if we want to find the solution at many x points, we just do this for every single point, right? Now, we said that this sequence can have an order of error, right? So we saw that this yn, the way we create this iteration, yn plus y equals y, so this can give us an error between y of b, for example, the value of the solution, the exact value, and the numerical solution yn, the iteration. And we said that for Euler it's order 1, order h. For midpoint it's order h squared. For Runge-Kutta fourth order, we saw that it was order h to the fourth power, right? And then so in general, there's the Runge-Kutta family has this format. So there are a few things. One is this s parameter. So we already know what h is. H is the uniform step size. Yn is the value of the iteration, right? y0, y1, these are the sequence that we calculate starting from y0. So we need to know S. S is called the number of stages, right? It's an integer, positive integer. It's called, and it starts from 1, so 1, 2, 3, etc. S is called the number of stages. B and K, Bi and Ki. So we need these three factors, S, Bi, and Ki. So Bi is just some numbers, right, that are given. For example, for midpoint, it was 1 over 2, right? For Runge-Kutta, it was 1 over 6, 1 over 3, 1 over 3, 1 over 6, something like that. And then Ki depends on how many stages we have. For example, K1 is always f of x and yn. So if I'm at step n and I want to calculate step n plus 1, K1 is always f of xn plus and yn. K2 end up with we have another sequence of coefficients, which is C, C1, C2, C3, all the way Cs, if we have S stages. And another matrix of coefficients Aij, right? So we need to know S, we need to know Aij, because Ki's are determined based on the C and A. So we need to know Aij, Bi, these coefficients, to be able to do this summation. And then in order to find Ki, we need to know Ci, this C coefficient, and this matrix coefficients Aij, right? Aij, Bi, and Ci. We need them. So S, the number of stages. In general, S gives us the order of magnitude for the error, right? Aij, Bi, and Ci are specific to a particular S. And the way we sum these up in a very nice visual way is called basically the Butcher tableau, right? The coefficients for any Runge-Kutta method, any family of the Runge-Kutta method, is summarized in the Butcher tableau. And the Butcher tableau is in something like this. So we have this half matrix, right? A11, so it has S rows because we have S stages. And then Bi's are given at the end, right? B1, B2, Bs, and Bs minus 1, and Bs. These are these coefficients that we know, and we need them. And then in order to find Ki's, each Ki corresponds to the ith row here, right? In order to find Ki, we need to know Ci, and then the Aij's for that particular Ki, all right? For example, basically here, C1 is always 0, A11 is always 0, so K1 is f of xn and yn, right? And for a particular row, Ki, Ci, these C coefficients are for incrementing the x, so xn plus Ci times h, all right? So this, and the Aij coefficients are for incrementing the yn, all right? So the yn plus h times Aij times Ki. So it's kind of like a recursive way. In order to calculate K2, we already need to calculate K1 first, all right? In order to calculate K3, we need to calculate K1 and K2 first. So let's just have a quick look at the first few rows. C1 is 0, A11 is 0. So K1 is f of xn plus C1 times h, which is 0. So it's just xn. And yn plus A11 times K0. There is no K0, and A11 is also 0. So K1 is always f of x and yn, all right? And then K2 is f of xn plus C2 times h, this row, and yn, so the increment of yn is yn plus h times A21 times K1. So the increment of y is h times A21 times K1. K3 is basically f of xn plus C3 times h, and then increment of yn, so it's yn plus h times A31 K1, A32 K2, okay? And all the way to the end, Cs. Ks is f of xn plus ch times h. This is the increment, h times this coefficient is the increment of xn, and these coefficients times K1, K2, etc. times h are the increment of y, all right? So there are two very important things for a general Runge-Kutta family in the Boucher tableau. The first one is the consistency condition. That means that the summation of the Aij coefficients at each row must be equal to the C in that row. That's one of the main conditions. So we see that A11 is C1, yes. A21 is equal to C2, it's always the case. A31 plus A32 must be C3, all the way, etc. All right? And we always need the B1, B2, all the way to Bs. But then the other one is the order of error. If order of the error for a S stage Runge-Kutta method is order of h to the p power, all right? Then this table tells us what is the theoretical minimum for S that we need to achieve that order of error for the numerical integration, all right? So the most important thing here is that if I want to have order of 1, 2, 3, 4, theoretically I only need 1, 2, 3, and 4 stages. So the minimum number of stages is equal to the order of the error that I'm looking for. However, after 4, something very interesting happens, that if I want to have order of h to the 5th power, I cannot have 5 stages. I need to at least have 6 stages. And that's very clear here. So for order of h to the 6th, we have 7 stages, and etc. For 8th order of h to the 8th power, we need 11 stages. That's why I mentioned before that the 4th order Runge-Kutta is like the sweet spot. Why? Because after that we need to have 6 evaluation of the functions, and then it just grows rapidly. So it may not be computationally interesting, and the 4th order Runge-Kutta is kind of like the sweet spot, and it always, in most cases, it gives us good accuracy with good speed, because we only need to evaluate the function 4 times, right, and get a 4th order error. Now if you've already looked at the midpoint, so Euler is a stage, 1 stage, right? Everything is 0 here, and C1 is 0. So Euler is yn plus 1 is yn plus h times b1 times k1. b1 is 1 and k1 is f of xn and yn. So Euler is the simplest one. And obviously you can see here that with 1 stage we get an order of 1. With 2 stages, which is the midpoint, we get order h2, h to the 2nd power, etc. So I have here a few examples. Midpoint, it has 2 stages. Theoretically it can give us order of h to the 2, 2nd order error, and the Boucher tableau is this. So the first row, we need 2 k values, k1, k2. Yn plus 1 is yn plus h times b1 k1, b2 k2, and b1 is 0. So it's only 1 times k2, b2 times k2, all right? That's the iteration. And in order to calculate k2, we need to calculate k1. So k1 is always, so the increment of xn is 0 because c1 is 0. The increment of yn is also 0 because a11 is 0. And people usually don't write a11. But so k1 is always f of xn and yn. And then k2 is f of xn plus the increment of xn, which is c2 1/2 times h, and yn plus the increment of yn, which is h times a12 or a21, which is 1/2 times k1. And this is exactly what we looked at when we talked about the midpoint method, all right? So k2, so yn plus 1 is yn plus h times f of xn plus 0.5 h, yn plus 0.5 h k1, which is f of x and yn, all right? And this gives us order h squared. 4th order Runge-Kutta, it has 4 stages, and in theory it's the minimum stages that we need, or we can have minimum stages that we can have to end up with a 4th order error, right? So this is the Boucher tableau. We have 4 rows, C0, C1, C2, C3, C4, and these are the A coefficients, and these are the B coefficients. And the iteration sequence is yn plus h times sum of bi times ki. H times b1 is 1 over 6 times k1, b2 is 1 over 3 times k2, b3 is 1 over 3 times k3, and b4 1 over 6 times k4. This is our iteration, and we construct the ki's based on each row of this tableau. So k1 is always the first row, which is f of x and yn, always. K2, we calculate the increment of xn, and then we calculate the increment of yn based on the aij. So increment of xn is c2 times h, which is 1/2 times h. The increment of yn is h times a21 times k1, so 1/2 k1. So k2 is yn plus h times 0.5 k1. All right. K3 is xn plus 0.5, which is 1/2 times h. That's the increment of xn. And for increment of yn, we end up with h times 0 times k1, 1/2 times k2. And for k4, we have increment of xn is 1 times h. Increment of yn is 0 k1, 0 k2, 1 k3. So this is exactly the Runge-Kutta method. Let's go back and look at it from before. Euler method, midpoint method. Let's see, where was the Runge-Kutta? Midpoint, Runge-Kutta. This one. H times, here I defined k1 including h, but in the general Runge-Kutta and the Butcher tableau, h is always outside, all right? So it's better to consider h outside here. And we said that it's 1/6 times f of x and yn, and all the way. Now you can in fact include h in the Butcher tableau. Basically, you have to always keep in mind that the increments of xn and yn are basically these coefficients times h. H multiplies by all these coefficients, and these k1s multiplied by h. So you can in fact define h inside of each one of these k1, k2, k3, k4, etc. But it's customary not to do that. H always is outside, right? And now there are two other methods that I mentioned in the beginning of this chapter, but I never went into the details of them. So here we can easily look at them. One is the Cash-Karp method that has 6 stages, and it has an extended Butcher tableau. So the extended Butcher tableau means for BIs, we have 2 rows. All right. So the AIs and AIJs and CIs are the same, but we end up with 2 rows for BIs, and one of the rows of the BIs gives us a 5th order error, and the other row gives us a 4th order error. Here the first row gives us a 5th order error, and the second row gives us a 4th order error. And this is a very good thing to have, because then we can calculate the solution with the 5th order error, the first row, and then also calculate the solution again with the 4th order error, and know that in order to do these 2 calculations, we only need to calculate the KIs one time, right? Because everything is the same for KIs. Only BIs are different. So we can easily get a 4th order and the 5th order errors simultaneously. But we can then use that as a comparison. So the difference between the 4th order and the 5th order error gives us a sense of how much the error is, the general error, right? And based on that, we can actually adjust the step size. So h doesn't have to be the same as we progress from x0, from A to B to C to D, etc., right? As we progress for the solution in the x-axis. We don't need to, and that's the basic idea for adaptive step sizes, all right? So Cash-Karp method, and the other one is Fehlberg. Again, it also has 6 stages, and sometimes it's also known as Runge-Kutta Fehlberg 4-5. RK45 is basically the Fehlberg with 6 stages. It's different from the 4th order Runge-Kutta. So when we say 4, 5, it means it can give us both a 4th order error and a 5th order error. And that's typically what is being used for adaptive step size solutions, adaptive step size algorithms, all right? And here's the Butcher tableau. Again, the first row gives us the 5th order error. The second row gives us the 4th order error. And once again, the implementation in our Java code is exactly the same as before. We first create a sequence, Fehlberg sequence, that converges to the value of the solution at x1, for example, starting from the initial point. And then the only thing that changes is this for loop that generates the iteration, right? Yn sequence. And we implemented this for Euler, Midpoint, Runge-Kutta. Now we're implementing it for Fehlberg, all right? And everything else remains the same. So this for loop, this is a multi-line lambda expression that creates Yn. And this for loop basically uses a uniform partitioning for x and then an iteration for y. So Yn plus 1 is Yn plus, and I'm implementing the 5th order Fehlberg method. Y plus h times b1, k1, b2, k2, b3, k3, b4, k4, b5, k5, b6, k6, all right? So b1 is, for 5th order, is 16 over 135. Just make sure that you use the double numbers, not the integers, because if you just write 16 over 135, Java compiler by default assumes that you're dividing integer by integer, so it doesn't give you the exact double value, and that causes pretty much this Fehlberg to fail, all right? Make sure you convert this to double. At least one of them should be double, so that the end result is also double. So I'm writing k2 multiplied by 0, but you don't need to write it in general because b2 is 0. And then 6656 over 12825 times k3, etc. all right? So I have k1, k2, k3, k4, k5, k6, and in each step I calculate all these 6 as xn and yn, and then we go to the next xn plus 1, yn plus 1, etc. So k1 is always f xn yn. K2 is the increment of xn is 1 over 4 times h, so x plus 1 over 4 times h. The increment of yn is 1 over h times 1 over 4 times k1. Y plus h times 1 over 4 times k1. For k3, the increment of xn is 3 over 8 times h, so x plus 3 over 8 times h. And then the increment of y is h times 3 over 32, h times 3 over 32 times k1 plus 9 over 32 times k2. And again, I'm converting all of these to double to make sure that the division is correct, all right? So etc. For example, in the last row, the increment of x is 1 over 2 times h, and the increment of y is h times minus 8 over 27 times k1, 2 times k2 minus 3544 divided by 2565 k3, etc. all right? And that's the implementation of the Fehlberg. And once we have this sequence, the rest is exactly like before. So let's head to Eclipse. In my ODE, in the ODE solver, now I have this Fehlberg sequence. I have both 4th order and 5th order, and here I'm using 5th order, so the 4th order is commented out, all right? And once we have this sequence, we can calculate the value of the Fehlberg, the solution, by getting the sequence and evaluating at after 10 iterations in the sequence, right? The 10th term of the sequence, all right? Just like Runge-Kutta, for Runge-Kutta, we also use the 10th term, 10th step, or anything after that is probably fine. And then if you want to get a solution for an array of x values, we call the Fehlberg, we update the initial condition, and each step we use the previous solution, previous step as the initial condition. That's why our accumulated error remains very small, right? And this is a very standard thing. The only thing that we change the name of the sequence and the Feldberg. And if you look at, for example, Runge-Kutta, as soon as we implement the sequence for that method, evaluate at 20, and let's also evaluate this, for example, at 20. And again, Runge-Kutta use the sequence evaluate at 20, and then for an array of x values, everything is, the code is exactly the same. We just change the name of the method here. All right. And then in the test package, I have the test Feldberg. So here I'm solving basically y prime equals y squared with y0 equals 1. So derive function, because this is one ODE, I call the derive function x and y, returns minus y squared. The initial condition for x is 0. The initial condition for y is 1. I create an ODE solver, and if you recall, I defined this ODE object before. It has only a static method. Basically, it's a helper class, and what the helper class does, it has private constructors, so the user cannot instantiate it. But it has one method that has been overloaded, get solver, all right, and it's going to help based on the basically it's going to help the user to select the correct ODE solver object. So based on what derive function the user passes in and what initial conditions. So the user doesn't know which solvers we have. The only thing that the user needs to know is what kind of derive function to define. So derive function means a single real valued ODE, and once we call the ODE.getSolver and pass in this function, it already returns the correct value. So it returns an object ODE solver, the correct solver, right? And then I want to find the solution from x0 to x0 plus 50 for 1000 points with these initial conditions, and I'm going to use compare four methods: Feldberg, Runge-Kutta, Euler, Midpoint. So blue is the Feldberg, red is the Runge-Kutta, green is the Euler, and then the black is Midpoint. So let's run this. As you can see, we pretty much have the same solutions. So all of them seem to have enough accuracy. Let's see if we can differentiate them. Yeah, we're starting to see something. So green is Euler, so it has the least accuracy, and then the black is Midpoint, blue and red are Feldberg and Runge-Kutta. They pretty much have the same accuracy. You see there's a little bit of difference. It's extremely small. So yeah, both Runge-Kutta and Feldberg give good results here. And Feldberg gives us a 5th order error. Runge-Kutta 4th order gives us a 4th order error. And all of them are pretty fast, all right? So that's how we implement Feldberg. Again, if I want to use the Feldberg now in the ODE system solver, for example, everything else is the same. So for example, here we have the array sequence for Runge-Kutta. What I'm going to do is do exactly the same thing for Feldberg, all right? And all we need to do, we need to just change this. So from ODE solver, I get the Feldberg sequence, and then let's copy this. So we have to have ND arrays K4, K5, and K6, all right? And basically, let's see. Let's copy all of these here. Let's remove this 4th order one. And then K1 becomes basically func.values. and we're going to remove the h here and put the h here, h times k1, all right, and then value y dot array, right? So this is our k1, and then k2, we're going to remove this, and k2 becomes values. The increment of x is correct. The increment of y is y dot so y plus this, all of this becomes an ND. So y is an ND object, ND array object. K1 is also an ND array object. The operators are already overloaded, and we have to call the basically let's see. So I feel like there is an extra parenthesis here. No, okay, so what we want here is this one that encloses this and called the array. Okay, so this is k2. X is real number, so this function is basically deriv n function. So k2 is also done, and then k3, the same thing here. Let's do this, k3, and also end the array, k4, k5, k6, 5, 6. All right, and then y is this iteration basically. All right, operators are overloaded, so we are good. We're implementing the fifth order, and then k2, k3 is this func, and the values, we take the y plus whatever that is here, we put this one here, dot array. All right, so k3 is okay now. K4 is this line thing, and we put it here for k4, func dot values, and basically we are going to add another, let's see, so it's this one dot array. This is k4, so k4 is gone now. Let's go full screen here. So k4 is gone, and now k5, func dot values y. Okay, so we do this dot array, so k5 is good now, and finally k6, values, we end up with this and then this, and get the array representation. All right, and again we're doing all this ND array to not go into the a lot of for loops here, because now ND arrays, the operators are overloaded. It makes us create a very nice nice looking code. All right, but once we have this Fehlberg sequence, everything is exactly the same. So if I want to calculate the solution at some number, at some x, using the Fehlberg, I call the Fehlberg sequence, all right, and then evaluate it at 20 terms, at 20 steps, and then the array. And if I want to find the solution at an array of x values, I again have Fehlberg. Everything is the same here, I just call Fehlberg. All right, everything is exactly the same, and that's how easy it is to solve. And then we can also implement cache carb. It doesn't really matter that much. It's eventually up to you. Every ODE solver method has its own advantages, because again, solving ODEs also depends on the ODE itself, the behavior of it, the stability of the ODE, and other things that we have to consider. So there is no one method for solving all the different types of ODEs, right? But typically, fourth order Runge-Kutta is the normal thing to do, right? So this was basically the general idea of the Runge-Kutta family methods, and I hope you enjoyed this lecture, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations or solving systems of ordinary differential equations. Now, so far we've looked at different topics, and we always solve an ODE or a system of ODEs based on the initial conditions. So it was always an initial value problem. But we can also solve some sort of boundary value problem. So we are given an ODE or a system of ODEs, and instead of having all the initial conditions for all the functions, we are given the boundary conditions for example, one of the functions or for a couple of the functions. Now you have to keep in mind that the number of conditions, whether it's an initial condition, boundary condition, should always equal the number of equations. Otherwise, we cannot uniquely solve the system of the equations, right? So sometimes there are unknowns in the initial conditions, right? So let's say we have two functions, y1, y2, and y10 is known, y20 is not known, okay? But the value of, for example, y1 at some later point is also known. So we can use that information to actually find the value of y2 at 0, the initial condition for the y2. And once we find that, we can in fact solve the differential equations and find the unique solution. So these unknowns must be solved for by knowing the solution at some other points, okay? And this translates into a boundary value problem, BVP. So it's not an initial value problem anymore because we do not know the initial condition for some of the functions. And we can use root finding methods. So basically we're going to solve the ODE anyways, okay? But we're going to define it such that the initial condition that we do not know becomes the roots of a root finding problem, all right? Which combines with our ODE solver, right? So here's an example that clarifies all these points. Let's say we have a system of two ordinary differential equations, y1 prime equals y2, y2 prime equals minus y1 plus 2. And we know that the value of y1, the first function at x equals 0, which is our initial point, is 0. But we do not know the value of y2 at 0, all right? So we do not know the initial condition of y2. But we are given that the value of y1 at some later point a is equal to 0, all right? So basically this is a boundary condition problem or a boundary value problem because from x equals 0 to x equals a, we know if these are the two boundaries of our interval that we're looking for the solution, then we know the conditions at the two boundaries for one of the functions, but not the initial condition of the other function. Well, the question is this then solvable? And the answer is yes, the system can be uniquely solved. And here's the code. So what we're going to do is we're going to define the problem such that the initial condition of y2 at 0 becomes a root finding problem, all right? Becomes the root of an equation. And what is that equation? So what we're going to do, we're going to basically solve the ODE by assuming so for different values of y2, okay? So we have y1 at 0, but we do not know y2 at 0. So we solve the ODE for different values of y2 at 0, and then we look for the specific value of y2 at 0 such that the y1 at x equals a becomes 0, and this can be easily translated into a root finding problem. So this is our deriv n function because we are solving a system of more than one ODEs, okay? And it's a real valued problem, so the functions, both of them are real. So that's deriv n function, x and z is our state variable. Let me write it down here. Z is y1, y2. This is our state vector or state array, and y1 and y2. Okay, so z are a state variable or a state vector. So and then this must returns the right hand side, right? The vector or the array of two equations. The first one is y1 prime, which is y2 or z1, and the second one is y2 prime, which is minus z0. So minus is here, z0 plus 2. All right, so that's the differential equations. We give a some value, let's say 5. x0 is 0, so from 0 to 5, and y1 at x equals 0, so y1 0 is 0. We already know the initial condition for the y1. And then we define an ODE system solver, because we have to pass in the derivative n function to an ODE system solver, new ODE system solver. We pass in our array of functions, the initial condition for x0, for the initial condition for the y0, for the y array, y1 and y2. Right now I'm passing a empty double array, so the initial conditions right now are set to 0 0. Okay, and then I define a root finding problem. So the way this works is that what I'm saying is that I look for those values of y2 at 0 such that it causes the y1 at x equals a to be 0. So I have to define a real root function, root func. The variable is y2 at 0, and I create the array of initial conditions for the ODE, because eventually I have to solve ODE, right? Each time I'm trying a different y2 0, I have to solve the ODE. So initial conditions are y1 0, which is fixed, y2 0, which is the variable of this root function, and then we set the y0, the initial conditions for the ODE system solver, to initial conditions, and then we find the solution at x equals a using, for example, Runge-Kutta method. So double z ODE solver dot Runge-Kutta at a. So it returns an array of two values. The first one is y1 at a, the second one is y2 at a, all right, which is z1. So, and we want to enforce the fact that y1 at a should be 0. And remember, real root function, when we pass it to a real root object, real root function basically a function that is solved for the variable by setting the root function to 0. So if I return the value of z0, then the root finder finds for the value of y2 0 by setting y1 at a to 0. All right, so this is our real root function. We're solving for y2 at 0, because once we have it, by enforcing this boundary condition at x equals a for y1, then we can run a final solution. We can run another round of solving ODE with these two initial conditions, and then the same old results. Okay, so the real root function y2 0 is the variable, and basically this function essentially solves the ODE with the given variable, with the given value for y2 0, and returns y1 at x equals a. And then the real root object is root finder. We pass in, and then the solution, I'm using a Newton-Raphson method or Newton method with an initial guess of 0 with 100 iterations. All right, and then if he finds a solution for y2 0, so if the ODE system has a unique solution, we should be able to find a unique solution for y2 0. So double y2 0 is root finder, use the Newton method with an initial guess of 0, 100 iterations, and then I'm just printing the value that it finds. And then eventually, now that I have find y2 0, I already have y1 0, so it's just doing using the ODE solver with the correct initial conditions set y0, now it's y10 and the y20 that we just found, all right, from the root finder. An array of x values from x0 to x0 plus 50, 1000 points, and then ODE solver.Runge-Kutta for this array of x values. It returns a two-dimensional array. The first row is all the values of y1, the second row is all the values of y2, and I'm just plotting the results, all right? So z0 or y1 with blue color, z1 or y2 with red color. Now as you can see, we are definitely able to find a unique solution for y20 and then be able to solve it. And as you can see, if I look at the solution that has been found for y1, at 0 it's 0, at x equals a, and remember a was 5, it's also crossing 0. And as we expect, the solution must be oscillatory, right? So the solution is oscillatory, and we also find y2, right? y2 at 0, and as you can see, y2 at 0 is some value between 1 and 2. Okay, so this is how we can solve a boundary value problem by using our ODE solver. Now the caveat here is that, yeah, of course we need to basically when we're trying to find y20, we have to basically solve the ODE many times, the system of ODEs many times in this root finding process, right? And that may not be the best or most efficient way of doing it, but it's the most straightforward. And because our ODE system solver or ODE algorithm that we implemented was pretty efficient, it takes like 20 or something milliseconds to do one round of solution, so it doesn't take that much time. So let's head to Eclipse and try to actually run the code and maybe time it and see how long it takes to actually go through the whole process. So we have this ODE package, and if you recall, we have 4 driv function interfaces: driv function, driv function complex, driv n function complex. ODE solver solves one real valued ODE. ODE solver complex solves a one complex valued ODE. ODE system solver solves a system of real valued ODEs, and ODE system solver complex solves a system of complex valued ODEs, right? And here I have this test BVP, boundary value problem. In test 1, that's the system, that's the example that I just discussed. y1 prime equals y2, and y2 prime equals minus y1 plus 2. And our state vector is y1, y2, and we're defining the root finding. We're solving. Let's look at the value of y20 by running, and then see what happens. So I'm going to run. As you can see, it solves using the Newton method, and with the initial guess of 0 and the maximum iterations of 100, and it's able to find y2 at 0 is equal to 1.4943627. all right? And if we look at here, the blue one is y0, and as you can see, it starts from 0, and at x equals 5 it must cross 0 again, and as you can see, at 5 it definitely crosses 0 again. And we expect to see this oscillatory behavior because y1 prime is y2, y2 prime is minus y1, so there is a change of sign. All right, so that's how we're combining our ODE solving algorithm with root finding algorithm to solve a boundary value problem instead of a initial value problem. All right, now I'm going to time this. So from here, let's create a timer, new timer, and I'm going to use the timer from my mathlib library, mathlibutil.timer, timer.start, and let's see how long it takes until we solve the timer.stop and timer.show. So we're going to see how long it takes to just run ODE several times and find the y20. Takes 22 milliseconds, almost no time. All right. Now let's see how long it takes to actually, after finding the and the other reason it takes very long time is very short time is because we're using Newton's method, right? If I go back to our real root object and the Newton's method, if you recall, if we don't supply the drift function, the analytic derivative of the function, it just tries to calculate the derivative using the center approximation with an order of h squared error. All right, but then it's Newton's method or Newton-Raphson method, so it's a quadratic convergence, so it's kind of like the fastest convergence that we can get. So let's put the timer here. So I'm going to time it to see. So we solved for the root and then we solved for the ODE. It takes 48 milliseconds, almost twice as it takes for the just finding y to 0. Okay, so it's still pretty fast. It's very fast. Okay. Now in test 2, let's go back to the PowerPoint. So this is the whole idea, and we can do other things. For example, in physics, typically, especially if we look at the like waves problems or quantum mechanics problems, there is a family of problems called eigenvalue problems. Now, eigenvalue means that we apply a derivative operator or differentiation which is linear in the function that we're looking for, and it becomes equal to some number times the function itself, and that number is called the eigenvalue of that operator. So here, for example, this is the Schrödinger's equation, time independent Schrödinger equation, and we need to solve for the wave function psi, and also we need to find the corresponding energy values, energy states. All right, so in the Schrödinger equation, for those of you who are not familiar with it, we apply this operator, which is the kinetic energy plus this potential energy u of x as a function of space x, y, z. Here it's just one dimensional, so as a function of x. So the left hand side is the operator of the Hamiltonian, which when applies on the time independent wave function, it should return the energy state of the energy of that state, and then multiplied by the wave function itself. All right, so this is definitely an eigenvalue problem. So in quantum mechanics, we always need to solve this eigenvalue problem, and energy values or the eigenvalues typically end up being discrete values. It's not a continuous spectrum of energies. So E is an unknown, and also the psi, the function, is also unknown. But we do know the distribution of potential energy, and we also have these coefficients, mass of electron, rest mass, and the reduced Planck constant. So we're looking for E and also the wave function. All right, so E is a parameter in the differential equation that is unknown. So these unknowns must be solved for by knowing the solution at some other point. All right, and we already know that. So let's look at the example. So in a very nice abrupt quantum well, right, with a potential well, let's say from let's say the length of the well is a, and x equals 0 is right at the center, and therefore the extent of the well is from minus a over 2 all the way to plus a over 2. All right, now let's assume a simple case where the potential energy is 0 inside the well and it's infinite outside the well. All right, so that's the simplest case. And if the potential energy is infinite outside this region, then the electron can never reach enough energy to get out of the well, so the electron can never be outside this region. So we already know that this psi function, the solution of the ODE, must be 0 right at the edge and outside. If outside 0, it should definitely be also 0 right at the edge. There's no other way, right? So no tail outside the well, and psi must, because psi is a continuous function, there is no way that psi is discontinuous. So if it's 0 outside, there is no tail outside for infinite energy outside, then right at the edge, left edge and the right edge, the psi, the wave function, must also be 0. All right. So here's our example is one-dimensional Schrödinger equation in infinite potential well, and we need to find energy eigenvalues E. And because we're talking about a real electron system, the energy values should be real values and in general should be positive. There are cases where, not for electrons, for other fundamental particles, that the energy values end up being negative, but for an electron, physically what makes sense is for the energy values to be positive. So we don't know what these eigenvalue energies are, and E is an unknown, but we have a boundary condition. So this is the key. Just like the previous slide that we had a boundary condition, here we also are given a boundary condition, because physically electron can never be outside, and because of the continuity of the psi function, the electron probability must be 0 at both ends, at minus a over 2, at a over 2, this be 0. So this is not a typical initial condition problem. We have a boundary condition problem, okay? Now furthermore, this is not a first order equation, this is a second order equation. And we already have seen how to solve this. We break it into a system of two ODEs. All right? One represents psi, the other one represents psi prime, right? The first derivative, and then we can solve that system. But again, it becomes exactly like the previous one. In this case, we also had the boundary condition on one of the functions, and we solve for the initial condition for the other one. But here, we are solving for the energy state, right? Therefore, we have to do some assumption on what the psi prime is. And if you look at the more details, if you look at actually the math of the solution, is that this psi prime eventually ends up being a normalization for the basically psi function, right? Because this is a probability, so it should have some sort of normalization property, because it's a probability at the end. So in order to find E, we need to have some assumption, or we need to assume some value for psi prime at x0, which is minus a over 2 at the initial point, right? So we cannot solve without knowing psi prime at x0, and also without knowing E, because we have two unknowns, but we know that this boundary condition, in order to give us a unique solution of a system of two ODEs, because this second order differential equation becomes two first order differential equations when we break it into a system of two ODEs. So here I'm just assuming that psi prime is 1. If you assume another number, the whole solution just gets multiplied by that number, because it's just a normalization. All right, so we're going to assume that psi prime is 1. So we already have established the initial conditions. We don't know what E is, so we cannot solve the ODE. So first we need to find E, this eigenvalue of the energy. And in order to do that, we solve the ODE for different values of E, and we enforce the condition that the psi at a over 2 must be 0. So we again use our root finding algorithm to find the E by enforcing this equation, this boundary condition. And then when we find that, we find E, and then we can solve the ODE. Now, as you probably can guess, the energy in a potential, the electron in a potential well can actually have multiple energy levels, right? So we expect to see an infinite number of energies. Now, the property that it should have is that these energy levels must be discrete values, and then discrete values, and for each one of them the distribution of the psi function is different. That corresponds to different probabilities of the distribution of the basically the electron. So here's the Java code, which is very simple, very similar to the previous case, but in the contrary to this slide that we solved for y20, we solved for the initial condition of the other function. Here we're solving for e. So a is 1, let's assume it's 1, and I'm going to also assume a normalization. So h bar squared over 2me, I'm going to assume it's equal to 1. It doesn't matter, we can divide everything by this and then do a change of variable for x, so it really doesn't matter. And for the, because we're solving for the inside of the well, the u function is 0, so our differential equation is basically y double prime is minus e times y. All right, assuming that the e is normalized to this value, which doesn't really matter. And if you do the math analytically, the solutions, the eigen energy solutions are n times pi over a squared. So in this case, it's simple enough so that we can solve for the eigen energy values analytically. So it's an integer number n squared times pi over a squared. And if a is 1, the energy levels should be n squared, an integer raised to the power of 2 times pi squared. So x0 is minus 0.5 times a, x1 is 0.5 times a, y0 is 0, y0 prime is 1, and the initial conditions are fixed, so we're not solving for initial conditions, right? We can assume anything for y0 prime, but it's just a normalization for the solution. And then we're going to construct a real root function, func e, all right? And we are looking for the e parameter by solving the ODE. So y double prime is minus ey, our state vector is yy prime, because we transformed this second order differential equation into a system of two first order ODEs. Derive m function func x and z, new double, z0 is y, so z0 prime is z1, which is y prime, and z1 prime is y double prime, which is minus e times z0, minus e times y. And then ODE system solver, we pass in the function, initial condition for x and the initial conditions for y0 and y0 prime. And then we look at the solution at x equals x1, which is 0.5. So we solve from x0, which is minus 0.5, to x1, which is plus 0.5a, using Runge-Kutta. And then what the equation that we're trying to enforce is that the y at x1 must be 0. The solution at x1 must become 0. And this method, when we invoke it at one particular point, x1, it gives us an array of two values, y at x1 and y prime at x1, right? So z0 becomes the value of the function y, so we return z0. And then we construct a root finder, and here I'm looking for a couple of solutions. So I already know that it has to have more than one solution, or it may have more than one solution. So I'm using, for example, the trisection method for e values from 0 to 100 in this interval, and for 100 sub-intervals, all right? And then print this list of solutions. And for each value, I divide it also by pi squared. Because if this code works, the analytic solution is n squared times pi squared. So I expect to see 1 squared, 2 squared, 3 squared, and etc. All right? So let's go and have a look at the actual code. So here's the code. Test 2, initial conditions, x0 minus 0.5 times a, x1 is 0.5 times a, and we can use Runge-Kutta or Fehlberg or any other methods. Fehlberg was the most accurate. This was the 5th order accuracy. So Fehlberg was order h5, the one that we implemented, and Runge-Kutta gives us order h4. All right. And then after that, if we find multiple solutions, we can solve the system of ODE for any one of these solutions, E values, energy values. and that will give us a different wave function, right? So after let me just comment this out first. So here I'm just solving for the E values. Alright, I have to run test 2 in the main method. Alright, let's see what we get. So I'm getting, after I divide the energy states, energy values by pi squared, I get 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, 6 squared, and 7 squared. And as you can see, the higher values, they tend to get error, right? And this error mostly comes from the error for solving the ODE, right? And it combines with the error for root finder. I mean, the error for root finder was good, so it's most likely from the ODE error. So let's increase the order of error by going to Fehlberg method, 5th order, and we expect these 16 and 25 and 36, these become closer to n squared. So we have 1, which is very close to 1, 4, 9, 16, 25. Now you see that it has the first 2 decimal places are 0. 36, the first decimal place is 0. So these become more and more accurate, all right? Okay, so now let's plot the wave function or the solution for any of these. So here I have a variable index, an integer, which picks the E value based on that, and then drift n function again is a system z1 minus E dot get index. Remember, E is a list object, so dot get at index. So I go at index 0 first. Alright, so let's run an index 0. This is wave function at index 0, alright? So as you can see, at minus 0.5 it's 0, at 0.5 it's also 0, so it satisfies the boundary conditions, alright? Now if I plot z1, here z1 is basically derivative, and we already know that the initial condition was that the y1 prime or the y prime at x equals 0, at x equals x0 should be 1. So we also have that. Yes, as you can see, the y prime is 1, all right? And we needed that assumption to be able to uniquely find the energy states. So this is the index 0. So this is also called the ground state. As you can see, the electron is basically has a probability of 0 at the edges, and the maximum probability is right at the center of the potential one. Now let's look at the next index, next energy level, which is a higher energy level. So in this case, as you can see, we have to actually look at the squared of this solution. A squared of the wave function is basically the probability density, and again it's 0 at both ends as we expect. So the energy values are found such that it satisfies these two boundary conditions, and then we see that in this energy state the electron is most likely to be found at this point, and it's not to be found anywhere in the middle, all right? And so on. We can find other energy states, for example the 5th energy state or the 6th energy state is something like this. And again, as you can see, the boundary conditions are satisfied. All right, it's 0. You see we have some error, so it's not exactly 0, but at x equals 0 it's definitely 0. All right. Now, as you probably can guess, this is not the best way to solve eigenvalue problems. There are better ways using linear algebra and the matrix formulation to solve eigenvalue problems, and we will look at that in the later lectures. So in the next slide, I'm just summarizing the fact that for this one-dimensional Schrödinger equation with an infinite potential well, so potential energy is infinite outside the well, so the solution must be 0 at the edges, And as you can see, this is mode 1, mode 2, mode 3, mode 4, and we also have a mode 0, or the zero energy, n equals 0. Basically the ground state is n equals 1, right? And that was just the ground state. So these are the analytic solutions, and again, this is the code. We construct our real root function to find the e. We need to do some assumption on the y0 prime, all right, or y and y prime at equals at the initial point, and that turns out to be just a normalization to the probability function, all right. And these are different solutions, wave function, and then once you take the square of this wave function, it gives you the probability density of the electron distribution. Okay, so I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations, and so far we have looked at the basically explicit method for solving ordinary differential equations, such as Euler method, Runge-Kutta method. In all the explicit methods, we calculated we created an iteration step, an iteration sequence, and at each step we used the values x and y from the previous step to find the new value of the function. And the idea was that if a is the initial point and we know the value of the function at an initial point, then if we want to find the value of the function at another point, at a later point b, we just discretize the interval between a and b into n subintervals, and we start from the initial point and write down an explicit equation that gives the value of each of y at each of the subintervals based on the previous value, okay? But implicit methods are not exactly like that. In implicit method, at each step we have to in fact solve an equation to find the value. So we end up with an implicit equation in terms of yn, xn, yn plus 1, and xn plus 1. And because we already know the value of the xn, yn, and xn plus 1, the only thing that remains to be found is yn plus 1. All right? Now, why do we even look at the implicit methods while we already have explicit methods? It's because of something called stability of differential equations, and explicit methods tend to become unstable for large intervals. And a measure of instability or a measure of stability is a test given by y prime equals ky with the initial condition of y of 0 is 1. Now, we said that in general our equation is always of the form y prime equals f of x and y, all right? Now, we can use different methods to solve the ODE, all right? So, and we said that in general, for the equations that typically happen in nature, in systems that we deal with, exponential solutions are the fastest, have the fastest growth and decay rates, okay? We typically don't get anything faster than exponentials. And this special ordinary differential equation, y prime equals ky with y0 equals 1, all right, can have two types of solution, either an exponential growth, e to the kx, or an exponential decay, e to the minus kx, all right? And if the numerical method ends up to have a good stable solution for this test ODE, then we say that it's a stable method for solving the ODE. And there are generally two types or two families of stability. The first one is astable, and we know that if k is negative, e to the ky, e to the kx goes to 0 as x goes to plus infinity. Now, if the numerical solution also behaves this way, if we use a uniform step size for solving the differential equation, if the numerical method also behaves like this, then we say that that particular method is A-stable. Now L-stable is more like a stronger version of A-stable. So in general, we can assume A-stability means a weak stability and L-stability means a strong stability. L-stable means region of absolute convergence has on the complex plane contains the negative part of the real axis. All right. Now what it means is you have to go actually look at the detailed descriptions of the stability to understand what this means, but I just put it here for your information, so you can just Google it or look at Wikipedia to get more information. All right. Now the key point here is that explicit methods, for example explicit Euler method, which we also called it forward Euler method, are typically unstable. All right. And Euler method in particular is unconditionally unstable, so you cannot do anything about basically regardless of what the basically there is no condition that you can put on the differential equation such that it becomes stable. And on the other hand, implicit Euler method, backward Euler method is A-stable and L-stable, so it's both of them. And what this means is that then it's basically based on if stability is a concern in our situation, then we have to consider something like an implicit Euler method instead of an explicit Euler method. All right. Now, as I mentioned, the problem with implicit method is that it doesn't give you a straightforward sequence for approximating YB based on the initial condition YA, because at each step you end up with an implicit equation. So what do I mean by that? So here in the Euler method, we said that y prime is f of x and y, right? So let's say at some point x with a step size h, we want to find the value of the y at x plus h. Now we know that y prime at x plus h is f of x and y, all right? Now for the forward method, we put here f of x and y of x. And we approximated y prime of x plus h with a simple forward approximation, forward difference, y of x plus h minus y of x over h, all right? Now we still do that here, but in the f function, instead of putting y of x, we put y at x plus h, all right? And then what happens is that then y of x plus h minus h times f of x, y x plus h becomes equal to y of x, all right? And now if we create our sequence yn that converges to the value of y at b, right, converges to the yb, starting from ya, y of a, then we end up with, so yx is basically y of n, and a step size is h, and then basically, so if we want to find y of n based on previous step, xn minus 1 and yn minus 1, this is the equation, right? So y of x plus h is basically yn, which is unknown, minus h, f of x, h here is the step n minus 1, so it's xn minus 1. But then we have yn instead of y of n minus 1, right? Equals yx, which is step n minus 1, yn minus 1, all right? So we're solving this, we're generating this sequence, and what we need to find here is yn, right? We already know xn minus 1, we already know yn minus 1, but we do not know yn. And in general, f of x and y could be a very complicated nonlinear function, right? So what happens here is that this becomes a very complicated equation, but we already know how to solve such an equation, right? We can use something like a bisection or Newton-Raphson method. So solving the equation in general is not a problem. But the problem here is that for bisection methods, for the method that require root bracketing, it's not easy to guess where exactly the yn is, right? It's not easy to base, because we really don't know the behavior of the function at any given point, so we don't know how to choose an initial bracket for the root, which is yn. That's why the Newton-Raphson method, which only requires a guess, it doesn't require an initial bracket for the root, are always preferred. And you always hear about NR iteration method. NR is Newton-Raphson. So most commercial softwares use NR iterations or Newton-Raphson because you only need an initial guess. And in most engineering and physics systems, the function doesn't have a rapid change, so you can in fact set the initial guess of the Newton-Raphson method to yn minus 1, right, the previous one. And that's how we're going to do it. So we already have a very good guess for yn, and it's just yn minus 1. And then we solve this equation, implicit equation, to find yn. All right. And this whole story about implicit equation is just because of the stability. And again, in most cases, we don't need to do this. We just use Runge-Kutta fourth order explicit or Fehlberg explicit, and we can solve the differential equation with a good accuracy and not worrying about the stability. All right, so here's an example. So this is the code. Again, everything implementing implicit Euler method is very similar to the previous cases. We start with a sequence, with a method that generates a sequence that converges to the value of y at a later point. Starting from x0, we want to find the value of y, the solution at x1, right? Y of x1. So we create a sequence that converges to that. So this is a multi-line lambda expression. If n equals 0, we're still at the initial point, so y0, else we copy x0 and y0. H is our uniform step, so we always do uniform partitioning, right? I'm going to write it one more time here, but you already know it by now that we're doing uniform partitioning, which always preferred in the ODE methods, ODE solver methods. So h is x1 minus x0 divided by n. So we're dividing the region from x0 to x1 to into n subintervals. And then I create a real root function, right? Root equation. Our root equation is going to be this one. And then real root, which solves for the roots, root solver is originally initiated to null, all right? And we know that we always had this for loop that generates a yn from yn minus 1, right? So it goes all the way from y0 n times. We have a loop, n loops basically. The loop goes n times, and then it starts from y0, x0, and eventually it should give us yn and xn, all right? So what do we need to do here? I'm going to copy x and y, which is basically x0 and y0. And the reason I'm copying them because in this lambda, we have to use, if I want to use them here in this lambda expression that defines the root function, root equation, I need to declare them as final. But then the problem is that x and y cannot be final because in each iteration of the loop, they are incremented. So I increment x because x and y start from x0 and y0 and then become x1, y1, x2, and y2, etc. So I cannot declare them final because they're not constant. Therefore, I'm just copying them and then use the copied versions in this lambda expression, all right? Whenever you're trying to use a variable in a lambda expression, it should be defined as final outside the lambda expression. Otherwise, the compiler complains about that, all right? So what is our root equation? Our root equation should be written for yn. So yn, let's call it z. It's the variable. And we know that in each step of this for loop, x and y hold the values of the current step, which is xn minus 1 and yn minus 1. So my equation becomes z minus h times f of x and z equals y, all right? Z minus h times func dot value x copy and z minus y copy, all right? So this function becomes equal to 0. And remember, z is the variable which is what we're solving for, which is yn. And in this for loop, x and y are the values at each iteration. They're the values of the current step. So we start from x0, y0, solve this equation, and the root solver is basically a root finder with this root equation. And note that I'm using Newton's method. And as I said, we already have a very good guess for the solution, which is current yn, or it starts from y0. So we start from y0, the Newton solves it with 100 iterations, max 100 iterations, and gives us y1, and then x0 is incremented to x1. And then in the next loop, in the equation, we have x1 and y1, and then we solve with the initial value, initial guess of y1. We get y2, and then x is incremented from x1 to x2, and etc. So this for loop can correctly generate the sequence that we want by solving the implicit Euler equation. And after that, everything else is the same. If I want to actually find the solution at x1, I call the sequence, I create my sequence that converges to the value of the solution at x1, and do a fourth order Richardson acceleration and evaluate it at some step of the sequence, let's say 100 terms into the sequence after fourth order Richardson acceleration. And as I mentioned, we typically use Newton-Raphson for finding the roots, and the reason we're doing that because then we don't need to hassle with looking at how to choose a root bracket, how to choose a bracket for the root, and the initial guess for yn plus 1 is just yn, and that makes life easy. All right, so here's an example. We had this before for the explicit Euler, now we compare it with the implicit Euler. So y prime equals negative y, and y of 0 is 1. And we already know the solution, which is e to the negative x. And on a log scale, this blue curve, which is a perfect line, is the exact solution. And this red one is the Euler method. Note that this Euler method doesn't have any, I didn't include the fourth order Richardson acceleration in this red one. All right. And then this green one is the implicit Euler without any fourth order Richardson acceleration. All right, so these are just the baseline Euler method, and they are evaluated, I believe, at 100 terms into the sequence. All right, now what you see is that the Euler method immediately diverges, so it doesn't really track the exact solution. The implicit Euler method, so the red one was the explicit, tends to stay closer, so it has a smaller error as we get away from the initial point, which is x equals 0. But at some point it flattens out, and this is due to the tolerance that we set for basically the tolerance that I set for solving for the root finder algorithm. We said that at some point we have to stop the iteration, right? These are all iterative methods, and that's based on the amount of absolute error that we want. And I said that here I probably set it to 10 to the negative 12 or something. So after that it just basically becomes flat. All right, so that could be a problem, but we already saw that Runge-Kutta method or Fehlberg method, they can give us very accurate result without doing any implicit calculations. So as I mentioned, the Runge-Kutta method or Fehlberg method, fourth or fifth order errors, method that have fourth order or fifth order errors are typically good, the explicit ones, but they require more calculations of the function. And if we have many equations to be solved, then Euler method is still sometimes or most of the time Euler method becomes the preferred choice, and due to the instability of the explicit Euler method, implicit Euler method is usually preferred. All right, so implicit for a big system of equations, let's say 100 equations, probably using a fourth order Runge-Kutta is not a good idea. So just the implicit Euler method plus a Newton-Raphson iteration might be a better idea. Okay, now the question is, how do you actually apply this to a system of equations? Because dealing with a system of equations is not basically easy, and the reason is that in order to solve a nonlinear system of equations, the Newton-Raphson method becomes complicated. You have to calculate a special matrix, and that's not easy, so it becomes complicated. But for a single ODE, we can use this implicit approach. All right, so let's head to Eclipse and let's quickly have a look at the code. So here I have a test Euler implicit class, right? And I have two tests. Test 1 is basically what I just discussed. I'm setting a timer, and then drift function is x and y goes to minus y, so I'm solving y prime equals negative y. I create my ODE solver, passing the function x0, initial value of x, initial value of y, so I'm solving for y0 equals 1. And then I create my Euler implicit sequence for x equals 0.5, so we're looking for y of 0.5. And then 100 indices, y and vals, these are the values of the sequence. Evaluate and then plot it. So let's just quickly run this. 82 milliseconds, and we definitely see a convergence, right? And if you recall, the explicit Euler method converged from below, and the implicit Euler method converges from above, as you can see here, right? And the convergence is still slow. So implicit or explicit doesn't make a difference in the rate of convergence or the speed of convergence, or basically the order of error for both implicit methods of the same family. For example, implicit Euler and explicit Euler, the order of error is the same. So both of the implicit and explicit Euler methods have the same order of error, which is h to the first power. However, implicit or explicit is more about the stability of the solution, right? And then here for test 2, what I have, so test 1 for just creating the sequence for a particular point of x and then looking at the convergence. Test 2 is basically solving the differential equations for many values of x. So from 0 to 50, 1000 points. And I'm comparing the exact solution, y exact, which is the solution is e to the negative t, all right, or e to the negative x for x values. And then y Euler, and which is explicit ones. So this one is explicit. And y Euler implicit, this is the implicit Euler method. The first one is explicit Euler method. And then this is the for loop. For Euler, I get the Euler sequence and then evaluate it at 100. Note that I'm not doing any Richardson acceleration. This is the pure ODE Euler sequence, and then evaluate it at 100 terms. Now obviously we expect the error to be large because Euler has a very slow convergence, so we have to go deep into the 1000, 10,000 terms of the sequence to start seeing a good accuracy without any acceleration. So y Euler implicit, get the Euler implicit sequence and then evaluate at 100 terms and then plot it. So let's run this one. And this is what I showed previously, and as you can see we have this thing because the accuracy, the root finder doesn't go below that 1 2 3 4 5 6 7 8 9, and this is like 14 digits of accuracy. Okay, so the root finder doesn't go below this. So I hope you enjoyed this lecture, and please stay tuned, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial I'm going to continue our discussion on solving ordinary differential equations, and we're going to look at one of the very interesting methods called finite different method. So this is completely different from the methods, basically the general Runge-Kutta family that we have talked about so far. So in the finite difference method is that the idea basically is that we want to solve the differential equation on a grid, and most of the time it's a uniform grid because it's just easier to deal with uniform grids. And what we do if we want to solve from x0 to xn, right? And basically in the previous method or general Runge-Kutta families, we said that if we have, for example, an initial value problem for an ODE, so at x0 y0 is given, and then at later point, let's say xn, we had to create a sequence and iterate through the sequence until we get a good accuracy for xn, right? But then if we want to find the solution at n points from x0 to xn, we have to do the same iteration for every single point, right? So in finite difference, it's not like that. In finite difference, what we do, we convert the differential equation into a system of equation, basically an algebraic equation. And if the differential equation is a linear ordinary differential equation, i.e. if I have y prime equals f of x and y, then f of x and y is linear, then I end up with a linear system of algebraic equation, and that's very easy to solve. And in most of the physics problems or engineering problems, the differential equations are in fact linear, so that's the advantage, right? So the idea here is that we set the values of y1, y2 all the way to yn as variables or unknowns that we want to find. And then based on these values that we don't know, we discretize y prime, all right? So yx becomes a vector, over this grid becomes a vector of values, right? A column matrix or a row matrix. Typically a vector is a column matrix, right? So here we're dealing with matrix algebra. So y of x becomes a vector of y0, y1, y2 all the way to yn, so n plus 1 components. And then y prime equals f of x and y can be either an initial value problem, a final value problem, or a boundary value problem specified over a and b. A is x0, b is xn, all right? So initial value or final value problem, and then we divide into n sub-intervals, right, from x0 to xn. So our grid, the size of our grid is actually n plus 1 nodes or points, right? And then the key here is to discretize y prime based on these unknown y values, the exact values of the function that we do not know, but we want to find them. So y prime, let's say the easiest way is to do a forward discretization, forward difference. So y prime at xi is 1 over h. H is the step size, which is our delta x. Y of xi plus 1 minus y of x, right? So at y0, y prime 0, y prime at x0 is y1 minus y0 over delta x. At x1, y prime at x1 is y2 minus y1 over delta x, etc. So we discretize. And then if we do that and we substitute here, we end up again with a similar sequence, with in general a nonlinear system. So similar to Euler method, if you recall, in the Euler method we did exactly the same thing, but here instead of generating a sequence that converges to the value of the y at each of these points and then doing it n times, we're going to actually create a system of n equations, right? So we put this for each of these points, we actually end up with n plus 1 equations, not n equations. Depending on whether we have initial value, final value, we have to remove one of the equations, and I'll talk about it in the next slides. So we have boundary conditions, initial value or final value, both of them are possible. And then we solve the nonlinear system, use our particles form optimization, which we already seen. If it's a linear system, we don't use PSO or any kind of Newton-Raphson method. It's a very easy to solve a linear system, and I'll talk about it in the next slides. Alright, so what's the benefit of finite difference method? We already have very nice Runge-Kutta methods for ODEs. So, I mean, finite difference method, first of all, it's mostly regarded for linear ODEs, right? For initial value problem, it's best not to use it. We already have Runge-Kutta methods. For boundary value problem or final value problem, it's an alternative to the shooting method. So if you recall, in the shooting method, we said that if we do not know the initial condition but we know the final condition, we can solve, we can do a root finding for the initial value by solving the ODE and finding the value at the final point, and then finding the initial value such that the final point actually becomes the final value that we are given. And then after finding the initial condition, we can solve the ODE based on any of the Runge-Kutta family methods, right? But for the eigenvalue problems, if you recall, eigenvalue problem is like the basically the differential operator acts on a function y and it becomes some number times y, right? And we do not know what that number is. For this type of problems, finite difference method is great because you translate the differential equation into a matrix equation, and for matrices, finding the eigenvalue is super easy. We already know how to find the eigenvalues of a matrix, and the eigenvalues of the differential equation are exactly the eigenvalues of the matrix problem. So that's very easy and that's great. So, and the other thing is that transforming the differential equation for an eigenvalue problem into a finite difference method or a matrix equation, then it can also give all the eigenvalues simultaneously, because when we solve for the eigenvalues of a matrix, we find them all together, right? And then for linear ODEs, we said that the finite difference method translates nicely into a system of linear equations, algebraic equations, and it's very easy and very numerically efficient to solve a linear system of equations. Now the key here is that how do we translate the problem, the original y prime equals f of x and y, into a matrix equation or a system of algebraic equations. The way we do it, again, we discretize the y primes over the grid, and then our y function becomes a vector of n values, y0, y1, y2, all the way to yn plus 1. So we have n all the way to yn. So we have n plus 1 components, right? And we either know the value of the y0 because we're solving an initial value problem, or the value of yn because we're solving the final value problem. So one of these two is known, right? So we do not end up with n plus 1 equations. One of them is going to be redundant anyways. And then if we do this and use the forward difference discretization for y prime, we see that the ddx of y of x. Now y of x becomes a vector, right? y0. This ddx becomes a matrix, 1 over h. So basically y0 prime, this ddx of y of x should give me a vector which has the values of y0 prime, y1 prime, y2 prime, yn prime. So y0 prime or y prime at x0 is y1 minus y0 over h. So the first row is 1 over h minus 1 and 1, right? Minus 1 is multiplied by y0, 1 is multiplied by y1, and the rest are 0 because they do not appear in the y0 prime. And again, this way we can construct this matrix that when is multiplied by the vector of y values, it gives me the vector of y primes based on our discretization, right? So we call this matrix the diff operator, or the diff ddx matrix operator. And it's a very nice matrix. Based on the forward difference approximation, all the diagonals are minus 1, all the upper diagonal are 1, and then there is the coefficient is 1 over h, or 1 over delta x, right? The step size. Okay. So that's our diff operator, and then we can translate any linear differential equation using this diff operator. For example, the second derivative becomes dx, this matrix, times itself, dx, right? And it gives us minus 1, minus 1, it gives us probably 1, 2, 1, minus 2, 1 or something, all right? And typically when we're dealing with matrices, it's easier to use the notation of Kronecker delta. So Kronecker delta is just 1 when the indices are exactly the same, and it's 0 in other cases if the two indices are not the same. And therefore the elements of this dx matrix, the ijth element is 1 over h For the diagonal, we end up with minus 1 times delta ij. So this term is minus 1 if and only if I is equal to j, or the diagonal element. The next one is I and j minus 1, or when the column is I plus 1. For example, here this one element is row 0, I is 0, j is 1, right? Let's start indexing the rows and columns from 0. So 0, 1 and row 0. So when I is 0 and j is 1, we end up with delta 0, 0, which is 1. So all the upper diagonal elements are delta I, j minus 1. And all the diagonal elements are minus delta ij, alright? And that's how we can easily construct this matrix in our programming, okay? So again, this diff matrix depends on the way we choose to discretize y prime. So based on the forward, this representation minus 1 diagonal and 1 upper diagonal is based on the simple forward difference approximation, all right? And it works great, so we do not need to go to the higher or better approximation. We just increase the number of points, or basically reduce the basically we increase the size of the grid or increase the number of discretizations. That gives us a better and better accuracy. All right. Now, how do we actually solve differential equations, ODEs, with this method, with this finite difference method? So the idea is that, okay, we have n plus 1 equations, but based on the conditions of the differential equation, either initial value or final value, one of the equations is redundant. We do not need that. So for an initial value problem, y0 is known, right? And for a final value problem, yn is known, right? So if I'm solving an initial value problem from this matrix, so eventually we transform our system into a matrix, which some matrix times the y vector equals to some vector that we already know the values based on the x. And this decomposition happens for linear systems, any linear ODE. So from now on, let's just assume we're talking about linear ODEs. So if I know the value of y0, basically an initial value problem, right? I only have n unknowns, y1, y2, all the way to yn, right? So for an initial value problem, I need to remove the first column and the last row and solve a system of n equations from row 0 to row n minus 1 and from column 1 to column n, right? So n equations. And then if the thing is that then look at the first row is minus y0 plus y1, right? So what I need to do, I need to take this coefficient multiplied by y0 and bring it to the right side of the equation, because I already know whatever values that I know from the y vector, I have to remove them from the left hand side and bring them to the right hand side, all right? So for an initial value problem, we remove the first column and the last row, and then take y0 to the other side of the equation. That's how, so basically we form our matrix equation, and then we have to apply our boundary conditions, either an initial value condition or a final value condition. And the way we do it, the way we apply it to our system of equations is that we bring the known values from y to the right hand side and set the coefficients that multiply by those values to basically we just remove those corresponding rows and columns, all right? Now for a final value problem, the value of yn is known. So I have to solve for y0, y1 all the way to yn minus 1. So I have to keep the first n rows, right? So I have to remove the last column. So we remove the last row and last column. And then what we do from the n minus 1 row, this row, we bring yn to the other side. So basically this coefficient here, 1, we have to bring it to the other side, all right? So this becomes more clear when we look at an actual problem and look at the code. But basically the idea here is that applying the boundary conditions means that we remove the corresponding rows and columns, and then bring those values, rearrange the equations or modify the equations to bring the known values to the right hand side. All right, now the question is, why do we go through this finite difference method? Didn't we already have like very nice, elegant Runge-Kutta methods? And the reason is that the Runge-Kutta families are specifically defined for ODEs, ordinary differential equations. As soon as we go to the partial differential equations, they don't really work, but the finite difference method actually works. So finite difference method, the idea is discretizing over grid, and this grid can be a one-dimensional, which is what we're doing right now, right? One-dimensional grid is basically solving an ODE, but a two-dimensional grid corresponds to a partial differential equation, and a three-dimensional grid corresponds to again a partial differential equation. So the concept of grid very nicely scales to higher dimensions, but the concept of Runge-Kutta method doesn't really work like that. All right, so that's why finite difference method is a very, very popular method when we are solving partial differential equations. So again, we create, based on a discretization, we create the representation of the diff operator, and the higher order differential or higher order derivatives are just multiplying the matrix dx by itself, right? Simply just multiply matrices for higher order derivatives. So how do we create this dx matrix? So basically it's a Java class, and I have a method here built dx. So the coefficient is 1 over x, or 1 over delta h. And then we iterate through the rows and columns, and deem the dimension of the matrix is n plus 1, right? And then dx ij, the ij component, it's just much easier to use the Kronecker delta notation. So I defined a method called delta Kronecker, which takes two integers. If the integers are equal, it returns 1. Otherwise, it returns 0. It's a very easy method, right? And it's a static method in my math utils class. So coef is 1 over delta x, or 1 over h, and then minus the diagonal matrix minus delta ij plus delta I plus 1 and j, right? I plus 1 and j, or I and j minus 1. Both are equivalent. Alright, here's an example. Y prime equals minus y plus 2x. Now obviously this is a linear function, right? So this is a linear ODE in terms of y and y prime. And we want to solve it over the interval x equals 0 to 10 with the initial condition of y0 is 1. So this is an initial value problem. So we consider y as a vector, capital Y, that holds the values of y0, y1 all the way to yn, right? So we have to specify n, or the number of the size of our grid, which is n plus 1. So here's the code. x0 is 0, so we're solving initial value problem. x1, or maybe let's call it xn, is x0 plus 10, right? This is the final value, final point, and y0 is 1. Our grid size is 501, and grid size is n plus 1, remember that? And we're going to discretize, create our matrix of x values, linear space, uniform grid, so linear space x0 to xn, and grid size. Remember, we have to have n plus 1 points, right? So n here is 500, for example, and this method linear space returns a one-dimensional array, and when we assign it to a matrix, it automatically transforms it into a row matrix, a one-dimensional row matrix. So this xvals is a matrix, and then our step size is just xvals get elements 0, 1, so row 0 column 1 minus row 0 column 0. Xvals is a one-dimensional matrix. Okay, so we already know that it's a uniform grid size, so all the delta x is the same. If it's not a uniform grid size, then what we need to do, we actually need to bring this 1 over h into the elements. Here, all the elements had the same 1 over h factor, so we could factor it out. But in general, if we're doing a non-uniform grid size, then this coef for each element can change as we go from one element of the matrix to another. All right, so it's easy to extend this to a non-uniform grid size, but in general it's better to stay with a uniform grid size. So we have our y vector, all right, and it's for the initial value problem we already know y0. So our y vector, what we need to solve for is y1, y2 all the way to yn. All right, so dy, y prime becomes a matrix D times the y vector equals minus y vector plus 2x, and we bring this vector to the right, D matrix plus the identity matrix. This I is the identity matrix. All the diagonal elements are 1, all the off diagonal elements are 0, equals 2x, and the solution for the matrix is 2 times d plus I inverse times x. All right, but in reality, inverting a matrix, especially if the size is large, let's say it's 500 by 500, it's very computationally expensive. So we do not invert a large size matrix. Instead, realizing that this is a linear system of equations, we solve a linear system by, and the main method that we typically use is a Gaussian elimination. We will get back to this when we discuss linear algebra and matrix algebra in the future lectures. But in general, for a linear system, we have a very efficient way of solving the system using Gaussian elimination method, right? So we do not invert a matrix. And again, we need to impose initial conditions. Here, it's an initial value problem. So we already know y0, so we have to solve for this system of equations from y1 to yn. So from this D plus I matrix, we take this chunk from row 0 to row n minus 1, column 1 to column n. We take this chunk, and then in order to apply the initial condition, we have to modify the first equation. So here the coefficient is 1 over h minus 1 times y0, which we have to bring it to the right side and add it to this vector 2x. All right, so here's the final code. So I'm going to the y-vals array. Here is n components, which represents y1, y2 all the way to yn, and then I define my forward diff operator, which basically this dx matrix, and forward diff operator based on the grid size, which is n plus 1, and the step size, uniform step size of the grid, which is delta x here. And then I define my identity matrix, which is just identity based on the grid size, the dimension. The right hand side becomes 2x, 2 times the row matrix x vals. And the operators are already overloaded for the matrix class, so we do not need to worry about that. And then the coef matrix becomes D plus I. So from the diff operator dot get dx matrix plus the identity matrix. So right now my system is ready. I have the coefficient matrix D plus I, and I have the right hand side, which is 2x. Now I need to do two things. First of all, I need to take only this block from the coefficient matrix and also apply the initial condition. So I'm going to impose the boundary condition, which here is the initial condition, here is initial condition, okay? And the initial condition is from right hand side, I'm going to set the element, so it's a 0, 0 element, right? Remember, this x is considered to be a row matrix. So set element 0, 0, and on the right hand side, the first row is 2x0, right, the initial point. But now I need to take this coefficient matrix, take the 0, 0 element, multiply it by y0, and bring it to the right side. So I have to subtract this coefficient times y0 from 2x0, right? So I'm modifying the right hand side based on the initial condition for y. And now I need to take this chunk of the matrix. So I'm going to solve ay equals b, and b is 2x with the corrected value for the initial condition, and my 2D array is get block. I'm going to get a block of the original matrix The block is from row 0 to row n minus 1, which is grid size minus grid size minus 2, n minus 1, and from column 1 to the end, which is grid size minus 1. This returns a matrix, get block, and then I call the get data method to convert it to a 2D array. And the right hand side, B, is basically 2x from row 0 to row basically n minus 1. So from row, and it's a one-dimensional matrix, so from row 0 to row 0, from column 0 to column grid size minus 2, because it's x vals, or basically 2 x vals. The right hand side is considered to be a row matrix. And I need to get the data, which returns a two-dimensional array, and it has only one row, so I just get the 0th row of this two-dimensional array, which is my right hand side, which has been corrected with the initial condition, this one. And then I pass my a coefficient, this chunk of the matrix, the b, which is the right hand side, and the empty array for the y values to a linear system object, and then it automatically solves and puts the values in this empty array y vals. And then y vals now contains the solution for y1, y2 all the way to yn. And if I want to plot against x vals, which also has x0, I need to append y0 to the beginning of the y vals. And I call the math utils arrays class inside the math utils and the concat method. All right. So it looks a bit complicated, but it's not that much. So you have to basically go through all these steps to create your system of differential equations, and then impose the boundary condition, the right boundary condition, by modifying the right hand side, and then create your system of linear equations, and then eventually solve them and plot them. All right. So here's the result. I'm solving y prime equals minus y plus 2x over 0 to 10 with y0 equals 1. And obviously accuracy depends on the grid size. Here we're doing 501 points. And I'm using the comparison here between our previous Runge-Kutta family, which I'm using Fehlberg. And if you recall, we implemented a Fehlberg that had the order of h to the 5, so 5th order error. So it starts from the initial point, which is at 0, it's 1, and then goes up. And as you can see, the finite difference method also gives exactly the same result. Now I think it's good if we go and look at the code. So in my ODE project, I have a new package, finite difference method, FDM, and here's my forward diff operator. It's just a class that has a two-dimensional array and keeps track of the dimension and delta x, and the constructor just takes the dimension and the uniform. So this is basically a uniform grid size. All right. And it creates a two-dimensional array and build it, and the build method just exactly does what we talked about. So this is a forward difference method. So y prime at point n is basically at point I is yi plus 1 minus yi divided by delta x. Right? This is the forward difference. So all the diagonals are minus 1, the off diagonals are plus 1, and then it can either return a 2D array that represents this matrix or a matrix object. So this matrix object is in my mathlib library in the matrix package. I have the matrix class, and we also have a complex matrix, which represents a matrix with complex elements. Here the matrix object represents real elements, the elements that are real valued, all right? And it's a fairly complete class, and operators are overloaded as well. So you can just download my Git project and just use this. And then we also need the linear system solver. So for a linear system with real data, all the coefficients and all the solutions are real values. We have this linear system, and in the constructor you pass the A matrix, the array of the right hand side, and then the empty array for the solution. All right, and it implements the Gaussian elimination method. So in the solve, if you look at the details, and we will get back to this later, it's a Gaussian elimination method, and it's a very efficient way of solving the linear system. All right, so here's our example class. So test 1 is basically solving the y prime equals minus y plus 2x with the initial condition. So this is an IVP problem, initial value problem, y0 equals 1. And it's very easy. The way we implement it is very easy and very elegant. So we define our deriv function, which represents a single real valued ODE. X and y goes to minus y plus 2x. This is the right hand side. And then x0 is 0, y0 is 1. And then ODE solver, we pass the function, we pass x0, we pass y0. And then the array of x values is from x0 to x0 plus 10, 1000 points. And we're calling one of the methods, such as Euler, Fehlberg, Runge-Kutta. I'm calling the Fehlberg, and that's it. That's done. So this is very elegant and very simple for solving an initial value problem of a single ODE. And then I'm just plotting it. So let's run. Yeah, so this is what we expect. It starts from 1, the initial condition, and it goes all the way to about 18 at 10, right? That's the numerical solution. Now let's test 2. In test 2, I'm using basically our finite difference method, and as you can see, it's not as elegant as the Fehlberg method or the general Runge-Kutta family, but finite difference in general is more powerful. And again, that's because you can extend it to boundary value problems, partial differential equations. It's very nicely extendable. So again, x0 is 0, xn is x0 plus 10, and then y0 is 1. Our grid size is 501, so n is grid size minus 1, right? All right, and then our matrix xval, this is a row matrix. For xval, it's a row matrix. From x0 to xn, obviously n plus 1, or the grid size, right? We have n plus 1 points or n intervals, and dx is just it's a row matrix, so the row index is always 0 and the column is 1 minus column 0, right? So this is basically x1 minus x0. And then I'm printing the dx, the step size, and then yval is a vector, and again it only has n elements instead of n plus 1, because we already know one of the boundary conditions, which is y0, right? So y0 is known. But then our forward diff operator is still n plus 1, right? So we form the system based on all the y0 to yn, based on the n plus 1. N plus 1 equations, right? So we form the system in the most general way, and then apply the boundary conditions, initial value, final value, or any type of condition. And based on that, we throw away some of the extra equations that are redundant and bring the known y values to the right hand side of the equation. So I have my identity matrix, which is also n plus 1, the dimension, and then the right hand side was 2x, right? The equation was, let me just copy this again here. The equation is y prime is minus y plus 2x, right? So the right hand side is 2 times the x value vector or matrix. And the coef matrix is just the d, so basically this becomes d plus I times the y matrix is 2x matrix in the general form, right? So coef matrix is the diff matrix, get dx matrix plus the identity matrix. And again, the operators are overloaded for the matrices, so no worry there, we can easily add them together. And now we form this equation. Now what we need to do, we need to apply the initial condition. And the initial condition is that we bring the first row y0 from the right hand side to the basically from the left hand side to the right hand side. So we take the 0 0 coefficient of this matrix. So basically on the right hand side, so the right hand, this is the original one, 2x. We set the element ij, the 0 0 element, which is the first element of this vector, to twice x0, which is the original value, minus the coef matrix, the 0 0 element, times y0. All right, we just remove the y0 from the left hand equation, from the left hand side, and bring it to the right hand side with the coefficient matrix at 0 0. This coefficient multiplies y0, so we bring it to the right. All right, and now we have to reduce this n plus 1 equation system to n equation system. So if I'm solving ay equals b, and then this 2D-dimensional array which represent the matrix is the coef matrix, get block. And let me just quickly go back to the PowerPoint. And again, we want to get this chunk of the matrix which removes the first column, the coefficients that multiply y0. We remove them. And this goes from row 0 to row n minus 1, and then column 1 to column n. So from row 0 to row n minus 1, and column 1 all the way to column n. All right, and get data. This data just returns an array representation of the matrix, and that's because in the linear system we have to pass in an array. And then b, right hand side, again we, after applying the initial condition which bringing the y0 to the right hand side, we have to keep the first n rows, so y0 to the yn minus 1. So here I'm going to the get block, and remember it's a row matrix, so from int row 1 to row 2 they're all 0, from 0 to n minus 1. And it returns a 2D array, and it's actually has only one row, so I get the row 0. And then linear system, coefficient matrix, right hand side, the empty array, it solves the y values, y1 all the way to yn, and then I append y0, and then plot x values from x0 to xn, from y0 to yn with the red color. All right, let's run this. So our delta x is 0.02, and as you can see, we get perfectly the same result, right? It starts from 1 as we expected and goes all the way to 18. So finite difference works fine, and let's reduce actually the grid size from 500, let's say 11. So our step size is 1. As you can see, the accuracy is not good as before, right? Again, the behavior is not bad, but here at the beginning it has some error. So if we go to 21, you see the accuracy gets better and better, right? And then if we go to 51, it should give us a relatively accurate result. Yes. All right, so let's do 501, and this is relatively accurate. All right, so that's how we solve an initial value problem with finite difference. And again, maybe the code looks complicated, but this is a general approach, and it has values that the original Runge-Kutta family don't have. And that's why finite difference is a very important numerical method in solving differential equations. Not only ordinary differential equations, but also basically partial differential equations. So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations with the finite difference method. So in the last lecture, we looked at the general idea of finite difference method, and we said that it works great for linear ordinary differential equations, and the main idea is to do a discretization of the interval and then translate the problem into a linear system of equations that once it's solved, it gives us the values of the function of the solution at the points that correspond to the grid that we define. And most of the time we just use a uniform grid, but it's not a necessary thing to do. And then we said that basically the idea is that the diff operator translates into a matrix, and then based on the type of problem that we are solving, either an initial value, final value, or if we are solving a partial differential equation, it could be a general boundary value problem. We have to throw away some of the rows, right? For example, for initial value problem, we know the y0, so we throw away the first column. So in general, we need to throw away a couple of columns. And here we're throwing away the columns that correspond to y0. So because we only have n unknowns, y1 to yn, and then we have to take this part of the matrix, and then in order to apply the boundary condition, we have to form our system of equations with the original n+1 equations, and then bring the y0 coefficient and the y0 to the right hand side. All right, for the final value, we throw away the column that corresponds to yn because we already know the value of the yn. And then after forming the system of equations with n+1 equations, we take this coefficient and basically bring it to the right hand side. And the example that we looked at for the initial condition problem or initial value problem was y prime equals minus y plus 2x. And we saw how it can give us a very accurate result if the grid size is relatively dense. So about 50 intervals is good enough. Here we had like 500 intervals. But now let's look at another case where we do a basically we do a final value problem. So in the final value problem, we said we throw away the last column of the coefficient matrix, and then we have to take the rows from 0 to n-1 and the columns from n0 to n-1. And the reason is that we don't know the value of y0, y1 all the way to yn-1, but we do know the value of the yn. Now when we do this, then because yn appears in the n-1 row as well, right? It's -1 coefficient times yn-1 plus 1 times yn. So we have to modify that equation and bring the yn terms to the right hand side to form a correct system of equations. So what I'm going to do here in this example, the differential equation is y prime equals y plus 2 times x. We're going to solve over the interval 0 to 10, but with the final condition of y of 10 is 1. So this is the condition or the value of the solution at the end of the intervals. That's why it's a final value problem. It's a final value problem. And then again, we discretize over the grid based on the n+1 variables, y0 to yn. So y prime becomes d times the vector y equals vector y plus 2y vector x, and then this comes to the left hand side. We end up with d minus the identity matrix times y equals 2x, right? So this is our general system, and then we have to, after forming this general system, we have to basically impose the boundary condition, which is the final value, and then solve the corresponding system, right? So again, we can do a Fehlberg method to solve this final value problem, and we can do it in 2 different ways. So I'm going to show you in the code. So if we go back to ODE project in the example 1, in test 3, I'm solving y prime equals y plus 2x with the final value problem y of 10 is 1. So there are two ways that we can use our ODE solver to solve this final value problem. The first one is direct method or backward solution. And the idea here is that we do exactly as we did before. So the function defines the f of x and y, which is y plus 2x. Now here, we still consider this as initial condition problem or initial value problem with our initial point x0 at 10 and y0 is 1, right? But then we solve backwards, and we can do that because all these methods, Runge-Kutta families, can work based on either a positive step size or negative step size. So both of them are valid. So we're going to do backward solution, basically IVP plus a negative step size. So basically h, our step size, is actually negative here, not positive. So ODE solver from x0, so we already defined it as an initial value problem with the initial point at 10, x equals 10, which is 1. And then our x value array is actually backwards from x0, which is 10, to x0 minus 10, which is 0, right? 1000 points. So we start from 10 and work backward using Fehlberg method. And this should work because Runge-Kutta methods don't care about the positive or negative step size. So let's run test 3. Yes, so at 10 we have 1, and then we work backward. We end up with about minus 2 at 0, right? So this is the direct method, direct application of the ODE solver by redefining the problem as an initial value problem and then working backward. Now the other way is in test 4. So let's go to the main method and try to run test 4. In test 4, I'm actually doing the forward solution. So I assume my step size is positive. And then in order to do that, I have to directly solve the initial value problem, but I don't know the initial condition. So I apply the shooting method, right? In the shooting method, if you recall from my previous lectures, we first try to find the initial condition by creating an equation that solves based on the final condition that is given here, right? So the derivative function is again the same, y plus 2x, x0 is 0 now, so this is our initial point. I create an ODE solver with a dummy y0 because I don't know y0 at the beginning. Let's set it to 0. And then I define a root finding code, so real root function, func, that tries to formulate an equation that gives me y0. That's why I call it func y0. So in the func y0, the variable is y0, and then in the ODE I set y0 to y0 and find the value of the solution at x0 plus 10, which is my final point. And then I have to solve this equation. So y1 must be equal to 1, right? I'm enforcing the initial, the final condition. So basically enforcing the final condition. So I'm forming an equation based on y0, the initial condition, that gives me the correct final condition. And then the real root, basically it's a root finder. I set my real root function, and because I don't know what the original interval is, so instead of using the method such as bisection that requires a bracket for the root, I use the Newton method. And I assume that the initial condition is probably close to the original 10. And then I want to do a maximum of 100 iterations. And this gives me actually the initial condition y0. And then I'm printing the y0. And now after finding y0, I can create my array of x values. Again, this is a forward array from x0 to x0 plus 10. I set y0 in my ODE to the y0 that I just found. And now I'm solving the initial condition problem. So this is solving forward with h positive. So I use shooting to find the initial condition and then solve the initial condition problem. All right, this is solving forward. So test 4, let's just run it. As you can see, it's basically the same result as before, right? Starting from 10, we end up with 1, right? And then at 0, we end up with about -2. And you see this y0 that we just found is -1.9989, something like that, which is pretty much similar. All right, so these two works, and obviously the shooting method is a little bit of overkill because the ODE solvers actually work backward as well as forward, so they do work with the negative step size as well, right? There was nothing in the implementation that prevents the methods that go backward. You work with a negative step size. All right, but then finally we want to translate this into a finite difference method. So I want to translate my differential equation into a finite difference method and then impose the final condition and then solve the equation. So let's see. We have d minus i times y equals 2x. So we start with x0, which is 0, right? And then xn, which is x0 plus 10, and yn is given, so y0 is not given. In the past we had y0 here, but now we have yn. And then let's say grid size is 1001, so n is 1000, right? We have 1000, an array of 1000 plus 1, and we have 1000 unknowns. So my x values, again, it's from x0 to xn, n plus 1 terms. Dx is just the first x minus the 0x, right? It's a uniform grid. And then the y values. Now the array of unknowns goes from y0 to yn minus 1. So it's an empty array of n again, but this time it goes from y0 to yn minus 1. For the initial condition problem, initial value problem, the empty array of y goes from y1 to yn because we already knew the value of y0, but now it goes from y0 to yn minus 1. And then I use my forward difference operator, forward diff operator, n plus 1 dimension and the uniform step size, which is delta x. And then I create my identity matrix based on the n plus 1 equations. The right hand side is again 2x, right? And then the coef matrix is d minus I. So diff get d matrix minus the identity, and the operators are overloaded. And now I have to apply the boundary condition. I form the n plus 1 equations. The coef matrix and the right hand side are now known, and now I need to impose the boundary condition. And the boundary condition here is a final value. So in the right hand side, I said that we know the value of yn, right? So we throw away this column, we take this basically n by n matrix, right? From row 0 to row n minus 1, from column 0 to column n minus 1. So in the last equation, which is the n minus 1 row, we have the value of yn, so we have to bring it to the other side. So in the right hand side, and the row n minus 1, so set element row 0. So the right hand side is a row matrix, so it only has one row and n columns. So basically n minus 1 column, which is this row corresponding to yn minus 1. We have to take the n minus 1, which is the original value of the right hand side, right? So twice that x at that row, n minus 1, minus, so we need to bring this coefficient in the last column, which is row n minus 1 and column n. So coef matrix get element n minus 1 row and n column times yn, right? We're bringing the yn from the last equation to the right hand side. And then again the array, so the coefficient matrix is just this chunk, this n by n matrix, which goes from row 0 to row n minus 1, column 0 to column n minus 1. So coef matrix get block from row 0 to row n minus 1, column 0 to column n minus 1, get data. And get data transforms the matrix into an array. And now in the right hand side, I go from 0 index to n minus 1 index. So it only has one row, from row 0 to row 0, column 0 to column n minus 1. Get data, it's a 2D array, has only one row, so I return row 0. And the linear system A, B, Y vals is originally empty, but then the linear system fills it out after solving. And then this holds the values of y0 to yn minus 1, and then I append the value of yn to the end of it, and then plot the y vals versus x vals. All right, so let's head to the code in the test 5. And in the test 5, exactly x0, xn, yn grid size, let's say only 501, so n is 500. And then x values, delta x, and then y values, diff operator, identity, right hand side is 2x, the coef matrix is now the dx matrix minus identity. We modify the right hand side by the n minus 1 n times yn element, and then the coef matrix right hand side, we append the yn to the solution and plot against x vals. And as you can see, it gives basically the same equation or the same result as before. So at 10 we start with 1, and at 0 we end up with about 1.9988. So it's pretty close to the Fehlberg and the shooting way of solving differential equation. So that's basically the general idea about finite difference method. In the next lecture, I'll try to look at the higher order differential equation, for example, a second order differential equation, and there instead of initial condition or final condition, we can have a boundary condition. So y at 0 and y at 10, for example, is given. So we have to modify the system in another way by throwing away both the first column and the last column. And then we also need to find the matrix that represents the second derivative. So that would be an interesting problem. So please stay tuned, and I'll see you in the next one.